Hi troops, my name is Brian Caffo. I'm an Associate Professor of Biostatistics at Johns Hopkins Bloomberg School of Public Health here in Baltimore. I'd like to welcome you to the Coursera class, Mathematical Biostatistics Bootcamp. Before I begin, I'd like to thank all of the folks here at the Bloomberg School of Public Health and Coursera for all of their technical support. So the format of the class is going to be a grueling 7 weeks of lectures where we'll have 2 lectures per week. I'll put up homework assignments that you can do or not, but the real evaluation will be 7 quizzes. Each one will have between 5 and 10 questions, and you'll be able to take them 3 times. So why would you want to put up with all this intense biostatistical training? This class will give you the foundation that you need at a rapid pace to join one of the key disciplines for solving the world's biggest health problems. All of the material for the class will be on the Coursera site. However, for the geekier subset of the class, I've created a GitHub repository that contains all of the lecture notes and materials. Just to remind you, we want a vibrant, lively, and hard-hitting discussion on the message board. However, please be civil, considerate, and constructive. So prepare yourself for 7 intensive weeks of pure biostatistical pain, but I guarantee you that the payoff will be great. Hi, my name is Brian Caffo. I'm in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. This is Mathematical Biostatistics Bootcamp, and this is Lecture 1, where we'll cover some introductory material. In this lecture, we'll talk about the basics of biostatistics and motivate it. We will abstract the idea of an experiment. We'll go over some basic set notation, because set notation in the context of probability has a slightly different interpretation than classical set notation. And then we'll cover some of the very basics of probability. Let's talk very briefly about the subject of biostatistics. My department, the Department of Biostatistics, in its 2007 self-study, we attempted to define biostatistics. The definition that we came up with, it was actually quite difficult to get everyone to agree, but this is what we came up with. Biostatistics is a theory and methodology for the acquisition and use of quantitative evidence in biomedical research. Biostatisticians develop innovative designs and analytic methods target at increasing available information, improving the relevance and validity of statistical analysis, making the best use of available information, and communicating relevant uncertainties. Now, I think there's a lot of very important topics in that definition, and it captures our discipline quite well. I have a much more simple definition of biostatistics that I like to use. And the definition that I like to think of is that experimentation and empiricism are ultimately the language of science. Inductive reasoning based on empiricism is, in my opinion, how the vast majority of science gets conducted. And I think of statistics as the language of empiricism. Simply put, that statistics is the formal syntax associated with empiricism. And so when you're studying statistics, I think you're actually studying how to conduct experiments and quantify information from experimental and empiric knowledge. Let me give you one of the most famous recent examples where existing clinical practice was reversed by empirical evidence. There was a clinical trial that published its result in 2002. And the amazing part about this clinical trial is that it contradicted prior evidence on the efficacy of hormone replacement therapy. Up to that point, hormone replacement therapy had been near universally thought of as a good treatment for postmenopausal women. In fact, the trial evidence was exactly the opposite and suggested the possibility of some harm. When conducting this experiment, the statisticians and the epidemiologists and et cetera that designed the trial had to come up with ways in which to decide whether or not to stop the trial, whether or not to keep the trial going, and how to quantify the evidence. In this case, they had a statistically based protocol that they executed, and the study was stopped due to an excess number of negative events. And I don't think I can appropriately describe how counterintuitive this was to the medical community at the time. But the key ingredient that I want to discuss is this bolded text here, where it was in fact a statistical decision based on probability that had to decide whether or not enough evidence had been collected at the time to make a decision to stop the trial or to continue going. This is an incredibly important decision because it's unlikely that another trial of this scope would have been able to have been executed anytime soon. So cutting it short would have the incredibly negative benefit of not having the full information available. However, keeping it going based on the evidence of an excess number of negative events could possibly put people at harm. So I just hope you understand the central role that statistics was playing in the decision in this trial. Another very good example of statistics kind of in the similar vein was ECMO, which is extracorporeal membrane oxygenation treatment. This is a treatment for newborn infants. It was an incredibly promising treatment. It is currently a standard treatment. And there was quite a bit of enthusiasm at the time of its creation that it would be a revolutionary treatment. So when they conducted the trial, it was very difficult to consider how you would conduct a trial for a treatment that has such obvious potential benefits. The ethical considerations in the trial wound up leading to a statistical design or randomization scheme whereby only one infant received the control therapy. That in turn introduced criticisms, sample size based, about the design itself. In this particular case, because the treatment was so potentially beneficial, it was difficult to figure out how exactly to conduct a trial to evaluate its efficacy. And in this case, only one instance were they actually willing to give the control therapy to a child. However, then immediately the degree of evidence to actually evaluate the therapy was very weak. So in this case, it wasn't just statistical considerations, it was ethical considerations and medical considerations all bundled together. So I hope these two examples illustrate the central role statistics plays in making public health decisions, in making medical decisions, and evaluating evidence. Let me just summarize again. Biostatistics is playing a central role in public health in design, analysis, and interpretation of statistical data. And here at Johns Hopkins, in the Bloomberg School of Public Health, we have kind of what I would like to consider a prevailing philosophy for conducting biostatistics that cuts across all of the departments. And of these, we include a tight coupling of the methods that we use with the ethical and scientific goals. We pay special attention to emphasizing scientific interpretation of statistical evidence and try to use that interpretation to impact public policy. And of course, we try to acknowledge our assumptions and evaluate the robustness of our conclusions to these assumptions. And I think these three principles underlie the majority of scientific research going on at the school. This is not to say this is actually the only way to think about doing statistics. Think of regulatory agencies like the Food and Drug Administration. There, they may not want a tight coupling of the statistical methods with the scientific goals. In contrast, what they may actually want is the statistical procedures to protect consumers regardless of the scientific evidence. Their loss function is, in essence, quite different. They may want to actually divorce the statistical methods from the science so that they can, in the most possibly unbiased way, evaluate a drug. This is not to say this is exactly how the Food and Drug Administration does things. I've never worked there, so I can't say with certainty. However, it's clear that different organizations and different entities would think about statistics and how it applies to scientific problems in different ways. Here at Hopkins, in the School of Public Health and at the Hopkins University more broadly, we are largely a research institution. We like to think of the statistics, statisticians, and those doing statistics as being highly embedded in the scientific process and in the scientific inquiry. So this is a very brief section, but a very important section on the idea of abstracting the notion of an experiment. Probably everyone has an idea of what an experiment is, and they are probably thinking of people in white lab coats, say with mice and test tubes and beakers and that sort of thing. In statistics, we think of an experiment in a much more abstract and general way. basically, we're going to think of an experiment as any purposeful inquiry that involves a non-trivial amount of error and randomness that we need to evaluate. That is going to be our notion of an experiment. So looking at the second bullet point, of course, something like a laboratory experiment would fall under this definition. But we also think of basically any collection of measurements from a sampled population. For example, if you wanted to study hypertension and you figured out a mechanism to sample and ask people their hypertension status, that would constitute an experiment just as much as the laboratory experiment in the way that we're thinking about them. Now, of course, in different kinds of experiments, there's different levels of evidence that come about, but in all of these, we're going to think of them as an experiment that requires statistical analysis. So another example of an experiment is a clinical trial, like the Women's Health Initiative that we just talked about and the ECMO trial. A recent and very important kind of experiment is a simulation computer experiment. So in addition to being very valuable tools for performing analysis, computers are increasingly becoming methods of actually generating the experiment. To give you a specific example of this, I work with colleagues across the street in the Division of Medical Imaging Physics, and when they're evaluating a new imaging technique, before they run very costly human or animal trials, they will actually design a computer experiment to evaluate image processing techniques, image analysis techniques, and so on. And they have highly accurate models of the imaging system that they've built. They added in randomness and other sources of variation, and then this produces a vast amount of data that they need a very sophisticated statistics to actually evaluate. And as a result, they can run quite detailed and quite accurate experiments entirely in silico, as they say, before they start running expensive human trials and animal trials. Another form of experiment is the so-called retrospective sampling experiment. So in many cases, it's very difficult to follow patients over time and ascertain disease status as it comes about, so-called prospective studying. Instead, it's frequently the only possible avenue available is to study things retrospectively. That is to, say, from hospital records or however, figure out who has a disease or a condition, compare them with controls who do not have the disease or condition but maybe have similar ages and demographics, and evaluate historically what their exposures were. This is so-called retrospective sampling, and it is frequently done because it's the only way to study a phenomenon, or the only convenient way to study a phenomenon when you're first looking at it. Each of these different kinds of experiments offer different sources of variation, different sources of experimental error, different kinds of randomness to be evaluated with statistical models. What we're going to talk about for the next several lectures is how we're going to connect these numbers resulting from all of these experiments and many others to probability models. And to do that, we're going to have to understand the subject of probability at a deeper level. And so that's what we're going to go over next, is the basic mathematics of probability. But while we're doing that, keep in mind that the eventual goal is to connect these probability models to the actual data. Okay, so before we begin discussing probability, we need some very basic mathematics. Now, everyone listening to this lecture will have had set notation at some point in their life and covered it from a very basic or even more advanced mathematical perspective. In probability, the set notation has the same rules, of course. It's just a subset of ordinary set notation. However, the interpretations of set notation are slightly different. So usually when you talk about set notation, you talk about some Uber space that contains everything. Well, in statistics, we call this the sample space, and that we usually denote with an uppercase omega. And this is the collection of all possible outcomes of an experiment. So as in a simple example, let's conduct an experiment. We roll a die. So the possible set of outcomes are 1, 2, 3, 4, 5, or 6, where here we're not going to play the sort of mental games that the die could land on an edge or a corner or something like that. It has to roll on one of the numbers. And then the sample space would be the integers from 1 to 6. An event is any subset of the sample space. So, for example, you could have the event that the die roll is even, i.e., that E is the set containing the numbers 2, 4, and 6. Certain kinds of events are so commonly talked about that we give them a separate name. An elementary or simple event is the particular result of an experiment. So, for example, if the die roll is a 4, then usually we denote this with a lowercase omega, omega equals 4. Here we don't tend to split hairs about the actual number 4 and the set containing the element 4. But I think in the traditional definition, a simple event is the actual element 4, not the set containing the element 4. But here, I don't think for our purposes that distinction will be necessary. And then it's always useful to talk about nothing. So the null event is actually the event that nothing occurs, the null event or empty set. And that's usually denoted with this letter here, which I'll just call null. Again, the sets in probability theory follow all the same rules as ordinary set notation, of course, because it is exactly ordinary set notation, but just with different interpretations. So when we say that an elementary event is an element of an event, then that implies that E occurs when W occurs. So, for example, just looking back at the previous slide, if our elementary event is that the die roll is a 4, and the event is that it is even. If you roll a 4, then the roll was even. If an elementary event is not in an event, that implies that E does not occur when W occurs. For example, if the elementary event is a 5, 5 not being in the set of even numbers means that when you roll a 5, you have not rolled an even number. We can follow along this logic. So, for example, E being a subset of F implies that the occurrence of E implies the occurrence of F. So, for example, let's take E as the event that the die roll is even, E equals 2, 4, 6, and F is the event that the die is either even or a 5. Hence, F is the event 2, 4, 6, and 5. So 2, 4, 5, 6. Then the occurrence of E implies the occurrence of F. That is, if you roll an even die roll, then you have also rolled an element of the set of even die rolls plus 5. Okay, if the standard set intersection E intersect F implies that both E and F occur. So to give you a specific example of this, imagine that E is the event that the die roll is even. F is the event that the die roll is a prime number. So let's think of what the prime numbers would be on a die roll. That would be 2, 3, and 5. So E intersect F means that the die roll is both even and prime. That would just be the number 2. So the event E intersect F occurs means that you get both a even number and a prime number, which of course in this case would mean that you get a 2. E union F is the standard set notation for union, but in probabilistic interpretation it means that at least one of E or F occur. So in my previous example it would mean that I either get an even number or a prime number, or both in the case of 2. If E intersect F is the null set, that means that both E and F cannot simultaneously occur. So imagine E is the set of even numbers, F is the set of odd numbers, then you cannot roll a die that is both even and odd. So E intersect F will be the null set, and that's important enough that we give it its own name. So in bold here you see its own name. That's called mutually exclusive. If we say that two events are mutually exclusive, that means that they both cannot occur, and you frequently hear people use the phrase mutually exclusive incorrectly. So what it technically means, things are mutually exclusive if they cannot both simultaneously occur. And then the complement of an event, E complement, or sometimes we might write E with a little bar on top of it, that is the event that E did not occur. So in our case where E is an even number, 2, 4, 6, E complement is the odd numbers. Okay? 1, 3, and 5. Since something and its opposite cannot simultaneously occur, their intersection is always the null set, so E and E complement are always mutually exclusive. There's some standard set theory facts that we should also just remind you of. There's the famous so-called De Morgan's laws. So A intersect B complement is A complement union B complement. And the way to think about this is this little complement symbol sort of distributes itself across the parentheses to A and B, A complement and B complement, and it flips the cap into a cup. And then what's nice is if you look at the second example of De Morgan's law, A union B complement is A complement intersect B, the same thing happens. This C distributes itself across the parentheses, so you get A complement and B complement. In this case, the cup turns into a cap. So De Morgan's law basically says if you complement across in either intersection or union, the complement distributes itself, but it flips everything. It flips all the cups and caps. Okay, so I struggled to come up with a verbal example of De Morgan's laws, and here's the best I could do. Let's let A be the event that you're an alligator, and B be the event that you're a turtle. So the event that A union B is the event that you are either a turtle or an alligator. And then complementing that, that means if an alligator or a turtle you are not, then De Morgan's law says that's A complement intersect B complement. A complement is you are not an alligator, intersect B complement is you are not a turtle. So the set theory association with the English would be if an alligator or a turtle you are not, then you are not an alligator and you are also not a turtle. Those are the equivalence between those two sentences. I think everyone would agree those two sentences agree. Another example, for the second De Morgan's law, if your car is not both hybrid and diesel, so A is the event that your car is hybrid, B is the event that your car is diesel, and you complement their intersection. So if your car is not both hybrid and diesel, then your car is either not hybrid or not diesel. So A complement, union B complement. Okay, some other small little facts that I'm sure you remember from set theory. A complement complement is A. So if you do not get an even number, you get an even number. And A union B, quantity intersection C, is A intersects C, union B intersects C. So the way to think about this, just to remember it, is think of the union as sort of plus and the intersection is sort of multiplication. And this little rule looks just exactly like the distributive property. So C sort of gets multiplied by A, C gets multiplied by B, and it sort of distributes across the plus sign, sort of the union. So that's the way you can sort of remember that one. So that gives you a very basic Rosetta Stone, taking ordinary set notation and connecting it to how we think about it in probability. Next, we're going to actually use the set notation to develop probability. So this is a very brief section, and in this discussion, we're just going to talk about probability at its very conceptual level, and in the next section, we'll talk about probability at its sort of mathematical foundation. But I wanted to spend a minute talking about where we're going with probability as a modeling tool to analyze data. And here's a strategy that underlies much of science. And the idea is this. For a given experiment, attribute everything that you know to a systematic model. So a good example of this are things like lines and planes and hyperplanes, where people presume that an outcome, say something like hypertension, depends on a lot of predictors in a linear fashion. And so that's either known or it's theorized or it's assumed for sake of convenience. But that relates known predictors to the known outcome. And then attribute everything else to randomness. Now, this is a very difficult bullet to swallow, I think, for many people, because in nearly all applications of probability, what the word random means is very difficult to tie down. As an example, earlier on in the lecture, we were talking about retrospectively sampling hospital records. And in this case, if you were to model the outcome of whether or not a person had a disease, as is predicted by their history, where we perform some form of retrospective sampling,
it's not exactly clear where the randomness is coming from, or even what randomness means in this context. So even if that's the case, we still often use probability to evaluate the collection of unknown things in an experiment, treating them as if they were random. And then we have to just be careful in how we interpret our probability statements in that context relative to what the word random is meaning in that case. In some other settings, people have very specific definitions of what random means. For example, sometimes people will analyze clinical trials using the randomization that was used to assign patients to treatment or control as the actual probability that they're modeling in their mathematical models. And there they can point very directly to what randomness they're modeling. However, that has its own problems as well. So I just want to say that this process of using probability, the third point, using probability to quantify the uncertainty in your conclusions to model this randomness is actually a very delicate subject. And as you can imagine from this discussion, all three of these first bullet points come with quite a bit of baggage in the terms of assumptions and things that you cannot evaluate at all. And so what we'd like to do is check how sensitive our conclusions are to the assumptions in these models. In some cases, we can actually directly verify them. We can check whether the relationship between the response and the predictors looks kind of like a line, so we're okay modeling it as a line. In other cases, they involve assumptions that we can't possibly check. They involve variables that we did not collect or variables that we do not even know. And in this case, we have to evaluate our sensitivity to our model in terms of unknowns. We have to evaluate how robust our approach is to the unknowns. And this comes from the study of how the data was collected, how the statistics were used, what exactly is probability actually modeling. In what follows, we're going to both cover the mathematics of probability, but hopefully touch on these subjects. Now, I want to emphasize that these are very, very difficult topics that many people struggle with if thought of with sufficient depth. And what we hope to do in this class is mostly get you started thinking about this. And I think if you just did one thing when thinking about probability and your data that you're analyzing, is when you say, I have a 95% confidence interval, or my p-value is blank, or something like this, where you actually use probability in your actual data analysis, go through the exercise of trying to think, what is it that you're modeling as random? What is the sources of this randomness? And how good of a job do you think your probability statements do at characterizing this randomness? This is the end of Mathematical Biostatistics Bootcamp Lecture 1. In this lecture, we covered basic conceptual ideas, and next lecture, we're going to be covering much of the basic mathematics that underlies probability. So make sure you have plenty of coffee to get ready. Hi, my name is Brian Caffo, and this is Lecture 2 of Mathematical Biostatistics Bootcamp. In the last lecture, we covered probability and the basics of biostatistics at a very conceptual level. In this lecture, we're going to get much more down to specifics. First, we're going to cover the subject of probability, which are mathematical functions. So we'll talk about the specifics of those kinds of mathematical functions. Then in 2, we'll talk about random variables. Random variables are just like any other variables that you've maybe encountered before, like in calculus, with the exception that they are random. They can take lots of different values. In section 3, we're going to talk about probability mass functions and probability density functions. These are mathematical functions that map probability to random variables. In section 4, we're going to talk about so-called cumulative distribution functions, CDFs, very associated things called survival functions, and quantiles. And then we'll wrap up with a brief summary. So a probability measure is the function that is going to govern the rules of probability for us. And there's basically 3 rules that a probability measure has to follow. And these three rules, and every probability textbook will give you these three rules are things that are equivalent. There's an interesting history behind these three rules. The Russian mathematician Kolmogorov, who's generally considered the father of all of modern probability, basically distilled everything that we thought of as in terms of things that a probability should have to follow. He minimized them down to the minimal set of rules that you could possibly have. If you delete any of these rules, you wind up with something that fails in some fundamental way to be probability. And if you add any other rules, they turn out to be excessive. So it's really kind of an interesting collection of research he did. It's also interesting to note that Kolmogorov tried to do something else, which is to figure out what exactly it is we mean by probability. So he found that problem to be very hard, and I think if you look into it, the theory of exactly what is randomness and exactly what is probability measure is a very deep problem, and philosophers are still debating this, and I question whether or not it will ever reach a resolution. However, one thing that's much less controversial is what rules probability has to follow, and Kolmogorov just nailed it. It's done. So let's go over these three rules. So a probability measure P, the letter P here in italics, is a function that maps events, which are subsets of the sample space, to numbers between 0 and 1. That's item 1 here. So events E have to be mapped to numbers between 0 and 1. So a probability is a function that operates on sets. The second item here says that the probability of the whole sample space has to be 1. Basically what this means is that something has to happen. The sample space has to enumerate everything possible that can happen. So for example, if you're flipping a coin, the coin can either be heads or tails. If the sample space is heads or tails, when you flip the coin, one of those two things has to happen. The probability of one of them happening is 1. The coin can't land on its side. If you want to allow for the coin to land on its side, then it has to be heads, tails, and land on its side as the sample space. The third statement, and we'll talk a lot about the third statement because we're giving you an incorrect version of it. The third statement says that if two events are mutually exclusive, and recall events are mutually exclusive if they have no intersection, if two events E1 and E2 are mutually exclusive, then the probability of the union is the sum of their probabilities. So as an example, we just talked about coin flipping, and we said the probability of a head or a tail has to be 1. The probability of either getting a head or a tail has to be 1. So let's talk about that in the context of Rule 3. If E1 is the event that you get a head and E2 is the event that you get a tail, then the probability of E1 union E2, the probability that you get a head or tail, winds up being the probability of getting a head, let's say it's 0.5, plus the probability of getting a tail, which is 0.5, which adds up to 1, exactly what we know it has to. So in part 3, the third rule that we talked about in the previous slide, I said that there was some concern over it not being complete. So I'm going to elaborate on what I mean by that in this slide. First of all, let's note the following fact. Part 3 of the previous slide, the fact that if you have two mutually exclusive events, the probability of their union is the sum of their probabilities. That pretty easily extends to the so-called finite additivity, that instead of having 2, if you had 3 or 4 or 5, or let's just say n events, that the probability of their union equals the sum of their probabilities. So in this case, I have the probability of the union of a collection of mutually exclusive events, AI, equals the sum of their probabilities. That pretty directly follows from the previous definition. Just to give you a sense of how it works, if you had 3 events, say A1, A2, and A3, and they're all mutually exclusive, then the probability of A1 union A2 and A3 is the sum of the probability of A1 plus the probability of A2 union A3, right? Because A1 is mutually exclusive from the union of A2 and A3. And then that second probability, the probability of A2 union A3, is then again the probability of the union of two mutually exclusive events. So it is the probability of A2 plus the probability of A3. And you can formalize this with mathematical induction if you want. So at any rate, the rule that I gave you implies so-called finite additivity, and it seems like maybe that should be enough to cover everything. Well, the probabilists have thought very hard, and they said, well, maybe we think it should be countable additivity. Instead of n, it should go up to infinity. And it's not the case that the definition that we gave implies countable additivity, that if you had an infinite collection of mutually exclusive events, that the probability of the union is the sum of the probabilities, which requires ideas of limits and other things that we're not going to cover so much in this class. So at any rate, it's the case that finite additivity does not imply countable additivity, but of course countable additivity implies finite additivity. So in standard probability classes, in the more theoretical probability classes, they make quite a bit of hay out of this distinction. They discuss it a lot, and the general definition gives countable additivity rather than finite additivity. If you take a more advanced measure theoretic probability class, they will deal with this issue at length. In this class, this will be the last time we discuss this. In general, finite additivity will work just fine for us. In the next slide, we're going to talk about more details about what the probability function operates on. And again, it's going to be a rather important but maybe unnecessary detail for this class. So we're going to, again, it's going to be another thing that we cover very briefly and then tend not to think about for the remainder of the lectures. Recall that our probability function operates on events which are subsets of the sample space and maps them to numbers between 0 and 1. So we need an appropriate domain of our function. Our domain is not an event, it's a collection of events. So let me go through an example to make this idea a little bit more clear. So let's suppose the sample space is simply the numbers 1, 2, or 3. Imagine somehow if you had a three-sided die that you were rolling. Then the probability function operates on all possible events that are subsets of that sample space. So in this case, the null event, the event that you get a 1, a 2, a 3, a 1 or 2, a 1 or 3, a 2 or 3, or the whole sample space, a 1, 2, or 3. And this is fine. Pretty much whenever you have a finite set, the domain of the probability function will operate on all possible subsets of the sample space. In this case, we're using the letter script F to denote this so-called domain. When the sample space is a continuous set, it actually gets a lot harder. And you can no longer say things like the probability operates on the set of all possible subsets of a continuous set. And it turns out that that is an incredibly deep mathematical problem. The mathematician Cantor thought about measure and sets in a very deep way, and if you want to read about an interesting character in the history of mathematics, you should read about Cantor. He came up with interesting sets that, for example, you just can't reasonably include in the definition of a probability. So in this class, we're not going to think about this at all, but I wanted to raise it just for those students that go on to take some of these more advanced classes so that you'll be prepared for some of these admittedly kind of strange ideas that come up when you try to talk about this set of sets that probabilities operate on. For our purposes, when our sample space is a continuous set, we're mostly going to be concerned with things like intervals or unions of intervals. And in that case, the definitions are very easy. So our definition of the domain that the probability operates on, we're just going to assume that anything that we can think of, and since none of us are Cantor, probably we won't think of anything too crazy. Anything that we can think of is just fine, and that definition will work really well for this class. In this slide, we're going to give a laundry list of properties that a probability function has to have by virtue of its three definitions. So you should find it kind of interesting that the three definitions then imply all of these things that we know probabilities have to have. So take this first bullet here. The probability of the null set is 0. Basically, the probability that nothing happens is 0. So if you say you're going to roll a die, you actually roll a die. If you say you're going to flip a coin, you actually flip a coin. That's basically what the probability of the null set being 0 is. The second bullet says the probability of an event is 1 minus the probability of its complement. In other words, for example, if E is the probability that you get a head when you flip a coin, the probability of getting a head is 1 minus the probability of getting a tail. And that's, of course, true on a fair coin, where the probability of a head is 0.5 and the probability of a tail is 0.5. But let's suppose you have an unfair coin. Maybe you glued together a nickel and a US dime and made a funny shaped coin that you didn't know whether or not the probability of a head was 0.5. Let's suppose the probability of a head in that case was 0.3. Well, this would say if the probability of a head is 0.3, then the probability of a tail has to be 0.7. The next bullet says that the probability of the union of two events is the probability of their sum, and that's all we would have to say if the events are mutually exclusive, but we have to subtract off the intersection if they are not mutually exclusive. And the intuition behind this statement is something like this. When you add the probability of A, you've added the probability of A, which includes the part of A that intersects B and the part of A that does not intersect B. And then you've added the probability of B, which includes the part of B that intersects A and the part of B that does not intersect A. So you have then just added the part of A that intersects B and the part of B that intersects A. In other words, A intersect B, you've added it twice. Once when you added probability of A, once when you added probability of B. You've added it twice, you only wanted to add it once, so subtract it out. That's how the rule works. The next bullet point is a pretty simple point. If A is a subset of B, then probability of A is less than or equal to the probability of B. So this is analogous to saying if I'm rolling a die and A is, say, the event that I get a 1 and B is the event that I get a 1 or a 2, then the probability of getting a 1 is less than the probability of getting a 1 or a 2. And so this rule, I think, makes a lot of sense. From De Morgan's laws, we get probability of A union B is 1 minus the probability of A complement intersect B complement. The next bullet point is kind of along the lines of subtraction. So A intersect B complement, that set is sort of like subtracting B out of A, the component of A that has nothing to do with B. So the probability of A removing B is the probability of A minus the probability of A intersect B. So that works out to be a nice rule. That sort of set level subtraction works out to be equivalent to subtracting the probabilities. The next bullet talks about the probability of the union of events again. This says the probability of the union of a collection of events is less than or equal to the sum of the probability of the events. Now again, if the events are mutually exclusive, then the probability of the union has to equal the sum of the probabilities. So this rule doesn't violate that rule whatsoever, but it also accounts for the times when the events are not mutually exclusive. The final rule talks again about unions of events. In this case, the probability that the union of events is bigger than the probability of the maximum of the collection of probabilities. Again, this rule holds if the events are mutually exclusive or not. But there's intuition behind this that's very easy. The union is everything that's in any of the events, E1 to En, so it contains anything. The probability of that has to be bigger than any of its component events. I think that makes quite a bit of sense. So just let me give you an example. Go back to our die roll. If E1 is the event that you get a 1, E2 is the event that you get a 2, E3 is the event that you get a 3, the probability on the left-hand side of the equation is the probability that you get a 1, 2, or 3. On the right-hand side, it says that it's the maximum probability. If you're talking about a standard die, probability of a 1 is 1/6, probability of 2 is 1/6, probability of 3 is 1/6, so the maximum of them is 1/6. On the left-hand side, the probability of the union is the probability of a 1, 2, or 3, which is 1/2. So 1/2 is definitely bigger than 1/6. So let me give you an example of one of these proofs. So let's take a simple one. The probability of an event is 1 minus the probability of its complement. So consider line 1. Recall that the probability of the whole sample space is 1. But again, the sample space for any event is equal to the union of that event and its complement. So omega equals E union E complement. Then consider the next line. An event is always mutually exclusive with its complement. Something cannot simultaneously occur and not occur. So events are always mutually exclusive with their complement. So E and E complement are mutually exclusive events. So we can take the probability of the union and turn it into the sum of the probabilities. Probability of E plus the probability of E complement, and then that's simply a restatement of what we want to prove. 1 equals probability of E plus the probability of E complement. Let's do a more complex example of the consequences of the probability rules. So recall that we discussed that the probability of the union of a collection of events is less than or equal to the sum of the probabilities. And recall that less than or equal to is an equality if the events are mutually exclusive. So let's prove this using mathematical induction. The way mathematical induction works is you prove it for some small statement, 1 or 2, then you assume that it's true for, say, n minus 1, and then prove that it's true for n. That's how mathematical induction works. So let's consider just 2 events. Probability of E1 union E2. Well, that's by one of the other consequences of the probability rules that we investigated. That's equal to probability of E1 plus the probability of E2 minus the probability of E1 intersect E2. And here I'm assuming that we've gone ahead and proved that one as well. So this final term here that's subtracted off, minus probability E1, E2, we are subtracting off a number that has to be positive. Remember, probabilities have to be between 0 and 1, so they have to be non-negative at least. So if we throw away that final term, what's left can only get bigger, right? So if we're subtracting off a positive number and we throw it away, then it's got to get bigger. So then we've established the result for the case when we have 2 events. Now let's assume the result is true when we have n minus 1 events, and let's consider n events. So we want to demonstrate that the probability of the union of the EI is less than or equal to the sum of the probabilities. So let's write out the probability of the union of the EIs as En union with the union of the rest of them. So the union of the rest of them, I equal 1 to n minus 1, is a single set. We've already done that. That's just 2 sets, En, and the union of the remainder are 2 separate sets. We already worked it out for 2 sets. So we can say that the probability of the union E1 to En is less than or equal to the probability of En plus the probability of the remainder. Now consider the next line. In the next line, we have the probability of En from the previous line, and then we can say that we have only gotten bigger by our induction hypothesis, by the fact that we assume that this statement is true for n minus 1 events. So there, if we switch this probability from the probability of the union to the sum of the probabilities, we've only made it bigger, so we can maintain that inequality. Then just collecting the terms, then we just have that this is the sum of the probabilities. And just to give you a sense of the notation I use, when I write equals on this last line, I mean it equals the previous line, not that it's equal to the first line. So I'm assuming that it's less than or equal to, less than or equal to, and equal to, implying that the final statement is less than or equal to the first statement, but equal to the previous line. So that's notation that I commonly use. So you should be able to prove all of these probability statements that we outlined on the previous slide. This particular one, let's go ahead and take a step back from the mathematics and try and put some of this within a context. So the National Sleep Foundation reports that around 3% of the American population has sleep apnea. This is a sleep disease where the upper airways collapses. They also report that around 10% of the North American and European population has restless leg syndrome. For the purpose of our discussion, let's just assume that this is 10% of the American population has restless leg syndrome. Similarly, they report that 58% of adults in the U.S. experience insomnia. So imagine if you were a sleep physician and you wanted to know the probability that a random American has any of these 3 sleep disorders. Can you simply add these 3 probabilities, 3%, 10%, and 58%, and get 71% of people have at least one of these sleep problems? So this question is nothing other than a restatement of the probability relationship that we just proved. So here I'm using A instead of E, but maybe that's a good thing to do just so you get used to not using the same letter for everything. So let's let A1 be that the person has sleep apnea, A2 be the event that the person has restless leg syndrome, and A3 be the event that a person has insomnia. And I'm going to gloss over the details, but the probability that a person has at least one of these diseases is, we're talking about the union, A1 union, A2 union, A3. So we want to know the probability of the union. Well, that's only equal to the sum of the probabilities, right, when A1, A2, and A3 are mutually exclusive. Otherwise, it's the probability of A1 plus the probability of A2 plus the probability of A3, and we have to subtract out other things. And in this case, I give you the exact equation for relating the probability of the union of three events to the probability of A1, A2, and A3. And so it works out to be 0.71, but then there's all this other stuff. The A1 intersect A2, A1 intersect A3, A2 intersect A3, and then you have to add in the triple intersection, A1 intersect A2, intersect A3. And I would suggest you go through and figure out why exactly it is this formula works out. But the point is that other stuff is non-trivial, and it's always there unless A1, A2, and A3 are mutually exclusive. And so you can't simply add these other things. And in fact, in this case, from a scientific perspective, I mean, we're talking about it from a mathematical perspective, but from a scientific perspective, it's probably the case that there's a non-trivial intersection of people with sleep apnea and restless leg syndrome, and a non-trivial intersection of people with restless leg syndrome and insomnia, and so on, so that probably this 0.71 is not close at all. So that ends our whirlwind tour of the basics of probability mathematics. Next, we're going to talk about random variables. So welcome back, recruits, to Lecture 2 of Mathematical Biostatistics Boot Camp, and now we're going to talk about random variables. So random variables, as the slide says, is simply a numerical outcome of an experiment. Random variables are just variables, like you see in calculus, but they have probability distributions associated with them. We're only going to talk about two kinds of random variables, discrete or continuous random variables. Discrete random variables are any random variables that can take just a countable number of possibilities. So even if it's infinite, if you can enumerate the collection of values that a random variable can take, it's going to be discrete. So what I mean by even if it's infinite, if you have a random variable that is the number of people that show up at a bus stop, well, I suppose there is a theoretical limit to that, but it might be useful mathematically to model that as if that count can go all the way up to infinity. But the point is that we can count them. We can count one person, two people, three people, four people, and so on. If the random variable can take any possible value on the real line or a subset of the real line, then we'll call the random variable continuous. And we'll have to have a slightly different treatment of continuous versus discrete random variables, but I think when we go through it, we'll try to draw the similarities between how they're treated. This list of random variables either being discrete or continuous is non-exhaustive. You can actually have a random variable that is both discrete and continuous. To give you an example, let's think of a good way to generate a continuous random variable, or something at least that could conceptually be viewed as a continuous random variable. Suppose you were to draw a line on a piece of paper that goes from 0 to 2. You label one end of the line 0 and another end of the line 2, and then you drop your pencil and it hits a random point in between 0 and 2. And you were to measure the distance between 0 to 2, how far that point is. Well, maybe you can argue you can only measure to so fine of a scale, but let's forget about issues like that. Honestly, you would model this as sort of a continuous random variable. That distance you can measure to several decimal places, and so we'll think of it as sort of a continuous one. So let's think about how could you possibly generate a random variable that's both discrete and continuous. Well, let's suppose, so we have our little experiment where we can generate something that's continuous or continuous enough for us to think of it as continuous. And then we have another example, say just rolling a die that generates 1, 2, 3, 4, 5, 6, clearly generates a discrete random variable. Suppose then you were to flip a coin, and if the coin comes up heads, you use your pencil to get this continuous random variable. And if the coin comes up tails, you use this die to get your discrete random variable. Well, the resulting random variable could have possibly have been continuous, or it could have been discrete. So that random variable, if we were to describe its behavior, we would have to describe it as potentially being both discrete and continuous. So we won't deal too much with random variables like that. I would add that they're not entirely useless. So let me give you an example of a random variable that's kind of both discrete and continuous, but is used in practice. So imagine if you're looking at expenditures of some sort. Let's say you were an insurance company and you were looking at how much you had to pay out in terms of insurance. Well, for some people that never got sick, you paid out zero. It's a discrete number, exactly zero. For everyone else, you may be paid out a certain amount, and that remainder would probably be best modeled by a continuous random variable because you have to account for it down to the fraction of a penny or something like that. So in that case, if you're the insurance company and you're evaluating the distributional behavior of expenditures, you might want to model that with a random variable that can both take the discrete value 0 and can take the continuous values for all expenditures beyond 0. So at any rate, this is a long-winded discussion of random variables that we're not going to consider in this class, ones that are both discrete and continuous, but I just wanted to raise the point that the kinds of random variables that we're going to describe are non-exhaustive. Let's go through some simple examples of variables that can be thought of random variables. So if you flip a coin, the head or tail 0 or 1 outcome of a coin flip is clearly a random variable. If you roll a die, the 1, 2, 3, 4, 5, 6 outcome from rolling a die could be modeled as a random variable. And again, I should say could be modeled as a random variable. If you say it is a random variable, then you get into this discussion of, well, is a coin flip really random? Maybe if you knew exactly how much pressure the person applied to the coin and all. We're not going to worry about that kind of extremely conceptual thinking in this class. We're going to say practically we'd like to model a coin as random. Practically we'd like to model a die as if it were random. But practically we'd like to model lots of other things as if they were random too. So for example, if we have a random selection of subjects and we take their body mass index at baseline and then take it 4 years later, we might want to model that change in BMI or the BMI after an amount of time as being a random variable. Same thing with hypertension. We might want to model their hypertension status, whether they have hypertension or not, as a random variable. And this latter point also reminds us of why coin flipping is very important. Coin flipping seems like a trivial random variable, but it forms the basis for a lot of analysis. We think of a lot of things as if they were coin flips. So we might model, for example, the prevalence of hypertension. We might think of the data going into that modeling as if they were a bunch of coin flips. And the idea of a coin flip will help conceptualize the model that we're formulating. So we've described some examples, some very basic examples of random variables. So what we need is a mathematics of random variables to use them. And we have a mathematics of probability. And we've acknowledged we're at least willing to think of kinds of variables as if they're random. We'd like to put those two ideas together. So we need functions that map the rules of probability to random variables. And so for discrete random variables, the kind of functions that we're talking about are so-called probability mass functions. So a probability mass function is simply a function that takes the values that a random variable can take and maps it to their associated probabilities. So for a die, a probability of P of 1 would be 1/6, for example. And it turns out quite a few functions satisfy the definition of being a probability mass function. In fact, you only have to satisfy 2 rules if you'd like to be a probability mass function. The first rule is that you have to be bigger than 0 for all of the arguments, where here x is the collection of possible values that a random variable can take. And the second rule is that if you sum over all possible values, then you get 1. This is just exactly analogous to our probability statement that the probability of the whole sample space has to be 1. But here we've put it in the terms of a probability mass function. I want to talk a little bit about this notation. Notice here I have this small x, and when we defined random variables 2 pages previously, we used a capital X. So this is very common and maybe slightly unfortunate notation, but it's used everywhere, so you might as well just get used to it instead of fighting it, that we use an uppercase letter typically to represent the random variable as a conceptual entity. So if we say capital X, we're talking about a die roll that we could have. When we use a lowercase x or a lowercase y or a lowercase letter of any sort, we tend to be talking about realized values of the random variable. So the x lowercase should be something that you should be able to plug a number into, where capital X is a conceptual random variable. It's a conceptual flip of a coin. It's a conceptual roll of a die. Lowercase x is 1 or 2 or 3 or 0. Okay, and it's slightly unfortunate notation. It takes a little bit of getting used to, but I think for everyone who works in statistics or probability, they've gotten used to it, and everyone does it, so you might as well do it too. Let's go over an example of constructing a probability mass function. Let's take the simplest possible example, a coin flip. So let's let x be the result of a coin flip where 0 represents tails and 1 would represent a head. So we want the function, and let's assume that the coin is fair. So we want a function that maps 0 to 1/2 and 1 to 1/2. And there's infinitely many ways you could write down that function. Well, we're going to pick one. Here we write it as 1/2 raised to the power x times 1/2 raised to the power 1 minus x. And notice that if you plug in x equals 0, you get 1/2. And if you plug in x equals 1, you also get 1/2. Now let's go to a slightly more complicated example where we assume that the coin is potentially biased, i.e. that it's not fair. So let's let theta be the probability of a head, in this case expressed as a proportion between 0 and 1. So just as an example, imagine if theta was 0.3 instead of 1/2, then we would think that the probability of a head is 0.3 and the probability of a tail is 0.7. But let's leave it as theta for right now. So we want a function that says probability of a 0 is 1 minus theta and the probability of a 1 is theta. And then we see our function here, theta to the x, 1 minus theta to the 1 minus x, exactly satisfies these properties. This is another common notation in the field of statistics that Greek letters, like theta, represent things that we don't know that we would like to know. So imagine if you had a coin and you didn't know whether or not it was fair, we would represent that unknown probability of a head as theta. So I want to give you a sense of where we're going. In this case, the probability mass function is the entity that governs the population of coin flips. And so if we wanted to know theta, we're going to collect data to estimate it and then to evaluate the uncertainty in that estimate. And the way we're going to evaluate uncertainty in that estimate is using this probability distribution. So all the probability distributions we're going to talk about are conceptual models of populations, and they are the entities that are going to tie our data to the population. So at any rate, right now this may sound a little heady, and we'll discuss this in much more detail throughout the entire class, but the one rule I want you to remember right now is that unknown things that we want to know, like in this case what would be the probability of a head, are generally denoted in Greek letters. These are called parameters usually. I also want to note one other thing. Why is it among all the possible ways that we could have written out this probability mass function did we choose theta to the x, 1 minus theta to the 1 minus x? There's lots of different ways we could have done this. You can try and figure some of them out yourself. Well, it turns out, and we'll discuss this at length, that in probability, multiplying is very useful. And so we want probability mass functions that make multiplication very easy. So if we take things and raise them to powers, then multiplying becomes easy. And that's a general rule. And you'll see later on why this is the case. But at any rate, this is why we choose this particular form of the probability mass function when you could write it so many different ways. But I want to say people have thought about this a lot, and this is definitely the most useful way to write out this particular probability mass function. So consider again the unfair coin. Our probability mass function satisfies p of 0 equals 1 minus theta and p of 1 equals theta. Let's just go through the exercise to prove to ourselves that this is in fact a probability mass function. It's greater than 0 because it's 1 minus theta for 0 and theta for 1, and in this case theta is between 0 and 1, so it's going to be greater than 0 for x equals 0 and 1. And then the sum of the probabilities, probability of 0 plus the probability of 1, in this case is theta plus 1 minus theta, which is 1. So it satisfies the two rules that probability mass functions have to satisfy. So that covers our principal entity that we're going to use to model discrete random variables, probability mass functions. So now we need to cover our principal entity that we're going to use to model continuous random variables, which are called probability density functions. So probability density functions are abbreviated PDF, by the way. So it stands for probability density function, not portable document format, which is what lots of people think of as PDFs. But in statistics, no one thinks of PDFs that way. I want you to remember one very important rule, and I put it in italics just to make sure everyone remembers it. And by the end of the course, this will be second nature to you, but if you haven't seen it before, it might seem a little odd. But the way that probability density functions work are that areas under probability density functions correspond to probabilities for the random variable. And there's definitely one undisputed king of all PDFs, and that is the so-called bell curve. So if you ever wondered what a bell curve was, if you hear it talked about a lot, the so-called normal density function, you might wonder what in the world is a bell curve accomplishing? Well, areas under bell curves correspond to probabilities. So if you're modeling something as if the population it belongs to follows a bell curve, then you are saying that probabilities associated with that random variable are governed by areas under that bell curve. So that's just one example of a PDF. There's lots of different kinds of PDFs. So just like probability mass functions have to follow two rules, probability density functions have to follow two rules to be a valid probability density function. They have to be positive for all the possible values that the random variable can take. That's called the support usually. And their integral has to be 1. I would also say a small point here. We define probability density functions as if they operate on the whole real line. So even if your random variable can only take values, say, between 0 and 2, like we talked about earlier with the pencil experiment, even if that's the case, we define the probability density function as 0 below 0 and 0 above 2 so that there's no associated probability, but we've defined the probability on the whole real line so that we define its integral from minus infinity to plus infinity. And I think in this class we tend to be a little bit fuzzy about sometimes operate on minus infinity to plus infinity, and other times we'll just write out 0 to 2, discarding all the area where the function is 0, and I hope from the context it'll be clear what we're doing. This final property, property 2 here, that the integral over the whole real line of the probability density function has to be 1, is simply again saying that the random variable has to take some value, that it has to be in some interval in the whole real line. Let's go through a specific example of a PDF, and let's put it in a context. So let's assume that the time in years from diagnosis until death with a specific kind of cancer follows the density that looks like this. F of x equals e to the negative x over 5 divided by 5 for x greater than 0. The greater than 0 being contextually clear because you can't have negative time from diagnosis, and the person is presumably alive at the time of diagnosis. So this is a very restricted example of a density that's commonly used in these sorts of analyses of things like survival times. It's called the exponential density function. And again, here you see that we have f of x written as e to the negative x over 5 for x bigger than 0, and 0 otherwise. Like I talked about in the previous slide, we often just ditch that 0 and just talk about f of x being the kernel of the function and just either explicitly write, or sometimes we'll fudge a little bit that x has to be greater than 0 if it's clear from the context that that has to be the case. In this case, it would be clear from the context. Is this a valid density? Could we model survival time after diagnosis with this density? Well, first of all, we know that the function is positive because e raised to any power is always positive. And then let's just check whether or not it integrates to 1. So we want the integral from minus infinity to plus infinity, but like we said, all of the meat of the distribution starts at 0 and goes to infinity. So let's just say the integral from 0 to infinity, f of x dx, is, in this case, the antiderivative is negative e to the negative x over 5, which when evaluated from 0 to infinity yields 1. Let's go through an example of using this probability density function to assign probabilities. So imagine if we were to model this population as if it followed this specific exponential probability distribution, And imagine if someone asked us the question, what's the probability that a randomly selected person from this population survived more than 6 years? So if X is the conceptual value that a random person takes, we want to know what's the probability that X is greater than or equal to 6, as represented by this probability statement. Remember again the golden rule for probability density functions that areas under the curve correspond to probabilities. So if we want the probability X is greater than 6, we want the integral from 6 to infinity of the probability density function. And you can go through the calculus here to get that that works out to be about 30%. In the statistical programming language R, you can do this automatically. It just does the integral for you. It uses a numerical approximation, and you just write px6 for the fact that we want the probability of 6 or larger. 1/5 represents this parameter 5 that you see in the exponential distribution. Lower.tail equals false means that we want the probability of being larger than 6 rather than the probability of being smaller than 6. So lower.tail equals true would give you 6 or smaller. Lower.tail equals false will give you 6 or larger. I want to elaborate on that point, by the way. For a continuous random variable, the probability that it takes any specific value is in fact 0. Now that seems strange, but it's true. So remember, areas under probability density functions correspond to probabilities. So what's the area of a line? It's 0. Now you might say, well, that doesn't make any sense at all. Specific values have to take probabilities because we see specific values when we actually observe variables. The point is that our probability density function is a model, and it is defined on continuous random variables. Continuous means measured to infinite precision. And so when we observe things, we never measure them to infinite precision. We measure them to finite precision. And probability density functions are perfectly happy with saying the probability that X is 6.01 to 5.99 and assigning a perfectly valid probability to that. But the probability that it's exactly 6 is 0. Because remember, exactly 6 means 6.0 followed by an infinite trail of zeros, or 5.99 followed by an infinite trail of nines. Either way, that's the idea behind what probability density functions are getting at. They're modeling truly continuous random variables. So just remember that when we observe data, we of course measure them with finite precision, but our continuous model is exactly that. It's a model. We find it far more useful in many circumstances to model random variables as if they were truly continuous than to account for all the potential specific values they could take. So in this specific example, a person will only measure how long they survive to the year, maybe to the month, maybe to the day, maybe to the hour, to the minute, to the second, but probably not much further than that. And so we're only going to measure to finite precision. Nonetheless, it still is much more useful to model that as if it was continuous because we don't want to have to assign probabilities to every single value. We want to assign a general function. And that's why continuous random variables are so intrinsically useful. So the belabored point I'm trying to make about this, by the way, is that whether or not you write probability X being greater than or equal to 6 or the probability of X being strictly greater than 6, in this case, doesn't change this calculation whatsoever. You get 0.301 either way. And so it also doesn't make a difference in the probability exponential for the R example. It doesn't matter whether you specify lower tail or upper tail, whether you're thinking about whether or not that includes 6, it doesn't care about that. However, for discrete random variables, it makes a big difference, right? Because specific values have actual probabilities assigned to it. So a die can take the value 1, 2, 3, 4, 5, or 6. So in R, if you're using these probability functions, so px are probabilities from the exponential distribution, p binom are probability from the binomial distribution, p Poisson or POIS for Poisson is probabilities from the Poisson distribution, p gamma probabilities from the gamma distribution. R follows that rule pretty neatly. If it's a discrete random variable, you have to be careful about whether or not it's including the 6. For a continuous random variable, you can be very sloppy about it. So here I'm just depicting the area that we're calculating. This gray area is the survival time from 6 to infinity. This is simply the integral that we're actually calculating. And I'll put the R code to generate exactly this figure in the files for the course. So in that specific example, we looked at what's the probability that the random variable was larger than 6. But we might want to look at what's the probability the random variable is larger than 7, or smaller than 6, or smaller than 5, or smaller than 4.3, or so on. So if you take a random variable, you could construct a function that when you plug in a value, returns the probability that the random variable is less than that value. And you could construct a function that when you plug in a value, returns the probability that the random variable is larger than that value. And these things are so inherently useful that we give them names. So the cumulative distribution function, CDF, is simply a function that takes any specific value and returns the probability that the random variable is less than that value. And again, if it's continuous, it doesn't matter whether it's less than or equal to or less than, but the cumulative distribution function is defined for both continuous and discrete random variables, so let's be specific and say that it's less than or equal to. The survival function is the opposite, namely that it is exactly the probability that a random variable is larger than any specific value. So if you plug in x into the survival function, it returns the probability that the random variable is larger than x. So if on our previous slide, this figure, imagine if on the horizontal axis, instead of looking at 6, I was looking at some arbitrary value x, the gray area would be s of x, and the white area to the left of x and to the vertical axis would be f of x. Notice in this case that f is the probability of being less than or equal to x, s is the probability of being strictly greater than x, so that s of x and f of x have to add up to 1 because they're probabilities of complementary events. Probability x is less than or equal to x, and the probability x is strictly greater than x. So if you've calculated the cumulative distribution function, you have also calculated the survival function because all you have to do is 1 minus it. Conversely, if you've calculated the survival function, then you've calculated the cumulative distribution function. Next, we'll just go through our previous example and calculate exactly the survival function and the CDF. Let's actually go through an example of calculating the survival function and cumulative distribution function just from the exponential density that we considered before. Let's calculate the survival function first. So recall the survival function is the probability that the random variable is strictly greater than the value lowercase x. So further recall that to calculate probabilities, we need to calculate areas under the probability density function. In this case, we want the probability of being x or larger, so let's take the integral from x to infinity of our probability density function. Here I use the dummy variable of t for integration. The integral, or the antiderivative of e to the minus t over 5 divided by 5 is just negative e to the negative t over 5. We want to evaluate that from x, which yields the value e to the minus x over 5, and then subtract off the value as it limits to infinity, which is 0, so we just wind up with e to the minus x over 5. Now we could also go through the example of calculating the cumulative distribution function, which would, instead of calculating the integral from x to infinity, we would just be calculating the integral from 0 up to x. But because we've already calculated the survival function, we know that it's 1 minus the survival function, so it's 1 minus e to the minus x over 5. So the cumulative distribution function is the integral from minus infinity to x of the probability density function. Again, here we're just doing 0 because the integral from minus infinity to 0 is 0. And so we can just apply the fundamental theorem of calculus and note that the derivative of the CDF is exactly the density again. So if we take, just to go through our specific example, 1 minus e to the negative x over 5 and take the derivative of that, we get exactly e to the negative x over 5 divided by 5. So we get the PDF back. So derivatives of the cumulative distribution function exactly yield the probability density function back. Quantiles are properties of distributions or density functions equivalently. When I talk about a distribution or density in general, I'll just maybe say the word distribution. So if I want to talk about the bell curve or the associated distribution, I'll just talk about the Gaussian distribution or the normal distribution and so on. And then when we're talking about the mathematics, I'll be more specific. The alphath quantile of a distribution is the point so that the probability of being less than that point is exactly alpha. So we want, if x of alpha is the alphath quantile of the distribution, we want the probability of being less than or equal to x sub alpha to be exactly alpha. So let's just take as a specific example, if alpha was 0.25, x sub 0.25 is that point such that the probability of being less than it is 25%. So for example, in our cancer survival example, the 0.25th quantile of that distribution is the time of survival so that 25% of the people survive less than that time. The percentile is merely the quantile expressed as a percent. So the 25th percentile is the 0.25th quantile. And then the median, the population median, is exactly the 50th percentile. Let's just go through these concepts again with our density that we've been looking at, this exponential density. Suppose we wanted to find the 25th percentile of the exponential survival distribution. What we want is to find the point x on the horizontal axis so that the white area to the left of it is 0.25. So let's actually go through this calculation. In order to find the point so that the area to the left of it is 0.25, we just want to solve the equation 0.25 equals f of x. Well, recall in this problem a couple of slides ago, we solved that f of x is 1 minus e to the negative x over 5. And if you just simply solve that for x, we wind up with the solution x equals minus log 0.75 times 5, which is about 1.44. How is that 1.44 interpreted? About 25% of the subjects from this population lived less than 1.44 years. You can get quantiles directly from R by the Q function, Qx in this case, because we're talking about the exponential PDF. So Qx gives you quantiles from the exponential PDF. Px gives you survival or CDF probabilities from the exponential. And dx gives you the density itself, and that rule R follows for most of the common distributions. The median, to remind you, is the 0.5th quantile, the 50th percentile. And the quantile that we just figured out, the 0.25th quantile, is generally called the lower quartile. And you might have said, well, I've heard of the median before. Maybe I've heard of what a lower quartile is before. And what those things are, to me, is that they're the middle of the data, or the point in the data so that 50% of the observations are lower than it. Or the lower quartile is that point in the data so that 25% of the observations are below it. What in the world is Brian talking about at this point? So when we talk about the median that we're discussing in this lecture, we're talking about the population median. And when you collect data and you take a sample median, that's an estimator of something, so we should talk about what that's an estimator of, right? It's an estimator, it has to have an estimand. In the same way, if we take a sample mean of data, that's an estimator of something, it has to have an estimand. And so what we're talking about in this lecture is one way to construct estimands of these quantities. In this case, the median, if you take the sample median, it is hopefully trying to estimate the population median, that point in the population so that the probability of being less than it is 50%. And you'll find in this class that there's this simple rule. Sample things tend to estimate population things. So sample medians estimate population medians, sample variances estimate population variances, sample means estimate population means, and so on. And what we're going to see is this probability modeling and the associated assumptions. These are the things that connect our data to the population so that we can actually have estimands. If we didn't go through this exercise, we would be able to take a median, but that would just be an entity in the sample. The whole point of probability modeling is then it connects your sample to this population so that your sample median now has a population median that it's trying to estimate. Now, and this is kind of a very difficult concept. I think the sample median is a very easy concept. It's saying, you have a list of observations, take the middle one after you order them. The population median is a much more difficult concept. It's saying, I have described a population via this distribution, and this distribution has a point so that 50% of observations lie below it, and that's the population median. And I think it's a good idea whenever you're talking in this class to put the word population or sample in front of it to remind yourself. Now, people who work in statistics do this so much that they just kind of forget about these distinctions, even though they know them. They just forget about them because they become sort of second nature. But when you're first learning this, it seems quite odd. And I also want to mention, the sample median is the well-defined quantity that doesn't require tons of assumptions. It's the probability modeling that's the delicate part that requires assumptions. So if you're going to say that the sample median estimates the population medians, where there's assumptions that need to be taken into account for that to be true. And especially if you want to do inference with your sample median or evaluate its uncertainty. And that's basically what we're going to spend nearly all of this class discussing, is how are we going to connect these probability and population concepts to sample data. Thanks, recruits. This was Mathematical Biostatistics Bootcamp Lecture 2. In the next lecture, we're going to expand on probability modeling and defining characteristics of probabilities. And I look forward to seeing you. Hi, my name is Brian Caffo. I'm in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health, and this is Mathematical Biostatistics Bootcamp, Lecture 3 on Expectations. Expected values are ways of summarizing probability distributions in the same way last lecture we talked about quantiles to summarize probability distributions. So we'll talk about the rules that expected values have to follow. We'll talk about the basic mechanics of how you calculate expected values for discrete random variables and continuous random variables. And we'll talk about important subclasses of expected values, the mean, variances, and we'll talk about how to interpret variances because they're a little bit trickier with Chebyshev's inequality. The expected value or mean of a random variable is the center of its distribution. It's in essence a particular definition of the middle of a distribution. There's more than one definition of the middle of a distribution. For example, the median would constitute a different definition of the middle of a distribution. But the mean is a particular one, and we'll talk about the intuition behind it in a minute. And consider how you would calculate the mean for an example for a discrete random variable. We denote the mean with this capital E here, which stands for expected value. And then usually, for whatever the reason, we tend to use square brackets for expected values rather than parentheses. And so we might write expected value of X. Here, again, we're using a capital X because we're talking about a conceptual value of the random variable. This, in the case of a discrete random variable, is the sum over all possible values that X can take of X times P of X. Now note here, if we didn't have this X out in front of the P of X, this would just sum to 1 because the PMF sums to 1 by the definition of a PMF. So this X out in front is what turns it into an expected value. Here we're just talking about the expected value of X, but if we wanted the expected value of X squared, it would be the sum over X, and we would have a little square in front of the X right here that we're summing over. So sum over X squared times P of X. E of X, one way to think about expected value of X is that it represents the center of mass. If the X's are locations and the P of X's are weights. And I have kind of a schematic here on the next slide that shows an example. So imagine if on the horizontal lines here, let's suppose the leftmost line is at the point 0, and it's just a real line extending in the positive direction. And each location of a line here is the value that X would take. So in this case, x takes 4 possible values, 2 low values and 2 high values. And the height of the bars is p of x. So in this case, p of x is equal for each of the 4 bars. So because p of x is a probability mass function, each of these 4 bars would have to take value 1/4. So the expected value then would be the center of this distribution, the point at which you would balance this out if this was, say, for example, 4 little bars and you wanted to put your finger on the horizontal bar so that it would balance out. And here, of course, because the bars are all the same height and you have 2 on the left side and 2 on the right side placed in the same configuration, the geometric center of mass would be right in the middle. Well, what would happen, consider the one next to the right, what would happen if you had 3 all squashed up on the right-hand side and 1 really far on the left-hand side? Well, the one really far on the left-hand side would pull the mean away from the center of the 3 just to a little bit outside of it. And then I go through 2 other cases over here where I vary the heights of the bars and their configuration. In each of these cases, the fulcrum point at the bottom is exactly where you'd have to put it to balance out the bars. And that's where the expectation gets its definition from. It actually draws exactly from the physics definition of center of mass. And in this case, it's exactly just another property of a probability mass function in order to characterize it. Let's talk about how you calculate the expected value for a coin flip. So in a coin flip, our sample space is heads or tails, and we'll define our random variable as being 0 for tails and 1 for heads. Let's calculate the expected value for the probability mass function from a fair coin. That is, it's a 50% chance of tails and a 50% chance of heads. So let's plug directly into the formula. The expected value of the coin flip, x, is 50% 0.5 probability of a tail times the value we've assigned for a tail, 0, plus 0.5 times the value we've assigned for a head, 1. Add those up and you get 0.5. So the expected value of a coin flip is 0.5. This exactly makes sense if you think back to our previous page. If you had a bar at 0 and a bar at 1 and they were both equal height, you would put your finger right at the 0.5 to balance out that bar. So it maps intuition. Also note, the expected value does not have to be a value that the random variable can take. In this case, the random variable can only take values 0 or 1, but the expected value is 0.5, which is between the two. Okay, let's go through the same exercise, but now instead of a coin, let's talk about a die. Here, the possible values that the die can take are 1, 2, 3, 4, 5, and 6. We're going to assume that the die is fair. So all of the numbers have probability 1/6 of occurring. What's the expected value of that die roll? So we denote the expected value again by E bracket X. Here we have 1 times the probability of getting a 1, 1/6, plus 2 times the probability of getting a 2, 1/6, and so on. And if you add them all up, you get 3.5. Again, this makes perfect sense. You have 6 bars of equal height, 1 at position 1, 1 at position 2, 1 at position 3, 1 at position 4, 1 at position 5, and 1 at position 6. And of course, if you were to balance that out with your finger, you'd put it right in the middle of those numbers as 3.5. That covers discrete random variables, at least 2 examples of discrete random variables. Let's talk about how you do continuous random variables. Well, again, the definition follows exactly from the physical definition of center of mass. And in this case, the expected value of a random variable x is the integral from minus infinity to plus infinity of t f of t dt. And here, t is just the dummy variable of integration. So it's pretty much the same formula. Here, if you omit this value t right here, then the integral just works out to be 1 again, because f is a probability density function. So it's putting the t there that turns it into expected value. If you wanted the expected value of x squared, then it would be integral minus infinity to plus infinity t squared f of t dt. And this just borrows from the definition of center of mass for a continuous body rather than the center of mass of a group of discrete bodies, exactly from physics. And again, it's just a description, or it's a useful summary of the density function f, which is a complicated functional construct, it reduces it down to one number, which is a property, which is what we kind of think of this as at least one of the definitions of the center of the density f. Let's go through an example of calculating the expected value of a particular kind of random variable, one that we have not encountered before. So let's think of a very simple density. The density is such that it's 0 below 0, constant at the value of 1 between 0 and 1, and it's 0 above the value 1. So let's mentally, just real quick, verify that this is in fact a valid density. Well, this density is exactly a brick, starting at 0, ending at 1, with height 1. You don't even need calculus to verify that this integrates to 1 because it's just a square. Its area is the length of the base, which is 1, times the length of the height, which is 1. 1 times 1 is 1, so it's a proper density. It's also positive everywhere because it's 0 below 0, 0 above 1, and the value 1 between 0 and 1, so it's positive everywhere, so it's a valid density. This is in fact actually an extremely important density. It's a pretty simple one, but it's an extremely important density, and it's called the standard uniform density. It sort of represents the idea that any value between 0 and 1 is equally likely. So imagine if you were to drop a pencil on a line between 0 and 1, and you were dropping that pencil in such a way that it was equally probable to land anywhere between 0 and 1, this density would represent that process. Well, let's go ahead and calculate its expected value. Now again, we already know what the answer is from the geometric argument. It's a brick that starts at 0 and ends at 1. The answer has to be 0.5 because if you wanted to balance that brick out, you would have to put your finger right in the middle. So let's just verify that calculation. Here, our expected value of our uniform random variable x is the integral from 0 to 1. And again, we have x, right? In the previous slide, I had t, but let's just use x in this slide, times the density, which in this case is just the constant 1, so I just didn't write it down, then dx, the variable of integration. And so that integral is x squared over 2, evaluated the bounds 0 to 1, which works out to be 1/2, exactly what we would have thought. Incidentally, I just want to remind everyone of this notation. The capital X in the expected value represents a conceptual value of the random variable, whereas the little x in this equation represents the dummy variable of integration, a value that's actually getting numbers plugged into it. So it wouldn't have mattered for this little x if we had used x or t or z or w or whatever. However, it's important that we kept it at capital X. That's what we've assigned this random variable, the value capital X. So it's a small point, but keep that in mind. So I wanted to talk about something that always comes up in my in-person classes when I talk about this. So here we calculated expected value of x. And I told you that expected value of x squared, well, you would just calculate integral from 0 to 1, x squared dx. And a question that always comes up in class is, well, wait a minute, I could calculate expected value of x squared that way, or I could figure out what the distribution of the square of a uniform actually is, right? A uniform random variable is a random variable representing some process. So the square of that has to be a random variable, and it itself must have a density. So I should be able to calculate the expected value from that density, and it should be the expected value of y. Let's say if y is x squared. Do I get a different answer if I figure out what the density associated with the square of a uniform random variable is? Do I get a different answer if I calculate the expected value that way, or if I calculate the expected value this way by just putting a square into the expected value calculation from the original uniform density? At any rate, you'll be happy to know that you get exactly the same answer. And in fact, I would also add that it's a lot easier to just put the square in this integral equation because we automatically know off the top of our head what the density of a uniform random variable is. We may or may not know what the square of a uniform random variable is. So this should give you some basic examples of calculating discrete and continuous expected values. In the problems, you'll have both harder and easier examples to work out, and in the assessment, we'll have harder ones. In the next section, we'll talk about rules that expected values have to take. So previously we talked about expected values and their properties and a little bit of how to calculate them. Now let's talk about the expected value operator itself. And the expected value operator is in fact a linear operator, and that'll greatly simplify calculating expected values for some relatively complicated things. So let me assume that A and B are not random numbers. So when you think about A and B, think A is something like 5. It's this number that you can plug in. And X and Y are actually two random variables. Then expected value of AX plus B works out to be A expected value of X plus B, exactly what you'd hope it to work out to be. And expected value of X plus Y works out to be expected value of X plus the expected value of Y. And the reason it works out in these cases is because the expected value is a linear operator. It is not always the case that expected value of G of X is equal to G of expected value of X, where G is some general function that's not linear. This can happen with specific random variables and specific values of G, but in general, it's not the case. The most sort of famous example where it's not the case is that expected value of X squared is not equal to expected value of X whole thing quantity squared. Now let's talk about what the difference of these two entities is. What do we mean by the difference between these two things? Here, X is a random variable. X squared is the random variable you obtain by squaring X. So, for example, if X is a die roll, it can take values 1, 2, 3, 4, 5, 6. X squared then can take the values 1, 4, 9, and it takes those values with probability 1, 6 each. So the expected value of X squared represents the expected value of the squared random variable. On the other hand, expected value of X quantity squared represents what you obtain if you first calculate the expected value of X and then square the result. And these two things are not equal. This is a well-known example where expected value of G of X is not equal to G of expected value of X, and we'll see in a couple of slides why it is a well-known example of that property. But in general, I would like you to remember that if G is not a linear function, then you can't just commute expected values outside of G to the inside of G. And that rule will generally hold. If it's linear, if G is a linear function, then you can always do it. If G is not linear, just in general, think that you cannot. The expected value rules hold no matter what constitutes X and Y. X could be discrete, continuous, mixed, discrete and continuous. Y could be discrete, continuous and mixed, and the rule still holds. So let me go through an example. Suppose you flip a coin X, and as we normally do, X is 0 if it's tails and 1 if it's heads, and you simulate a uniform random number Y. The random number is between 0 and 1. What's the expected value of their sum? Well, the sum of a coin flip and a uniform random variable is a weird distribution. It's not obvious, especially if all you've had is the handful of lectures from this class, how you would calculate that distribution. And then from that distribution, then calculate the expected value. However, we do know how to calculate the expected value of a uniform random variable and the expected value of a coin flip. And so the expected value of their sum is the sum of their expected values. We know the expected value of the coin flip is 0.5. We know that the expected value of the uniform random variable is 0.5. So that expected value is 1. So you can see how these expected value operator rules make calculating things associated with expected values a lot easier. Another example is suppose you roll a die twice. What is the expected value of the average of two die rolls? So you often roll two dies when you're playing a board game, for example. Okay, let's let x1 be the result of the first die and x2 be the result of the second die. Now, the variable that we're interested in, let's call it y, equal to x1 plus x2 divided by 2. Now, one way you could calculate the expected value of y is to figure out what the distribution was of the average of two die rolls. So let me give you a sense of this really quickly. The reason we think the distribution of a single die roll is 1/6 at each number is if you roll a die a lot of times, you get about 1/6 of the die rolls are 1, 1/6 are 2, 1/6 are 3, 1/6 are 4, and so on. And then kind of geometrically, we're modeling the process as if they're all equally likely. And so that's why we're going to model the population of die rolls as having probability 1/6 on each number. Now, this implies a distribution on the average of two die rolls, right? The smallest number it could take is 1, right? 1 plus 1 divided by 2, the average of if you were to get two ones. And the largest it could take is 6 plus 6 divided by 2, or 6, if you were to roll two sixes. But it takes different values in between, and it's not equally likely for all the numbers in between. A 1 has probability 1/36, but some of the middle values have higher probabilities. So this, at any rate, our variable y itself has a distribution, and you could get a pretty good sense of it. Maybe you could do this by taking two dies, rolling them, taking the average, rolling them again, taking the average, doing that over and over and over again, and plotting, a bar plot of the frequency of the averages that you get. And that'll give you a good sense of what the population distribution is, or you could work it out on pen and paper as to what the distribution actually is. And then once you get that worked out, then you could use your expected value formula to calculate the expected value of y directly by doing summation over all the possible values of y times p of y and calculate its expected value. Another way to do it is to directly use the expected value as a linear operator rules. So in this case, expected value of x1 plus x2 divided by 2 is 1/2 expected value of x1 plus the expected value of x2, because the 1/2 is a non-random variable that we can just pull out, and the expected value goes across the two sums here to get expected value of x1 plus the expected value of x2. That then yields 3.5 plus 3.5 divided by 2, which is 3.5. Now you might be wondering after hearing this is, oh, that's interesting. The expected value of the average of two die rolls is the exact same as the expected value of an individual die roll. And that is exactly the case, but you're probably thinking, maybe does this extend beyond that? Is the expected value of the average of n die rolls equal to the 3.5 as well? And the answer is yes, that's exactly true. In fact, that's a nice segue into our next slide, where we actually derive the property that we were hinting at in the previous slide, namely that the expected value of the average of a collection of random variables from the same distribution is the same as the expected value of the individual random variables. So let's let xi for I equal 1 to n be a collection of random variables, each from a distribution with mean mu. Just want to also point out that we tend to use Greek letters to represent population quantities. In this case, the population mean of the distribution is mu. So let's calculate the expected value of the sample average of the xi. Well, we want the expected value of the sample average, which is 1 over n, summation I equals 1 to n to the xi's. The 1 over n pulls out because it's not random. The expected value commutes across the sum. And the expected value of each of those xi's is itself mu. So we get the summation I equal 1 to n of mu. We get mu added up n times then, which is n mu, divided by n on the outside. So we get mu. So what this says is it doesn't matter what the distribution of the individual x's is, the distribution of the mean of the x's has the same mean as the individual means. So let me just summarize one more time. The expected value of the sample mean is the population mean that it's trying to estimate. The population mean of the distribution of the sample mean of n observations is exactly the population mean that it's trying to estimate. And so when this happens, when the expected value of an estimator is what it's trying to estimate, that's a good thing. We say that the estimator is itself unbiased. So sample means are unbiased estimators of population means. And again, there were some assumptions for this to be true, right? All the x's have to be from a distribution that has mean mu being the value you want to estimate. And then the sample mean is an unbiased estimator of the population mean. And we're finally getting to the point where we can talk about how we're going to connect our probability modeling to the data that we observe. We're not quite there yet, but we're getting closer and closer to this. And I want you to remember that we're throwing around the term mean a lot. And so if you get confused, I want you to remember to qualify the mean that you're talking about, whether it's a population quantity, i.e. component of the probability distribution, or a sample quantity, an empirical quantity that you connect from the data. And remember, our goal in probability modeling is to connect our sample observations to the population using our probability model. So the variance of a random variable is another expected value property of a distribution. Recall the mean measured the center of a distribution. The variance measures how spread out it is. So if x is a random variable and it has mean mu, i.e. expected value of x equals mu, then the variance of x is defined as the expected value of quantity x minus mu, whole thing squared, and the expected value. So what does that mean? So the expected value is in essence an average, right? So it's sort of the average or the typical value that the random variable takes. It's the center of the distribution. On the other hand, the variance is sort of the average distance the random variable is from the mean. So what that means is sort of higher variances imply that variances are more. What that implies is that random variables with higher variances come from distributions that are more spread out than ones that have a lower variance.
That makes sense. And I'm just kind of thinking of that fulcrum point still.
Yeah.
You know, if things are more spread out, there's going to, yeah.
Exactly.
Okay, cool.
Exactly. Great.
All right.
And so let me just remind you what this formula, the variance formula, means again. If you were to take the random variable x and figure out what the distribution was if you were to subtract off its population mean, which turns out to be the exact same distribution, just with all the possible values of x shifted by the value mu, and then it has mean 0. And then I were to take that random variable and figure out what the distribution of the square of it is, then take the expected value of the resulting random variable. And that's hard. So we don't ever calculate the variance that way. We typically calculate the variance by a convenient shortcut. And that is that the variance of a random variable is the expected value of x squared minus expected value of x quantity squared. And again, this expected value of x quantity squared is just mu squared. This shortcut formula then requires you to calculate the expected value of x squared. But again, the kind of typically the more convenient way to do that is to use, if it's discrete, the summation of say t squared p of t, where p is the probability mass function, or if it's continuous, use integral t squared f of t, where f is the density function. It would be nice for you as an exercise to show that this original variance calculation equals this shortcut variance calculation just by expanding the square and using the expected value rules. It would be convenient if the variance operator was also linear. It's not. As an example, the variance, if you pull a random variable out of the variance, it gets squared. So variance of a times x, where a is not a random variable, is a squared variance of x. The square root of a random variable is called the standard deviation. And the reason we use standard deviation often instead of the variance is that the standard deviation has the same units as the random variable. So let's say x as a random variable has units in inches. The variance has units inches squared, whereas the standard deviation has units inches. So it's often quite convenient to talk about the spread in the same units as the random variable itself. So the standard deviation is a very common summary of the variance. Well, let's calculate a sample variance. What's the sample variance from a toss of a die? So in this case, expected value of x is 3.5. We've covered that already. And expected value of x squared, let's calculate that. Well, we have 1 squared times a sixth plus 2 squared times a sixth plus 3 squared times a sixth plus 4 squared times a sixth plus 5 squared times a sixth plus 6 squared times a sixth. That works out to be 15.17. And then you subtract 15.17 minus 3.5 squared, and that works out to be about 2.92. let's go through a very important formula. Let's suppose we flip a coin, but let's make it slightly more interesting. Instead of the coin having probability 1/2 of a head, let's say that it has probability P of a head. So here, expected value of x equals 0 times the probability of a tail, which is 1 minus P, plus 1 times the probability of a head, which is P. So it works out to be P as the expected value. And of course, this agrees with our calculation when the P happens to be 1/2 for a fair coin. Now let's calculate the expected value of x squared. Well, actually, it's kind of interesting in this case. It's pretty easy to do that because x takes only the values 0 and 1. And if you square 0, you get 0. And if you square 1, you get 1. So x squared is in fact exactly x. So expected value of x squared is equal to the expected value of x, which we already calculated is P. So the variance of x in this case is expected value of x squared minus expected value of x quantity squared, which is P minus P squared, which works out to be P times 1 minus P, which is a formula you may have encountered before. It's interesting to note that this variance formula is maximized when P is 0.5. So just simply plot the function P times 1 minus P between 0 and 1. So plot this function between 0 and 1, and you'll see that it maximizes at 0.5. So the most variable coin flip can be is, in fact, exactly a fair coin. It's interesting to note that the most variable a random variable can be in general is if you shove all its mass to two endpoints and equally distribute it between those two endpoints. That's so if you have a continuous random variable and you want to make it more variable, kind of chop out the middle and spread it out equally distributed between the two ends. And in fact, let's talk about this in greater detail. Suppose that you have any random variable, like a uniform random variable, that's between 0 and 1, and its expected value is P. Now, since the variable takes values between 0 and 1, P has to be a number between 0 and 1. And then notice if x is a random variable that's between 0 and 1, x squared has to be less than or equal to x. Because if you take any number between 0 and 1 and square it, you get a smaller number. And so expected value x squared has to be less than or equal to expected value of x, which is P. Therefore, the variance of x, which is expected value of x squared minus expected value of x quantity squared, has to be less than or equal to the expected value of x minus the expected value of x squared, which is P times 1 minus P. And basically, this is then just a proof that the Bernoulli variance, this binary variance where the random variable can only take the value 0 or 1, is the largest possible for a random variable that has expected value of P. And then we also noted that earlier that the maximum value that you can get is when P is in fact 0.5. So this basically just shows that this is basically a simple little proof that the random variable, that the largest variance that you can get for a random variable is that you sort of shove its mass to two endpoints, and the closer you can get to an equal mass in both the endpoints, the larger the variance is. I'm not sure if I've mentioned this previously, but I called the variable a coin flip that can take heads with probability P. I called it a Bernoulli random variable. This is named after the mathematician Jacob Bernoulli, who is one of the fathers of probability. And Jacob Bernoulli is an interesting character. You should read up on him. The Bernoullis were a very famous mathematical family. They came up with lots of discoveries. Jacob was a particularly influential member of the Bernoulli family, and he discovered quite a bit of probability theory very, very early on. At any rate, when you have a random variable that takes the values 0 or 1 with probability P, then we call that a Bernoulli random variable. So here we are back talking about variances, and variances are kind of difficult things to understand, and equivalently standard deviations. I prefer to interpret standard deviations. intuitively, we know that bigger variances mean distributions are more spread out, but we need some way to actually interpret what bigger means. Now, in the context of a specific distribution, we might learn the kind of quantities associated with that distribution to know that, well, what does one variance mean, or 2 standard deviations mean, 3 standard deviations mean, and that's particularly true of the Gaussian or bell-shaped density. We tend to know the values associated with those variances sort of by heart. But there is a general rule that applies to all distributions, and it's so-called Chebyshev's inequality, after the Russian mathematician Chebyshev. So at any rate, Chebyshev gives a really useful inequality for interpreting variances. So basically, the inequality says the probability that a random variable is k standard deviations from its mean or more is less than or equal to 1 over k squared. So let me repeat that because it's so important. The probability that a random variable is more than k standard deviations from its mean is less than or equal to 1 over k squared. And let's just look at some simple benchmarks for k. The probability that a random variable is more than 2 standard deviations from its mean is 25% or less. The probability that a random variable is 3 standard deviations from its mean is 11% or less. And the probability that a random variable is 4 standard deviations from its mean is 6% or less. And again, note that this is a bound on the probability statement. It's not an equality. So it's the worst that it could possibly be. The lots of distributions, the probability of being 4 standard deviations or more beyond the mean is far lower than 6%, but 6% is the worst it can be. So it's unlikely, say, for example, that you will, if you observe a random variable, it's unlikely that you will see that random variable be, say, 6 standard deviations from the mean. That's quite unlikely. That's has probability less than 1 over 36, regardless of the distribution. What's interesting about Chebyshev's inequality is that it's quite easy to prove. And so let's just go through the proof really quickly. Well, let's look at this probability statement. The probability that a random variable is more than k standard deviations from its mean, and let's do it in the continuous case. Let's just do it in the continuous case. You can prove it more generally, but this just gives you the intuition behind the proof. Well, that's the integral over the set of x where it's more than k standard deviations from the mean. Where here now the little x in the domain of integration is a dummy variable of integration, f of x dx, and this could be, we could replace this by another letter over on the right-hand side, but on the left-hand side it has to be capital X. Well, notice that x minus mu over k sigma, absolute value x minus mu over k sigma, has to be bigger than 1. So if we square that, it has to be bigger than 1 as well. So if you take a number that's bigger than 1 and square it, it's still bigger than 1. So we can multiply by x minus mu squared over k squared sigma squared, and we've only made the integral bigger, right? So we can replace this equality with an inequality where here the alligator's chomping the bigger part. Okay, so now we have this quantity here, and we'll only make it bigger yet if we, instead of integrating over this restriction of the domain, we integrate over the whole thing from minus infinity to plus infinity, because everything, the x minus mu squared is strictly positive, so we'll only make it bigger. And then notice now that the k squared sigma part is a scalar that we can just factor out, and then we have minus infinity to plus infinity x minus mu squared minus infinity to plus infinity integral of x minus mu squared f of x dx. Well, that's just exactly the definition of the variance. And so that equals sigma squared. The sigma squareds cancel and you get 1 over k squared. So we see that the probability that x is more than k standard deviations from the mean, we started out with an equal sign, we got bigger, then we've had a final equality. So the whole thing is less than or equal to 1 over k squared. So I find it remarkable that Chebyshev's inequality, this powerful result that applies to all distributions, has such a simple little proof. Let's go through some numerical examples just to show why this result is useful. So intelligence quotients, and I would recommend that you look up intelligence quotients. Are often called Binet scales. They have a very rich and interesting history that intersects with statistics and several other fields in psychology and so on. And it's really quite an interesting literature on intelligence quotient. So I would highly recommend you look it up just because it's quite fun. But let's kind of skirt that discussion and just say, let's suppose intelligence quotients really are distributed with a mean of 100 and a standard deviation of 15. What's the probability that a randomly drawn person from this population of people that have IQs with mean 100 and standard deviation of 15, what's the probability of drawing a person with an IQ higher than 160 or below 40? And of course, I picked the 160 or 40 specifically. Well, 160 is 4 standard deviations above the mean, and 40 is 4 standard deviations below the mean. So Chebyshev's inequality that this will be no larger than 6%. If in fact the IQ distribution is bell-shaped or is Gaussian, this bound is very, very conservative. Just to give you a sense of how conservative, the probability that a random draw from a bell curve being 4 standard deviations from the mean is not 6%, but on the order of 10 to the minus fifth, 1,000th of 1%, which again, it doesn't violate Chebyshev's inequality. 10 to the minus fifth is less than 0.06, so it's fine, but it's quite a bit less. So just to give you a sense of how conservative Chebyshev's inequality can be. Let me go through another example. So a buzz phrase in industrial quality control is Motorola's so-called Six Sigma. And I have to admit to being largely ignorant of exactly what the Six Sigma industrial protocol is. But the gist of it, as far as I understand, is that businesses are suggested to control extreme events or rare defective parts. And the idea is that you go out 6 standard deviations. So let's, as an intellectual exercise, maybe you on your own can go look up what exactly the Six Sigma protocol is. Let's, on it as an intellectual exercise, talk about what the probability of 6 sigma events are. The idea of having a random variable that lies 6 standard deviations above the mean. Well, that's by Chebyshev's inequality, 6 standard deviations above or below the mean. By Chebyshev's inequality, that's the probability of such an occurrence is less than 1 over 6 squared, which is about 3%. So it's highly unlikely. But again, remember, Chebyshev's is a bound that applies to all distributions. If you know something about the distribution, for example, if you know the distribution is a bell curve, then the probability of a 6 sigma event is on the order of 10 to the minus ninth, which is, I calculated as 1/10,000,000th of a percent. So again, that doesn't violate Chebyshev's inequality. 10 to the ninth is less than 0.03, so it doesn't violate Chebyshev's inequality. But at any rate, that's what a 6 sigma event is discussing. Hi, my name is Brian Caffo. I'm in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health, and this is Mathematical Biostatistics Boot Camp, Lecture 4. Today we're going to talk about random vectors and independence. Independence is a key ingredient in simplifying statistical models. Independence is a useful assumption, and we frequently use it in statistics to get a handle on complex phenomena. In addition, we'll find that independence and identically distributed random variables are going to be our canonical model for what we might think of as a random sample. So let's just briefly talk about what we're going to cover today. Random vectors, which are simple collections of random variables. Then we'll talk about independence, and you probably have a rough idea of what is meant by independence to begin with, but we're going to talk about the mathematical formalism a little bit. We'll talk about correlation, and then go over various mathematical properties of the correlation and covariance operators. And then we'll use our facts about independence and variance and correlation to talk about properties of the sample mean. And then we'll cover the sample variance and end with some discussion. This lecture is actually one of the hardest things in all of statistics. I think if you can kind of understand this lecture, you've understood what the goal of probability modeling and this kind of population modeling really is. You might want to consider listening to it over and over again. And it's incredibly difficult concepts until you internalize them. And then once you internalize them, they seem simple. So what I'm hoping in this lecture to do is to help you internalize them. Okay, so a random vector is nothing other than an ordinary vector with random variables as its entries. So if you have x and y as random variables, then simply the ordered collection x comma y is a random vector. So just like individual random variables have densities and mass functions or distributions that govern their probabilistic behavior, random vectors have joint densities and joint mass functions and joint distribution functions that govern their probabilistic behavior. Let's just simply talk about densities and mass functions to begin with. A joint density f of x comma y, first of all, it has to satisfy that it's positive everywhere. It's the two-dimensional random vector. So this surface f exists on the two-dimensional plane, and the fact that f is greater than 0 suggests that its height everywhere is above the horizontal plane. And it has to integrate to 1, but when you integrate over the whole xy plane. So the z direction has to be greater than 0, and the integral over the xy plane has to be 1. So it's a direct extension of the ordinary one-dimensional probability density function. And I think from this definition, you should probably be able to guess what the definition of a joint density is for 5n random variables. And then for discrete random variables, let's say f now is a joint probability mass function, then the joint probability mass function f maps possible values of x and y here, so lowercase x and lowercase y are the possible combined values of x and y, to probabilities. So to satisfy the definition of being a joint probability mass function, f has to be bigger than 0 for all possible combinations of x and y, and then the sum over all possible combinations has to equal 1. By the way, the joint density function exactly works like a univariate density function in that, in this case, volumes under it, so integrals under it, correspond to probabilities. And so the total area is 1. And in the same case with the joint mass function, the sums of collections of possible values of x and y yield the probability of that collection. So for this class, a general discussion of random vectors is probably too much. So we're only going to focus on one specific kind of joint densities, the particularly manageable type, and that's when the random variables x and y are independent. And what we'll see is that for, say, a joint density or a joint mass function, if the random variables x and y are independent, then the joint density just factors into the product of the two individual densities, the f of x and g of y. And basically, this is what mathematically independence does for us a lot, is it turns complicated multivariate structures into products. We're going to use this fact a lot, and we'll explain some of the intuition behind this. Thinking back to our early definitions of probability, we were discussing the sample space and events. Two events are independent if the probability of their intersection is equal to the product of their probabilities. So probability of A intersect B is probability of A times the probability of B. So A and B are independent. Incidentally, if this is true, then A is independent of B complement, B is independent of A complement, and A complement is independent of B complement. And the mathematical definition of independence is equivalent to our kind of intuition of what it means to be independent. A is unrelated to B. That's what the mathematical definition implies, and we'll kind of get a better sense of that. For two random variables, we would maybe define that they're independent if you have any two sets, A and B, that probably the X lies in A and Y lies in B is the product of the probability that X lies in A regardless of what Y is doing, and the probability that Y lies in B regardless of what X is doing. And so that's just simply a direct extension of the definition of independence above that I think probably everyone is maybe a little bit familiar with. We automatically think of independence all the time already. So if you were to ask nearly anyone who has a basic amount of mathematical training, what's the probability of getting two consecutive heads on two consecutive coin flips, they would probably say, okay, well, the probability of getting a head on the first one is a half, and the probability of getting a head on the second one is half, so it's probably a quarter, right? Well, that is just an exact execution of the independence rule. Let A be the event that you get a head on flip 1, B be the event that you get a head on flip 2. Then basically what you're saying is you want the probability of the intersection, a head on flip 1 and 2. And so then the probability of that intersection is exactly the product of the probabilities via independence. Probability of A times the probability of B. So 0.5 times 0.5, which is 0.25 or a quarter. So we use independence all the time, and the main consequence of independence is that probabilities of independent things multiply to obtain the probability of both occurring. But this creates a problem in that people have then gone on to extend this rule to where they just multiply probabilities regardless of whether they're independent, and this can lead to tragic consequences. Here's a great example. In Science, volume 309, they report on a physician who gave expert testimony in a criminal trial. And he was giving expert testimony on sudden infant death syndrome, SIDS, which is this tragic phenomenon where a baby dies, for example, in the middle of the night, and no one exactly knows why. So a woman was on trial because she had two consecutive children who died of SIDS. And there was a court case that then considered whether or not this was too unlikely to happen by chance, and that there really wasn't SIDS, it was something malicious on the part of the mother. So the person who was testifying did the following calculation. The person said that, well, the probability of SIDS is 1 out of 8,543. I'm not 100% clear where they got that number, but let's assume for the case that's correct. Then the person giving the testimony said, well, then the probability that you have two SIDS would be the product of that number twice, or the square of that number, 1 over 8,543 squared. Based on this evidence, the mother was convicted of murder. So what was this physician's mistake in this case? For the purpose of this class, there's actually quite a bit of discussion you could have over ethics, probability, evidence, and culpability based on this case. There's quite a collection of complicated issues that intersect when you're discussing a case like this. For example, where and how does this probability of a SID come from? What's the evidence for it? How do you balance medical evidence when convicting a person or not convicting a person in a trial? For the purpose of this class, let's just simplify the discussion down to, is this direct calculation warranted of simply multiplying this number twice, given that it's correct? Well, if A1 is the event that the first child died of SIDS and the A2 is the event that the second child did, then the inherent calculation the inherent assumption being made is that A1 is independent of A2, so that you can multiply probability of A1 times the probability A2. But this logic fails immediately. There's no reason to believe that the event of a second SID is independent of the event of a first SID. So in this case, and in many cases in biology, biological processes that have a genetic or familial component would tend to be dependent within families. So you couldn't multiply the marginal probabilities to obtain the intersection. And there's other problems, and I outlined an example of one here with this estimate. The prevalence was obtained from an unpublished report on single cases. And quite a bit of the discussion surrounding this case revolved around these and other issues. But the point I'm trying to make for the purposes of this class is you can't just go around multiplying probabilities willy-nilly. The random variables or events that you're discussing have to actually be independent. Okay, so we'll use the following fact extensively in this class, and we'll use it as a basic simplifying principle. If we have a collection of random variables that are independent, x1 up to xn, then the joint distribution of x1 to xn, or the joint density function, is the product of the individual densities or mass functions. So in other words, the density of f of x1 up to xn is the product of the individual densities. And here I have fi of xi, indicating that every xi could potentially have a different density. The most common model that we'll be dealing with is the instance where x1, x2, all the way up to xn are from the same distribution. And this particular case, we would say that the xi's are independent and identically distributed, the independent being that x1 is independent from x2 and so on, and identically distributed in that f1 is equal to f2 is equal to all the way up to fn. The IID samples are very important in the subject of statistics. And the reason for that is because IID random variables are a basic kind of default model for random samples. If you have a collection of things that are, in essence, we believe exchangeable, then we treat them as if they are IID. And many of the important theories of statistics are founded on the assumption that variables are IID. So to give you an example of IID random samples, imagine just simply rolling a die. Each roll of a die is a draw from the uniform distribution on the numbers of 1 to 6. So when we say that a process, when we model a process as if it's IID, we're saying it's like we're rolling a die for each variable that we're modeling from some population level distribution. I just want to comment on the broader discussion on probability modeling. This is never actually the case, right? It's probably a very good model for rolling a die, but we use IID to model things where surely the variables themselves are not IID. We can rarely guarantee that our sample is actually a random draw from some population distribution F over and over again. The point is that it's a statistical model used to simplify calculations and simplify our discussion. But whenever we use this statistical model, we have to be cognizant of the fact that it is a model and it's an enormously simplifying assumption. Let's just go through a very important example of flipping a coin. So imagine if we have a biased coin, and remember, if we have a biased coin, let's say the probability of a head or a success probability is P, and we flip it n times. Well, what's the joint density of the collection of possible outcomes? Recall, each coin flip here is a Bernoulli random variable with success probability P. And recall, we wrote out the density in the form p to the x, 1 minus p to the 1 minus x. And notice that's a very easy form, right? So if you plug in x equal 1, you get the probability p of a head or of a 1. And if you plug in x equals 0, we get 1 minus p for the probability of a tail or a 0. So this density is a nice way to represent it. And you'll see why we represent it specifically this way in the next line. So the joint density is the joint mass function f of x1 to xn. If they're independent coin flips, right, is simply the product of the individual densities. And you'll see from this formula we get p raised to the summation xi, 1 minus p raised to the n minus summation xi. So if the x's are all zeros and ones, this works out to be p to the number of heads, 1 minus p to the number of tails. And that's basically why we write out the density this way, is because if we have a bunch of independent coin flips, then it's convenient that the mass functions multiply, and we wind up with this nice form for the joint mass function. So if you wanted to say, for example, if I have a biased coin with success probability P, and I had 4 coin flips, and I wanted to know what's the probability of getting a 1 and then a 0 and then a 1 and then another 1, so 1, 0, 1, 1, you would just simply plug into this formula. And notice the order of 1, 0, there we got 3 heads and 1 tail. Notice the order doesn't matter. We would need P to the 3, 1 minus P to the 1 would be the probability of that occurrence. And notice it's the same probability regardless of what order the 1s and 0s occurred. So this formula makes it easy to calculate the joint probability for a collection of 1s and 0s from a potentially biased coin flip. I just want to mention again that this model is tremendously important. So imagine, for example, we want to model the prevalence of hypertension in a population. One way we might go about doing that is to say that our sample is IID. And again, that's often a big assumption that people are IID draws. Individuals are coin flips. And what we would like to know is their success probability of having hypertension. And so that success probability is the prevalence of hypertension in the population. And we would use this joint mass function to model that process for our collection of data. And that's the idea behind where we're going with this. But notice there's a lot of assumptions that go into that, right? I just want to emphasize this fact quite a bit. We're assuming that we're randomly drawing people from the population that we're interested in, or not even that we're randomly drawing them, but that we can model the collection of people, their hypertension status, as if they were a bunch of independent coin flips with the prevalence being the success probability. That's ultimately what our model is stating. So it's important to always keep that in mind. So let's stop here and we'll next talk about some of the mathematical properties associated with random variables and covariance and correlation and their consequences when variables are independent. Okay, so welcome back, troops. We're going to talk about covariance and correlation now and what happens when random variables are independent. So if we have 2 random variables, x and y, then their covariance is defined as here cov x comma y, the expected value of x minus its mean times y minus its mean whole quantity. And just like the variance, there's a shortcut formula for covariances. And it works out to be expected value of x times y minus the expected value of x times the expected value of y. So there's some very useful facts about covariance. First of all, the covariance, you can interchange the variables and you get the same number. So covariance of x comma y is covariance of y comma x. The covariance can be negative or positive, but in an application of so-called Jensen's inequality, we'll tell you that the absolute value of the covariance of x comma y is less than or equal to the square root of the variance of x times the variance of y. So we could just write this right-hand side as the standard deviation of x times the standard deviation of y. This final property is very useful because as we go on to the next slide, we use it to define the correlation. The correlation of x and y is nothing other than the covariance divided by the product of the standard deviations. So there's a couple reasons why we might want to do this. From the previous slide, notice that this then normalizes the covariance so that it's between -1 and +1. And that's a very useful thing to do so that maybe we can somehow utilize the idea of covariance across different kinds of random variables. Now, another rationale for doing this is if we look back at our covariance formula, right, it's expected value of x minus the mean of x times y minus the mean of y. Well, that has units of x times units of y, right? So the top part of the calculation has units x times units y. The standard deviation of x has units of x and standard deviation of y has units y. So the bottom part has units x times units y. So the correlation is a unit-free measurement. That's a useful property to have. So if x is in inches and y is in pounds, then the covariance is in inches times pounds, but then the correlation is then unit-free, which is useful. Correlations have some nice properties. One is that the correlation is only plus or minus 1 if and only if the random variables are linear related, x equals a plus by for some constants a and b. Correlation is unitless, as we discussed already. And then we say x and y are uncorrelated if correlation x and y are 0. And sort of the more positively correlated they are, the closer correlation, core x comma y gets to 1, and they're more negatively correlated as core x, y goes to minus 1. And this is, again, a description of a population quantity, not a sample quantity, right? So this is a description of you're using a joint probability mass function or joint probability density function to model the population behavior of x and y. Then we want ways to summarize that joint mass function or joint density function. And the correlation is a summary of how related joint random variables are from this distribution. So it's a summary of a population quantity. And of course, if something's a population quantity, we want sample quantities that are able to estimate them. So probably what you've heard of if you've never had a mathematical statistics class before is the sample correlation. And again, the goal of the sample correlation is to estimate the population correlation if you're using a probability model. So the sample correlation estimates the population correlation. So if you've ever had a sample correlation and you've had a probability model, what you are trying to estimate is the population correlation. The estimand is the population correlation. So it follows the same rule we have so far for everything. The sample variance estimates the population variance. The sample standard deviation estimates the population standard deviation. The sample median estimates the population median. So all these sample quantities have analogous population quantities. So if two random variables x and y are independent, then their correlation is 0. The reverse is not true. Things can be uncorrelated but not be independent. So if they're independent, then they are uncorrelated, but if they're uncorrelated, they're not necessarily independent. In the case of Gaussian random variables, by the way, the two things agree always. But in general, that's not always the case. So let's talk about some useful results that rely on correlation and covariances. And probably the most useful one we'll talk about is this variance idea. So if we have a collection of random variables, x1 to xn, when the x's are uncorrelated, and here I wrote out a very general form, the sum of the x's maybe times some constants ai plus a constant b works out to be the sum of ai squared times the variance of the individual x's. And let's think about the specific case when b is 0 and the a's are all 1. That just means that the variance of the sum is the sum of the variances. And here we just wrote out a slightly more general term. We know in general that constants pull out of variances and get squared. That's why you have the ai squared. And we also know that if you have a random variable and you shift it by a constant b, it doesn't change its variance. It just moves the density to the left or right. So it doesn't change the variance. So the a's and the b's are kind of fluff on top of this equation. The core of this equation is just think about the instance when b is 0 and a is 1, that when the x's are uncorrelated, they don't have to be independent. They just have to be uncorrelated for this result to hold. Then the variance of the sum is the sum of the variances. If they're not uncorrelated, then you can actually calculate what their variance is in a way that it depends on the covariance. It works out to be the sum of the variances with the ai squareds out front plus twice the sort of sum of all the pairs of covariances. So this is a very useful formula. We won't use it in this class, but I thought I'd give it to you. And so notice if they're all uncorrelated, all these terms here are 0, and then we get the top formula. The top formula is what we're really going to use in this class. And it basically says that the variance of the sum is the sum of the variances if you have independent events. The other important thing that this kind of says is that you shouldn't be adding standard deviations. You should probably be adding variances is another way to kind of think about it in general. So this leads to an interesting proof of a useful property that the variance of x bar, the sample mean, is sigma squared over n, and it also leads to the fact that the expected value of the sample variance is sigma squared. These are two very important properties that we'll go on and on about. Okay, so I don't want to prove the general facts from the previous slide. Let's just go through the heuristic because it's pretty easy to do. So let's prove that the variance of x plus y is the variance of x plus the variance of y plus twice the covariance of x and y. So at the top line, let's start with variance of x plus y. Well, just by the definition of variance, right, that's the expected value of x plus y squared minus expected value of x plus y quantity squared, right? So if you're confused by that, just replace x plus y with a random variable z, and it's expected value of z squared minus expected value of z quantity squared, directly plugging into the shortcut variance calculation formula. Well, the right-hand element here is expected values always commute across sums, so we have mu of x plus mu of y quantity squared. And the left-hand side, let's just expand out this x plus y squared to get x squared plus 2xy plus y squared. And then let's just move the expected value across the three elements of this expression. Well, then let's just organize terms, and we get expected value of x squared minus mu of x squared plus expected value of y squared minus mu of y squared, and then 2 expected value of xy minus mu x mu y. Well, this first one, expected value of x squared minus mu x squared, that's variance of x. The second one, expected value of y squared minus mu y squared, that's variance of y. And this latter part, 2 expected value of xy minus mu x mu y, right? Expected value of x times expected value of y for this right-hand part. Well, that's just covariance of x comma y, completing the proof. So you can see that it only requires the basic rules for expected values to perform this calculation and the definition of covariance to perform this calculation. So just to reiterate some things we discussed earlier, if a collection of random variables are uncorrelated, then the sum of the variances is the variances of the sum. So what it basically means is that sums of variances tend to be useful, not sums of standard deviations. And this is just the issue I'm trying to raise is don't sum standard deviations. So in other words, the standard deviation of the sum of a bunch of independent random variables is the square root of the sum of the variances, not the sum of the standard deviation. So it's just a common little problem, so maybe trying to avoid it from the start. There's an important result that arises out of these facts, and the important result is that the variance of the sample mean of a collection of independent and identically distributed random variables is sigma squared over n. So let's assume that we have a collection xi, I equals 1 to n, that are independent and identically distributed, IID, and that the variance of the distribution that they're drawn from is sigma squared. Okay? So let's calculate variance of x bar. Well, that's just the variance of 1 over n times the sum of the x's, right? That's just the sample mean formula, the sum of everything divided by the number of things you added up. The 1 over n is a constant, so we can pull it out, 1 over n squared, and we get the variance of the sum. The variance of the sum is the sum of the variances because the x's are independent, hence uncorrelated. And then because they're IID, the variance of each xi is the same, it's sigma squared, and we've added up n sigma squared, so we get n sigma squared. And so it works out to be sigma squared over n for the final line here. So what does this mean? It's really quite an interesting fact. What this says is if I want to know what's the variance of the distribution of averages of 10 random variables, say, from a distribution, I don't actually have to know what that distribution of averages actually is. So I don't have to do that. All I have to know is what the variance from the original distribution that the individual observations are drawn from, and that gives it to me. I just have to divide that by n, right? So if I want the variance, I divide by n. If I want the standard deviation, take the original standard deviation and divide by square root n. And why is this important? Because remember, eventually we'd like to connect all of these ideas, these population model ideas, to data. And if we have a bunch of things that we're willing to model as if they were IID, well, we get multiple draws from the distribution of individual observations. All the xi's are separate draws from the original distribution. So we can estimate things like sigma squared, but we only get one sample mean. Let's say we have a sample of 100 observations. We only get one sample of 100. So if we calculate the sample mean of all those 100 observations, we have nothing empirically to estimate the variance of sample means of 100 variables. We don't have repeated samples of 100 variables. We only have the one. Well, what this result says is you don't need that, right? Because all you need is the variance of the original population and divide it by n. The variance of the original population is something we can estimate. And so it's a very nifty result. Let me give you an example of this property that you could do at home to just test this result to make sure it's true. Recall in the last lecture, we said the variance of a die roll, which takes values 1 to 6 with equal likelihood, 1, 6 for each number. The variance of a die roll was 2.92. So what that says is if you roll a die over and over and over and look at the distribution, you'll get about 1/6 of each number. And that the variance of that distribution, so if you were to roll it thousands and thousands of times and take the variance of the thousands of measurements, you would get around 2.92. So do that. Roll a die a lot of times and take the sample variance of 1,000 die rolls, for example, and you'll get about 2.92. Why is that? That's saying because the sample variance of lots of die rolls estimates the distribution of the population of die rolls, which is this uniform distribution on 1 to 6, and its variance is 2.92, so you'll get that. Now here's the question that the calculation on the slide is answering. Suppose now, instead of rolling a die over and over again, you rolled 10 dice and took their average and repeated that process over and over again. Right? So now this would no longer be uniform on the numbers 1 to 6. Still, the minimum would be 1, right? If you got all 10 ones, the average of 10 ones is 1. And the maximum would still be 6. The average of 10 sixes is still 6. And so the bounds are 1 and 6, but it would not look like a uniform distribution on the numbers between 1 and 6, because you can get all sorts of different numbers, right? You can get numbers between 1 and 2, 2 and 3, and so on. So it has kind of a funny distribution, the distribution of averages of 10 die rolls. So imagine if you were to do that, roll your 10 dice and take the average, and do that over and over again so that you got, say, 10,000 averages of 10 die rolls, right? And you wanted to know what was the variance of that distribution. Well, it seems kind of like a hard calculation. First, you'd have to figure out what's the distribution of the average of 10 die rolls, which seems kind of like a hard distribution. And we'll actually later on discuss that that's maybe even a little bit easier to calculate than you might have thought. But this calculation says you don't even have to worry about that. We know that the variance of the distribution of individual die rolls is 2.92. So the variance of the distribution of averages of 10 die rolls is 2.92 divided by 10. So it would be 0.292. And so we could run this experiment in R, for example, where we rolled a digital die thousands of times and took the variance of 1,000 die rolls, and you'd find that's about 2.92. And then we could also do this experiment where we rolled 10 dice, took the average, and repeated that process over and over again and got 10,000 averages of 10 die rolls. And you would find that the variance of those averages was about 0.292. Very interesting. And so it's a very simple formula. And so let's belabor this point on the next slide. So when the x's are independent with a common variance, the variance of x bar is sigma squared over n. The quantity sigma over n, the square root of this, is so important, we give it a name and we call it the standard error of the sample mean. Basically, a standard error is nothing other than the standard deviation of a statistic. In this case, the statistic is the sample mean, but you might have a standard error of another statistic. For example, the median then itself has a standard error. It's maybe a little hard to calculate, but nonetheless, it has a standard error. So what is the standard error? The standard error of a sample mean is the standard deviation of the distribution of the sample mean. So sigma, the standard deviation, talks about how variable the population is. Sigma over square root n talks about how variable the population of averages of size n from that population are. So two different statements, and they estimate different things. So for example, if the x's are IQ measurements, sigma talks about how variable IQs are. Sigma over square root 10, say, then talks about how variable averages of 10 IQs are. Okay, so they're different. They're obviously related, but they're different concepts. And it's easy to confuse the two. And an easy way to remember this, by the way, is that the sample mean has to be less variable than a single observation. Therefore, its standard deviation is divided by square root n. So that also gives you a sense of how the rate at which standard deviations decline as you collect more data. So since we've talked about the sample variance a lot, why don't we actually define it? So the sample variance is that entity that we use data to estimate the population variance. So recall the population variance was the expected value or the average, the expected deviation of a random variable around its population mean, right? So what is the sample variance? Well, it's the average deviation of the sample values around the sample mean. So it's quite convenient. Now notice it's not exactly the average. We divide by n minus 1 instead of n, which is a little annoying, but we do it. So imagine for the time being that this is an n in the denominator, not an n minus 1. Then the sample variance is nothing other than the average squared deviation of the observations around the sample mean. So the sample variance is an estimator of the population variance, sigma squared. And just like the population variance has a shortcut formula, the sample variance has a shortcut formula. Summation xi minus x bar squared, the top of the variance calculation, is summation xi squared minus nx bar squared. So if someone gives you the sum of the squared observations in the sample mean, then you can calculate the sample variance really quickly. So why do we divide by n minus 1 instead of n? And again, for large samples, it's irrelevant, right? The factor n minus 1 over n is small, so you're going to get about the same answer either way. But for small samples, it can make a difference. So why do we choose to divide by n minus 1? So recall we have this property, unbiasedness. And the property of unbiasedness meant that the statistic, its expected value, equaled the quantity that it's estimating. So just to remind you, the sample variance is a function of our observed data. It's a function of our random variables, right? So itself is a statistic. So it is a random variable itself. So it has a distribution. And so that distribution has a variance, and that distribution has a mean, okay? That's what we're going to talk about right now, is that the mean of that distribution turns out to be sigma squared if you happen to do the calculation where you divide by n minus 1. So I'm going to show it by showing that the expected value of the numerator of this statistic is equal to n minus 1 times sigma squared. That's the same thing as showing that the sample variance is unbiased, because then you just divide both sides of this equation by n minus 1 and you get the result. So let's do that. Just to say it again because it's important, what are we doing? Remember, the sample variance is itself a random variable. That random variable has a distribution. That distribution has a population mean. And we want to say that that population mean is in fact sigma squared. Okay. So expect a value of the numerator part of the sample variance calculation, the sum of the squared deviations around the sample mean. If we use the shortcut formula, that's sum of the expected value of the xi squared minus expected value of x bar squared. Okay. And now let's use a really kind of nifty fact. Recall for the variance, the shortcut variance formula was defined as the expected value of a random variable squared minus the expected value of the random variable quantity squared. Well, we can shift that formula around to get it to say that the expected value of a random variable squared is the variance plus the mean squared. And that's what we do right here. So the expected value of xi squared is variance xi plus mu squared. Okay? And then the same thing is true, of course, for the mean, because the mean itself is just another random variable. So the expected value of x bar squared is variance x bar plus mu squared. And then we have this n out front. Okay. And so the variance of xi is sigma squared. So we wind up with some sigma squared plus mu squared, which is a constant. So we wind up with n of those. And then variance of x bar, we just derived a little bit ago as being sigma squared over n. So we get n times sigma squared over n plus mu squared. And just collect terms now and you get n minus 1 sigma squared. So this is a really interesting fact. So this says that the expected value of the variance is in fact the quantity it's trying to estimate if in fact you divide by n minus 1 instead of n, and that's why we divide by n minus 1. Another way to kind of think about this is that, well, you know, we don't know the population mean, mu, and if we knew it, instead of plugging x bar into the sample variance formula, we would plug mu into the sample variance. We would calculate the deviations of the observed observations around the population mean rather than the deviations around the sample mean. And so the idea is that we will sort of lose a degree of freedom by plugging x bar, its sample analog, instead of plugging in that mu. So that's the kind of heuristic behind why you divide by n minus 1. It's an interesting fact, though. It's not 100% clear that you do want to divide by n minus 1. It's sort of every introductory statistics textbook divides by n minus 1. But there's this interesting phenomenon called the bias variance trade-off. And in this case, we've obtained an unbiased estimator by dividing by n minus 1 instead of n. But what if we had divided by n? Maybe as an exercise, I could ask you to calculate the expected value of the sample variance if it was calculated with n in the denominator instead of n minus 1. Okay, so basically, what's the expected value of n minus 1 over n times s squared? And you can calculate that very easily. It's not sigma squared, but it's quite close to it. So it's a biased estimator, but the other thing I would ask is, well, which of the two estimators, the estimator s squared calculated with n minus 1 in the denominator, or the calculation of the variance with an n in the denominator, has a lower variance? And what do I mean by that? Remember, the sample variance is a random variable. It has a distribution. That distribution has a variance. And the question is, which of the two calculations, dividing by n or dividing by n minus 1, results in a smaller variance of that distribution? And what does that mean? That would mean how precise your estimate of the variance is. I'll give you the punchline. The sample variance divided by n has a slightly lower variance than the sample variance divided by n minus 1. So it's another kind of classic bias variance trade-off. In this case, we divide by n minus 1 because we want unbiasedness, but then we wind up with slightly greater variance. If we divide by n, we wind up with a slightly lower variance of our sample variance, but it's slightly biased. I know extremely well-established statisticians that say they would prefer to have the lower variance, but pretty much every introductory statistics textbook divides by n minus 1. It's kind of an interesting discussion. You know, one of the confusions that always comes up seems quite simple. We divide by an n minus 1 when we calculate the sample variance. People have a tendency to confuse that with the n that we divided by when we talked about the standard error of the mean. And so let's just try to avoid some of this confusion. Suppose you have a bunch of observations that you're willing to model as IID with population mean mu and population variance sigma squared. Then the sample variance s squared estimates the population variance sigma squared. The calculation of s squared involves dividing by n minus 1, and we just spent forever talking about the difference between dividing by n and dividing by n minus 1. Then the standard error of the mean is sigma over square root n. So s over square root n will estimate the standard error of the mean. So we've already divided s squared by n minus 1, then we square root it, and then we divide by an additional square root of n if we want the standard error of the mean. Okay, and I'm just trying to avoid some confusion because people seem to get confused by that. So I guess if you wanted to attach a label to the quantity s over square root n, it's the sample standard error of the mean. What does it estimate? It estimates the population standard error of the mean, sigma over square root n. Let's tie this down with some actual numbers. So I was involved in a study where there was a lot of organo-lead workers. In this case, I took a subset of 495 of them. And the total brain volume for the lead workers, they were interested in studying how their exposure to lead in their job changed their brain volume. So TBV stands for total brain volume. In this case is a measure of the brain volume on the inside of the skull. So all the measures are in cubic centimeters. So the mean in this case is 1,151. If we're willing to assume these organo-lead workers are, say, an IID draw of organo-lead workers from a population that we're interested in, then the sample mean 1,151 would be an estimate of that population mean. The sum of the squared observations works out to be this number. So the standard deviation, the sample standard deviation works out to be that number minus 495 times the sample mean squared, all divided by 494, that minus 1 in the denominator. Square root the whole thing, you wind up with 112. So what does 112 describe? 112 describes the variance of the population of brain volumes of organo-lead workers. Okay, so it's a direct estimate of my sample variation, right? And then it's an attempt to estimate, if you view my data as a sample from a population of organo-lead workers, it attempts to then estimate the population standard deviation of that distribution. So we could, for example, use Chebyshev's rule to interpret what the combination of the mean and the standard deviation say about brain volumes of lead workers in the population. Now, what does, if I take this 112.6 and divide it by square root 495 give me? It gives me 5 as the numerical result. But what does that 5 actually estimate or do for us? Well, the 5 is no longer talking about the variation in total brain volumes in the population. It's talking about the variation in averages of 495 organo-lead workers. So the idea is, if we're willing to model our 495 organo-lead workers as a draw from a population of organo-lead workers, then 5 estimates the distribution of averages of 495 draws of organo-lead workers from that population. It talks about how variable averages of 495 brain volumes are. The 112 talks about how variable brain volumes are. Okay, so let me just repeat that because it's very important. The 112 talks about how variable brain volumes are of organo-lead workers in the population, and it directly talks about it in the sample, but it's an estimate of our population variance. And the 5 is an estimate of the population standard deviation of averages of 495 organo-lead workers. So I hope you're getting a sense of what these numbers are trying to calculate. So there's several concepts that are being used here. First, we have our observed data, right? And these quantities, the sample mean, sample standard deviation, and standard error, tell us things about our observed data, right? And then there's the assumptions, for example, that they're IID, that help to try and connect it to a population so that we can maybe generalize the results from this data to a population of organo-lead workers. Say, for example, if you wanted to use this data to inform policy, and then these numbers would then be estimates of these population quantities, and then dividing by the square root 495 is telling us things about how variable this mean is relative to the variability in the population. Okay, so that's the concepts we're trying to use, and we'll formalize these much more when we actually do things like generate confidence intervals and perform hypothesis tests and these things. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 5 on Conditional Probability. So in this lecture, we're going to talk about conditional probabilities and then the associated density functions for calculating conditional probabilities, basically just called conditional densities, and we'll talk about conditional mass functions for discrete random variables. We'll talk about Bayes' rule and then briefly talk about an example of Bayes' rule using diagnostic tests, and then we'll talk a little bit about so-called diagnostic likelihood ratios. So let me give you some brief motivation for conditional probabilities. I think we kind of internally do these things pretty easily. So imagine rolling a standard die, and we're assuming that the probability of each face is 1/6. Suppose you didn't know the outcome of the die, but someone were to give you the information that the die roll was odd. So it had to be a 1, a 3, or a 5. A 2 or a 4 or a 6 is not possible given this extra information. Then conditional on this new information, everyone would probably agree that the probability is now 1/3. And all we're going to do in the next couple of slides is mathematically develop these ideas a little bit more completely. So let's develop the notion of conditional probability just generically talking about events. So let's let B be any event such that the probability of B is greater than 0. This condition is kind of important because it doesn't make any sense to condition on the probability of an event occurring when that event cannot occur. So it doesn't make any sense to talk about the probability of A given B occurred if the probability that B occurred is exactly 0. Just to put this in words, it makes no sense to talk about the probability that a coin is head given that the coin is on its side if you're not going to allow for the possibility for the coin to land on its side. So the definition of a conditional probability of an event is the probability of the event A occurring given that the event B has occurred is the probability of the intersection divided by the probability of B. Now, notice if A and B are independent, then the probability of A given B, well, the numerator component, the intersection, A intersect B, factors into the product of the two probabilities, probability of A times the probability of B. The probability of B cancels out in the numerator and denominator, and you're left with the probability of A. So this actually makes a lot of sense that if the events A and B are independent, then the probability of A, given that B has occurred, is simply the probability of A without knowledge of whether or not B has occurred. That is, the information about whether B has occurred is irrelevant to the calculation of the probability of A. This matches our intuition as to what independence means, and it's nice that the mathematics works out that way. In fact, in some probability texts, this is their definition of independence, as opposed to the definition that we gave earlier. So let's just work through the formula given our example with the die roll just to convince ourselves that it's actually working. We want the probability of a 1 given that the die roll is odd. So in this case, B is a 1, 3, or a 5. A is just a 1. So the probability of A given that B has occurred is the probability of the intersection. And in this case, A is the set containing 1, B is the set containing 1, 3, and 5. So A is a subset of B, so when you intersect the two, you just get A by itself. So it works out to be the probability of A divided by the probability of B. The probability of A by itself is 1/6. The probability of B is 3/6, and we get 1/3, exactly the answer that our intuition told us. Okay, so that ends our very brief discussion of basic conditional probability calculations using the standard events and generic discussion of probability. Next, we're going to talk about conditional densities, which will be our mathematical formulation for conditional probabilities for continuous random variables. So welcome back, troops. we're going to be talking now about conditional densities now that we know a little bit more about conditional probabilities. So conditional densities or mass functions are exactly densities and mass functions that govern the behavior of a random variable conditioned on the value the other random variable or another random variable took a different value. So just to tie this down a little bit, let's let f of x comma y be a bivariate density or mass function, and it governs the probabilistic behavior of the random variables capital X and capital Y. Now, I'm going to abuse notation slightly and let the letter f be the joint density and f of x be the marginal density associated with x, and f of y be the marginal density or mass function associated with y. And it's probably not the best notation to use f for the joint density, f for the two marginals when they are all referring to different things. So, just keep in mind that the arguments are kind of differentiating what I'm talking about here. This is exactly very sloppy notation, but I'm using it anyway. So just to remind you, the marginal density f of y is the joint density f of x comma y integrated over x, or if the random variables happen to be discrete, then f of y is the joint mass function f of x comma y summed over x. So in other words, if you want to know, regardless of what happened with respect to x, what is the probability behavior of the random variable y, you have to integrate over the random variable x, over all the potential values you could take with what probabilities, and then you get the marginal behavior of the random variable y. In similar, you could get the marginal for x. F of x is the integral of the joint density over y, or the sum of the joint mass function over y. Well, the conditional density is exactly, say, for example, f of x given y is the joint density f of x comma y, or mass function, divided by the marginal f of y. It follows actually directly from the definition of conditional probabilities that we just gave you a couple slides ago, and that we sort of all agreed on made a lot of sense. Let me elaborate on that point. It's in fact in the discrete case where x can only take so many values, 1, 2, 3, 4, then this definition of conditional probability is exactly the definition that we used from events, where A is the event that x equals x and B is the event that y equals y. So there's no confusion. It exactly agrees with our definition of conditional probability. The continuous one is a little bit harder to kind of motivate why this is the definition. The event that x takes on a specific value or y takes on a specific value has probability 0 for continuous random variables. And so that kind of fails our basic premise from conditional probability associated with events, that the probability of the event that we're conditioning on has to have probability greater than 0. Now note, we're talking not about conditional probabilities, we're talking about the construction of conditional densities which govern the behavior of conditional probabilities. So we haven't violated that rule from earlier, but it still kind of seems to break the spirit of the rule. And how do we get at this idea? How can we have a meaningful definition of the probabilistic behavior of a random variable given that another random variable takes on a specific value? Well, here's the motivation that I like. So imagine if you define the event A that the random variable x is less than or equal to a specific value, little x, and the event B is that the random variable y lies in this interval from y to y plus some small amount, say epsilon. Then now A and B are events that have positive probability, and we can apply our standard definition of conditional probability to talk about the probability of the event A given that the event B has occurred, right? That would just follow from our standard definition. So actually, let's formulate this. So the probability of A given B is the probability of x being less than or equal to little x, given that y is in the set y to y plus epsilon. And then now in this case, nothing has probability 0. We can just directly apply the probabilistic formula. And I don't think this is terribly important for this class. I just wanted this argument to be here for those who want to see it. But then you can just follow through the arithmetic or not the calculus here and get that basically this construction yields the conditional distribution function associated with the x given that y equals y as we let epsilon get smaller and smaller. So as the conditioning event gets closer and closer to y conditioning on it being the specific value y, we limit to a conditional distribution function associated with x. And then remember that density functions are derivatives of distribution functions. So if we just take the derivative of this, then we get the conditional density function. So we can see right here that if we differentiate this conditional distribution function, we get exactly the definition of the conditional density that we gave you before, f of x comma y divided by f of y. So if you're interested in this at this level, then you can go through those arguments carefully. And to be fair, these only cover the definition in the continuous case when we have differentiable distribution functions, but this is more than enough for our case. If you're interested in it at a deeper level even than this, where you have mixed continuous and discrete densities, then you can take an advanced probability course somewhere. But for our purposes, this is enough. And so just to summarize, we have the conditional probability definition associated with events that kind of governs all of our thinking about conditional probabilities, and that's the probability of A given B is the probability of A intersect B divided by the probability of B. And then in the event that you're talking about random variables, where we want to talk about the probability of a random variable x, given that the random variable y is taken on a specific value, it's the joint density or mass function divided by the marginal. And it has a nice sort of parallel with the probability associated with events. And here we've gone through the arguments to show how we get from these statements about events to this definition for mass functions and density functions. So conditional densities actually have a very nice geometric interpretation. So if you have a joint density, f of x comma y, that's a surface. F yields the z value, and xy is the plane. So f of x comma y is a joint density, is a surface, and its volume under the surface has to be 1 for it to be a joint density. Well, what does it mean to get the conditional density of x given that y takes a particular value? The event that y takes a particular value, that's sort of like a plane at the point, let's say y is 5, at the point y equals 5, that's a plane. And that plane slices through this surface and yields a function. That function is just f of x comma y evaluated at the point 5, f of x comma 5. Okay, so we have this surface, we have this plane, the y equal 5 plane that cuts through the surface, and then we have the function that is on that plane at f of x comma 5. And that is exactly the conditional density, with the exception of now it doesn't integrate to 1. So we have to normalize it by something that integrates to 1. Well, that's exactly what we divide by there, f of 5. Let's go through a specific example. We have f of x comma y equals y e to the negative xy minus y for x and y both greater than 0. Now the marginal density associated with y, let's just perform the integral. We integrate from 0 to infinity of the joint density function over x because we want the marginal associated with y, and you can perform the integral. It works out to be e to the minus y. And then our conditional density then, f of x given y, is the joint density f of x comma y divided by f of y. So just churn through the calculations and you get y e to the negative x times y. And so if you wanted to know what's the conditional density, the governing behavior of the random variable x, given that y is, say, 3, then that density would be 3e to the negative x times 3. Okay, so you just plug in y equal 3. So now this function, if you plug in any possible value of y, this function will now give you the associated density function for the random variable x, conditioning on the information that y takes on that specific value. Okay, welcome back, troops. This is Mathematical Biostatistics Bootcamp Lecture 5, and we're going to start talking about Bayes' rule. Bayes' rule is one of the most famous results in statistics. It comes from I believe, Presbyterian minister named Thomas Bayes, who wrote down the rule. I believe it was published posthumously much later, and it's an astoundingly simple rule that has incredible power to it. And the idea is basically, how can you relate conditional probabilities of the form A given B to probabilities of the form B given A? So you reverse the arguments. It's very important, right? It's saying, how can I talk about A given that B has occurred when I only know things about the distribution of B given that A has occurred? It's a very important thing. And of course, you can't do that without a little bit of extra information. And we'll talk about it specifically where that extra information comes from. I wanted to give the mathematical, the probability, density, and mass function version of it first. And then we'll talk about the kind of classical treatment with events. But let's let f of x given y be a conditional density or mass function for x given that y has occurred and has taken the value y, and f of y being the marginal density for y. Then if y is continuous, then Bayes' rule basically says that f of y given x is f of x given y times f of y divided by f of x given t times f of t dt. And notice that what we needed to know to do this calculation of f of y given x is f of x given y, and then this extra argument, f of y by itself. And so the idea of Bayes' rules is sort of flipping the arguments. And then if y is discrete, f of y given x is f of x given y times f of y divided by the sum over t of f of x given t times f of t. Bayes' rule, again, relates f of y given x to f of x given y, and then the marginal density f of y. And if we apply this to events, it takes a kind of familiar form that you may have run into before. So a special case of this relationship basically works out to be probability of b given a is the probability of a given b times the probability of b, divided by probability of A given B times the probability of B plus the probability of A given B complement times the probability of B complement. And you could do this exactly from our previous formula. Let X be a discrete random variable, that's the indicator of whether A has occurred, Y be an indicator that the event B has occurred, then plug into the discrete version of Bayes' rule. That would be a simple proof if you were willing to stipulate the previous page. You can also prove it very easily just by working with the rules of probability and sets. So this numerator is probability of A intersect B. This denominator is probability of A intersect B plus probability of A intersect B complement. So the numerator works out to be probability of A intersect B. The denominator works out to be the probability of A. So that's exactly the conditional probability B given A. So it's quite easy to prove, but I just wanted to, by discussing this, indicate to you that there's no real distinction between the way we're discussing it in terms of continuous densities or discrete joint mass functions and this kind of traditional method of treatment using probabilities and events. So that's a very brief treatment of how you can use Bayes' rule with densities and with mass functions. We'll go through several examples next time, but one of the most common and biggest examples that we're going to talk about is associated with diagnostic testing, and that's what we'll do next. Okay, welcome back, troops. This is Lecture 5, Mathematical Biostatistics Bootcamp, and now we're going to be talking about diagnostic test. So a particular application of Bayes' rule, its use in so-called diagnostic testing. And we'll talk a little bit about the kind of traditional treatment of this, but we'll also delve a little bit into the intricacies of these calculations. They're a little bit more complex than people usually give them credit for. But the simple treatment is as follows. So let's let plus and minus be the events that a diagnostic test is either positive or negative, respectively. So plus being positive, of course, and minus being negative. And then let's let D and D complement be the event that a subject of the test does or does not have the disease, respectively. We can make a definition. The sensitivity of the test is the probability that the test is positive given that the subject actually has the disease. Probability of plus given D. That's the sensitivity. The specificity is the probability that the test is negative given that the subject does not have the disease. That is the probability of a minus given D complement. So let's give a couple more definitions. So the positive predictive value is often what a subject would want to know. That is the probability that a person has the disease given a positive test result. And the negative predictive value is another thing that people would very much so like to know in the result of a negative test, is the probability that they do not have the disease given that the test is actually negative. And then we might declare the prevalence of the disease to be just the marginal probability of disease. Okay, last set of definitions. The diagnostic likelihood ratio of a positive test, and let's call it DLR plus, is the probability of the test being positive given that the person has the disease divided by the probability the test is positive given that the person does not have the disease, which is exactly sensitivity divided by 1 minus specificity. The diagnostic likelihood ratio of a negative test, labeled DLR minus, you can read the formula there, probability of negative test given the disease divided by the probability of a negative test given disease complement, which is 1 minus the sensitivity divided by the specificity. Okay, we'll go through in detail why all these things are useful through a specific example. And then we'll come back and talk a little bit about maybe why these calculations are a little bit more subtle than people often discuss. Okay, so a study comparing the efficacy of HIV tests reports on an experiment which concluded that the antibody tests have a sensitivity of about 99.7 and a specificity of about 98.5. And I got these numbers from a website, but am fudging them a little bit because it's kind of more important to just perform the calculations than to talk about specific tests and to evaluate them. So imagine these numbers are accurate with respect to a specific test. And by the way, why Bayes' rule is kind of convenient in these sorts of settings, it's in principle a little bit easier to get these numbers, sensitivity and specificity, by virtue of the fact that you would just take blood samples for a set of people that you know are HIV positive and see the proportion of them that the test comes up positive, and you take a group of people that you know to be HIV negative and see the proportion that have a negative test result. And you could get these numbers or get estimates of these numbers. And of course, that's a very simplistic treatment of how you actually would get a sensitivity and specificity. There's lots of issues like how do you actually know if you're working in an area where the tests are difficult, how do you actually know whether a person has the disease or not is in question. Or if you wait so long to where the disease is very clinically relevant, then are you evaluating the test in a stage of the disease where it's not interesting for when you would be applying the disease? There's a lot of issues in development of test and evaluation of test and constructing their validity that we are going to completely gloss over in this discussion. So for our discussion, let's just assume these numbers are right, that they work well. And then also let's assume that there's a 0.1% prevalence of HIV in the population, and a subject receives a positive test result. Well, what is the probability that this subject has HIV? Well, mathematically, what we want is the probability of disease given a positive test result, given the sensitivity, the probability of a positive test result given disease, which is 0.997. The specificity, probability of a negative test result given disease complement, 0.985, and the prevalence, probability of D, 0.001. So using Bayes' formula, we can just plug in. We get 0.997 times 0.001 divided by 0.997 times 0.001 plus 0.015 times 0.999. This works out to be about 6%. So it works out that a positive test result only suggests a 6% probability that the subject has the disease. Or in other words, the positive predictive value is 6% for this test. Now, you might wonder, that seems awfully low. Why is this the case? That, if I take a collection of blood samples that I know to be positive and I apply the test, it's 99% are accurately labeled as positive. How is this so low? And if I take a bunch of blood samples that I know to be negative and I apply the test, I get a very high percentage of negative tests. How is this so low? Well, it's basically the low positive predictive value is due to the low prevalence of disease and the somewhat modest specificity. It's not so bad. And in this case, this is what Bayes' rule actually does for us. You start out with prior information, basically, a very low probability of thinking that this person has the disease. Then you update it with the information of the positive test result, and that gets codified by updating it with the sensitivity and the specificity associated with the test, and that informs the positive predictive value, and you get something that's much higher than the prior probability of disease, the prevalence, but still isn't terribly high because you started with such a low prior. And that's how Bayes' rule works. So, for example, here the prevalence we're talking about is some, say, national prevalence in the US. But imagine if you knew that the subject was an intravenous drug user and routinely had intercourse with an HIV-infected partner. Well, your prior that this person has HIV would be much, much higher than the low prevalence that we cited here. I don't know what the prevalence is among a population like this, but suffice it to say that it's much higher. And then your positive predictive value would be similarly higher, which is kind of an interesting discussion. Imagine if you were a clinician of some sort and you were working with a patient and you saw their positive test result and you'd say, yeah, it's a positive test result, but maybe we should run another test or do some other things to evaluate your condition. The positive predictive value associated with this test is only 6%. Well, then in the same interview, it came out that the person was an intravenous drug user and routinely had intercourse with an HIV-infected partner. Well, then the clinician would say, oh, well, the test is very conclusive. We need to start you on antiretrovirals or something like that. So from the patient's perspective, that might seem a little odd that this external information is what kind of changed the conclusion. The test value didn't change. Just in the discussion with the clinician, only their prevalence changed. And only the prevalence in the calculation changed. So from the patient's perspective, this might seem a little weird. But again, the mathematics are exactly accurate. So there's a question as to what is the component of the calculation that does not change regardless of the prevalence? And that's ultimately what the diagnostic likelihood ratios are giving you. So take, for example, here, the probability of having disease given a positive test result. We use Bayes' rule, and you see Bayes' formula on the right, and the probability of not having disease given the positive test result. And then we see Bayes' rule on the right for that setting. If you take these two equations and divide them, you get the following very, very nifty formula. The probability of disease given a positive test result divided by the probability of not having disease given a positive test result is equal to the diagnostic likelihood ratio times the probability of disease divided by the probability of disease complement. So just to simplify this formula a little bit, we need to talk about odds. So odds has a formal mathematical definition. If you say the odds of something is 2 to 1, that's a ratio of 2, right? 2 divided by 1. That has an implied probability of 2/3 that the event occurs and then 1/3 that the event does not occur. So the way you go from probabilities to odds is you take the probability and divide it by 1 minus the probability. So in this case, take 2/3 and divide it by 1/3, you get 2, you get the odds. To go from odds back to a probability, you take the odds and then divide by 1 plus the odds. In this case, we had 2, take 2, divide it by 2 plus 1 or 3, you get the probability, 2/3, and then 1 minus the probability is 1/3. So if someone were to say the odds are 3 to 1, then that means the probability is 3/4 and the probability of the event not occurring is 1/4. If the odds are 4 to 1, that means the probability that the event occurs is 4/5, and the event that it doesn't occur is 1/5. Okay, so hopefully you get the picture. Work out some examples on pen and paper. Just to let you know, if you go to horse racing in the US, it's always the case that they give you the odds against something happening instead of the odds for it. So they're defining odds in terms of the odds against rather than the odds for. So anyway, that's just a small thing if you happen to go gambling this weekend. Okay, so in this formula, it has a very specific form then. The post-test odds of disease, probability of D given positive test result divided by the probability of D complement given a positive test result. So the post-test odds of D is equal to the diagnostic likelihood ratio times P of D divided by P of D complement, which is the pre-test odds of disease. So we have some inkling of whether or not a person has the disease just based on prior knowledge before we administer the test. We obtain the test, and that yields data. Well, the DLR plus, because it's a positive test, is the factor by which we multiply our pre-test odds to obtain our post-test odds. So in the discussion I was talking about earlier, whether the person is an intravenous drug user and has sex with an HIV positive partner is irrelevant to the DLR, right? The DLR says, for example, that your odds of disease has increased by X amount by virtue of having a positive test, regardless of your prevalence, right? Whereas the positive and negative predictive value inherently factor in the prevalence. Okay, so that's the reason why you get drastically different numbers for these things, because they're interpreted in different ways. So I also want to talk a little bit about this idea of Bayesian philosophy, and regardless of whether you're a Bayesian statistician, Bayesian philosophy is quite appealing. And this formula that the post-test odds is equal to the likelihood ratio, which is the probability model and the data combined times the pre-test odds, it's a very appealing sort of mirror to how we think the scientific process should work. You start out with an a priori kind of weighting of a set of hypotheses. In this case, it's sort of a hypothesis and its complement. And you collect data, and that data informs your belief. And then now you have a post-test odds of disease. And then suppose you were to actually run another test. Well, the likely starting point for your new prior would be the post-test odds, or the posterior, after your first test. And it turns out it all works out just fine, that if you take two tests and they're both positive, your diagnostic likelihood ratios just multiply. But in terms of Bayesian think, it's the idea that you have a prior, you update it with data, you get a posterior. Now that posterior is your prior. It also codifies a lot of scientific discussion. If your prior is absolutely fixed at a specific point, then the data is irrelevant. Nothing's going to move you off of it. A lot of politics is that way, of course. So I think if you think about political discussions in terms of Bayes' rule, it's really not very surprising at all. So at any rate, let's just go through our HIV example in more detail. So suppose someone has a positive HIV test. The DLR plus is 0.997 divided by 1 minus 0.985, which works out to be about 66. So that means that regardless of your prior behavior in the population you're coming from, the virtue of this test is that now you have 66 times the pre-test odds of having the disease. Or you could say, or equivalently, the hypothesis of disease is 66 times more likely, supported by the data, than the hypothesis of no disease. And then let's just go through another example. Suppose that the subject has a negative test result. Then the DLR minus is 1 minus 0.997 divided by 0.985, which works out to be about 0.003. So the DLR minus is telling you about your odds of disease and the result of a negative test result. So your factor that you're multiplying by is 0.003. So now your post-test odds is 0.3% of your pre-test odds given the negative test. I wanted to conclude with a discussion on kind of a very deep point associated with these calculations. These calculations are done, and there tends to be very little discussion of how much sense they actually make. So if you are, in fact, a Bayesian, then none of this has any problem whatsoever. Assigning a probability to the event that an individual has a disease offers no complications in Bayesian thinking. A probability to a Bayesian is not as much of an objective thing. It's a quantification of belief. So you have your prior belief, you have the component that is independent of your prior in the diagnostic likelihood ratio, and then you have your posterior belief, and that if you're consistent with respect to Bayes' rule, then your posterior belief has been multiplied appropriately by the diagnostic likelihood ratio vis-a-vis the data. And then you wind up with a very consistent picture. If you're a frequentist, then it's a little bit harder to think about these things, because the standard frequentist sort of boilerplate line is that the person either has the disease or they don't. There's no probability associated with it. And if you're not being a Bayesian and that probability, it's not a mathematical codification of a belief, then it takes on a different character. You can still interpret the calculations, though, I would contend. Maybe some hardcore Bayesians would still find issue with how I'm proposing to interpret it as a frequentist. But still, I would say you're not talking about the probability that this specific subject has the disease in the frequentist sense, because they either have the disease or they don't. There's no probability left. But what you're talking about is this idea of potential fictitious repetitions of this experiment, and using the probability as a contextual entity to evaluate this person's probability of disease as context. It's probability if lots of people exactly like this person took this test, what would be the long run percentage of positive test results that we got. That sort of thinking is what I'm proposing is the way you could shoehorn these calculations into frequentist thought. And I think it's probably fine. Either way, churn through the mathematics in the same exact manner, but the interpretation is quite dicey. And I think it's probably fair to say that most statistics texts kind of gloss over some of these finer details because, admittedly, they're quite difficult to think about. The other thing I wanted to briefly touch on is the nature of actually collecting data to inform these calculations. And I touched on this a little bit before, but it's very difficult to know conclusively whether or not someone has a disease when you're developing a test, usually. And it's very difficult to develop things like actual real prevalence estimates that are relevant to the person that you're talking about with respect to the disease. It's also very difficult to have whatever samples you're using to develop sensitivity and specificity be indicative of the population of samples that the test will be applied to in actual clinical practice. So in the process of saying this, even though these calculations are very simple and they actually highlight Bayes' rule quite nicely. Actually, that's the primary point of the lecture, is that they highlight Bayes' rule, and we've churned through some Bayes' rules calculations. But I don't want to give you the sense that this is all there is to the world of diagnostic testing and validation, which is a very, very deep subject and quite a fun subject, I might add, but involves quite a bit more than Bayes' rule. So thanks for attending the lecture. We'll see you next time. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 6 on Likelihood. In this lecture, we're going to define what a likelihood is, which is a mathematical construct that is used to relate data to a population. We're going to talk about how we interpret likelihoods, talk about plotting them, and then talk about maximum likelihood, which is a way of using likelihoods to create estimates. And then we'll talk about likelihood ratios and how to interpret them. Likelihoods arise from a probability distribution, and a probability distribution is what we're going to use to connect our data to a population. So the idea behind this, and a lot, but not all of statistics follows this rubric, is to assume that the data come from a family of distributions, and those distributions are indexed by an unknown parameter that represents a useful summary of the distribution. To give you an example, imagine if you assume that your data comes from a normal distribution, so-called Gaussian distribution, so a bell-shaped curve, To completely characterize a bell-shaped curve, all you need is its mean and its variance. So the probability distribution, the Gaussian distribution, or the bell-shaped curve, has two unknown parameters, the mean and the variance. And then the goal is to use the data to infer the mean and the variance. And the idea is that the mean and the variance from the Gaussian distribution are unknown population parameters, because the Gaussian distribution is our model for the population, and the data, our sample parameters, is what we're going to use to estimate the unknown parameters. So the nice part about this approach, other than quite a bit of other directions in statistics, is that the sample mean, the sample variance, these are all estimators. With a population model, you actually have estimands. The sample mean is actually estimating something. It's not just a statement about the data. It's an estimate of the population. And that's what we're going to be talking about today. We're going to be talking about a particular way of approaching estimation and summarizing evidence in the data when you assume a probability distribution using likelihood. Likelihood is a mathematical function, has a particular definition, and it's just the joint density of the data evaluated as a function of the parameters with the data fixed, and we'll go through an example. Before we go through our example, I want to talk about what it is the likelihoods are attempting to accomplish and how we might interpret them. So I'm going to put forward a particular theory of how likelihoods can be interpreted and how they can be used, and I guess I should stipulate that maybe not everyone agrees with this theory. But the theory I'm going to put forward is that ratios of likelihood values measure relative evidence of one value of an unknown parameter relative to another. So if you evaluate the likelihood with the parameter at a specific value, you get a number, and then you take the ratio with the likelihood evaluated at a different number. That ratio, if it's bigger than 1, it's supporting the hypothesized value of the parameter in the numerator. If it's less than 1, it's supporting the hypothesized value of the parameter in the denominator. So this is a somewhat controversial interpretation of likelihoods, but it's the one I'm going to put forward. The second point is similarly controversial, though there is a mathematically correct proof that at least it motivates to. It actually doesn't prove to, but the statement I'm making in 2 is that given a statistical model, so given a probability model and observed data, there is a theorem called the likelihood principle that says all of the relevant information contained in the data regarding the unknown parameter is contained in the likelihood. Now, the likelihood principle has a mathematically correct proof, but not everyone technically agrees on its applicability and its interpretation. But nonetheless, I'm going to put this forward as a way that in this class we're going to interpret likelihood, so that once you collect the data, if you assume a statistical model, then the likelihood is going to contain all of the relevant information. It's interesting that this point 2 has very far-reaching consequences to the field of statistics, if you believe it. Things like p-values and much of hypothesis testing and other staples of statistics become questionable if you take point 2 as being true. So, for today's lecture, we're going to take it as being true, and we'll talk a little bit about maybe some of the controversy associated with it. Probably from a much more practical point of view is point 3, which says, and we already know this, but let's state it in the term of likelihood. So when we have a bunch of independent data points, xi, then the joint density is the product of the individual densities. So equivalently, as we said that the likelihood is nothing other than the density evaluated as a function of the parameter, it's also true that their likelihoods multiply. So independence makes things multiply. It makes the joint density multiply. It makes the likelihood multiply. So I summarize that here in the statement that is the likelihood of the parameters given all of the x's is simply the product of the individual likelihoods. The last point I'd like to make on this slide is that, especially points 1 and 2, the likelihood assumes these interpretations of likelihoods. One negative aspect of them is that you have to actually have the statistical model specified correctly. And of course, we don't know the statistical model really ever. If we assume that our data is Gaussian, that's an assumption. It's not generally something we know. Maybe in some rare cases, like in, for example, radioactive decay, there's some physical theory that suggests that that data is Poisson, for example. But in most cases, we don't actually know that the statistical family is a correct representation of the mechanism that would generate data if we were to draw from the population. So I think the way in which people still rationalize using likelihood-based inference in these cases is that they say, well, given that we assume this is the statistical model, then we will adhere to the use of the likelihood to summarizing the evidence in the data. Let's go through a specific example, one of the more important examples, and it's very illustrative, so let's do it. Consider just flipping a coin, but this coin, let's say it's an oddly shaped coin, maybe it's a little bent or something like that, so you don't actually know what's the probability of a head. Let's label that probability of a head as theta, and then recall that the mass function for an individual coin flip is theta to the x, 1 minus theta to the 1 minus x. Here, in this case, the theta has to be between 0 and 1. So if x is 0, it's a tails, and x is 1, it's a head. So if we flip the coin and the result is a head, then the likelihood is simply the mass function with the 1 plugged in, right? So in this case, we get theta to the 1, 1 minus theta to the 1 minus 1, which works out to be theta. So the likelihood function is the line theta, where theta takes values between 0 and 1. And if you accept our law of the likelihood and likelihood principle and interpretations of likelihood that I sort of outlined in the previous page, then this says that consider two hypotheses. The hypothesis that the coin's true success probability is 50%, 0.5, versus the hypothesis that the coin's true success probability is 0.25. In the light of the data, right, the one head that we flipped and obtained, the question is, what is the relative evidence supporting the hypothesis that the coin is fair, 0.5, to the coin is unfair with the specific success probability of 0.25? We would take the likelihood ratio, which is then 0.5 divided by 0.25, which works out to be 2. So if you accept our interpretation of likelihoods, this would say there's twice as much evidence supporting the hypothesis that theta equals 0.5 to the hypothesis that theta equals 0.25. So that's the idea behind using likelihoods for the analysis of data. Now let's just extend this example. So suppose we flip our coin from the previous example, but instead of flipping it just once, we get the sequence 1, 0, 1, 1. I have kind of a funny notation here. I'm going to write script L as the likelihood, and L is a function of theta, but it depends on the data that we actually observe, 1, 0, 1, 1. And so we're assuming our coin flips are independent. And so what happens with likelihoods? Well, we take the product. So here I have the first coin flip, theta to the 1, 1 minus theta to the 1 minus 1. Here I have the second coin flip, theta to the 0, 1 minus theta to the 1 minus 0, and so on. So I take the product of all of those, and you get theta cubed to the 1 minus theta raised to the first power. And that's the likelihood for this particular configuration of ones and zeros from 4 coin flips. Notice, however, that the order of the ones and the zeros doesn't matter. Regardless of the order, as long as we got 3 ones and 1 tail, the likelihood was going to be equivalent. It was going to give you theta to the 3, 1 minus theta to the 1. So that is a property of likelihoods. It's illustrating that if you have a coin, the particular configurations of zeros and ones doesn't matter. All of the relevant information about the parameter theta is contained only in the fact that we got a specific number of heads and a specific number of tails. It doesn't depend on the order whatsoever. And in this case, because we know how many coin flips we have, all we need to know is the specific number of heads. So instead of writing likelihood of theta depending on 1, 0, 1, 1, we might write it as likelihood of theta depending on getting 1 tail and 3 heads, because it's the same thing. The order is irrelevant. This, by the way, raises the idea of so-called sufficiency. In this case, the number of heads and the total coin flips is sufficient for making inferences about theta. You don't need to know the data actually. All you need to know is the total number of heads and the number of coin flips. So often that total number of heads, conditioning on the fact that we know the total number of coin flips, is called a sufficient statistic. It's saying that there's a reduction in the data to make inferences about the parameter. You only need to know a summary of it, a function of it. And in this case, the function that we need to know is the sum total number of heads. So let's do a likelihood calculation again. Let's take the likelihood supporting the coin is fair, that theta is 0.5, and divide it by the likelihood assuming that the coin is unfair, specifically with a 25% chance of heads, and we get a ratio of 5.33. So in other words, there's over 5 times as much evidence supporting the hypothesis that theta is 0.5 over the hypothesis that theta is 0.25. Now, that relative values of likelihoods measure evidence. Well, that's useful, but we're not particularly interested in, say, 0.25. I mean, the 0.5 is kind of interesting because the coin is fair, but, most of the other points, we're not interested in 0.25 any more than we're interested in 0.24 or so on. So we'd like a way to consider likelihood ratios of all values of the parameter theta. And this is just simply a likelihood plot. That simply plots theta by the likelihood value. And remember that likelihoods are really interpreted in terms of relative evidence. So it's the fact that the ratio of the likelihood at 0.5 to the likelihood at 0.25 is 5 is what's saying that we have 5 times as much evidence. So it actually doesn't matter. Constants that don't depend on theta don't matter in the likelihood, right? Because when you take the ratio, if there's a constant that doesn't depend on theta, if it's in the numerator and the denominator, it'll just cancel out. The likelihood in their interpretation should be invariant to constants that are not a function of the parameter. So because of that, the raw absolute value of the likelihood isn't altogether that informative. So we need to pick a rule for kind of normalizing it. And so why don't we just divide it by its maximum value so that its height is 1? And that seems to be a pretty reasonable rule, and it helps with interpretations, I think. And again, I just want to reiterate this last point, because likelihoods, if you're going to buy into this sort of likelihood paradigm of interpreting likelihoods, everyone agrees that they measure relative evidence rather than absolute evidence. So, dividing the curve by its maximum value or any other value, it doesn't change its interpretation. It's actually an interesting question, I might add, to try and think of, could someone create an absolute measure of evidence in statistics? And I'm not aware of any, but so we'll have to stick with relative measures for right now. So here on the next page is a likelihood plot. We have theta on the horizontal axis, and we have the likelihood value with the maximum at 1 on the vertical axis. In this case, this is exactly the likelihood for the 4 coin flips that we saw. So the peak value is 1, and as the likelihood goes down, those values of theta are worse and worse supported. Now, it's kind of interesting that the peak value, right, the likelihood value at which we divided the likelihood by is the best supported point in the data. So that's kind of interesting, right? Because that point has the highest likelihood value. So no matter what you divide it by, you're always going to get a likelihood ratio bigger than 1. So that point seems kind of special. And in fact, we give it a name. We call it the maximum likelihood point. And it's a maximum likelihood turns out to be a very useful technique. And in fact, you might not know this, but the vast majority of statistical estimators you use, maximum likelihood estimators, are very close to them. So the way you would interpret this plot, for example, is take any 2 points. Say if you take 0.4, you get a height at 0.4, and take the value, say 0.6, and you get a height at 0.6. The ratio between those values is the relative evidence. And then because we divided by the maximum, every value that we look at is the relative evidence of that specific value of theta when compared to the point that is best supported by the data, the maximum likelihood point. So the fact that here the value of a fair coin, 0.5, well, it actually has, surprisingly, a likelihood value of about 0.5, which means that the hypothesis, if you were to divide the likelihood at the maximum likelihood value by the likelihood at the fair coin value, you get a ratio of about 0.5, and that gives the relative evidence supporting the point for which you have the maximum likelihood, which turns out to be 0.75 relative to 0.5. So we might draw a horizontal line, and let's say we drew a horizontal line at 1/8. I think that's what this top line is at. It's at 1/8. What does that mean? Well, every point that falls between the endpoints of this line is such that there's no other point that's more than 8 times better supported. So take this point where the curve meets this line. That's exactly 1/8. What does that mean? That point is exactly 8 times worse supported, given the data, than 0.75, which is the maximum likelihood value. And take any point in this interval that falls between the ends of this line, and you can't find another point that's more than 8 times better supported. Take, for example, 0.4. It has a likelihood value that is about 0.3 or whatever, but its ratio relative to the maximum is less than 1/8. So its ratio with everything else is going to be less than that. So you're not going to be able to find for 0.4 another point anywhere on this curve that's more than 8 times better supported than it. So that's the idea behind drawing a line at, say, 1/8 or whatever. If you draw a line, the collection of theta values that lie on that horizontal line between the points where it intersects the likelihood curve are well supported. And of course, as you draw the line, as you go up and up and up, fewer points stay in the interval, to the point where if you draw it high enough, then you only have the maximum likelihood value surviving the threshold. So just to reiterate some of the points we made on the previous slide, the value of theta where the curve reaches its maximum is the maximum likelihood estimate. And if we wanted to write it out mathematically, the MLE is the argument maximum over theta of the likelihood having plugged in the data x. And a nice interpretation of the MLE is it's the value of the parameter that would make the data that we observed most probable. So in this case, we have 3 heads and 1 tail. And the question is, what's the success probability of the coin that we could pick that would make the data that we observe most probable? And that's a nice interpretation of the MLE as well. Well, it turns out, and I think I've alluded this because I kept saying that the likelihood MLE in the previous example was 0.75. How did I get that? Well, there was 3 heads out of 4 tails, so that's a proportion of heads of 0.75. Well, it turns out that if you have independent identically distributed coin flips, then the MLE for theta is always the proportion of heads that you get. And again, I think if anyone were to give a single point estimate for the success probability of that coin, they would all give the proportion of heads. So to be honest, the fact that maximum likelihood yields that is not so much a booster for using the proportion of heads as an estimator. It's more fact that it motivates the use of MLE perhaps in more complicated settings where we don't have great intuition already as to what the kind of logical estimator should be. That's kind of the benefit of MLE, is that in a lot of the cases where we have a really good idea of what should be the right estimator, the MLE returns estimators that exactly mirror our intuition. And that gives us some hope that it would be a useful thing to do in these settings where we don't know what the best estimator is. Then in addition to that, there's been, I think it's fair to say, tomes of theory that have been developed in support of MLEs as you let, say, for example, the number of data points go to infinity. So let's actually just prove this fact that if you have a binomial or if you have n Bernoulli coin flips, that the maximum likelihood estimator is the number or the proportion of heads. So let n be the number of trials, and let's let x be the number of heads. And remember that in this case, the likelihood is theta to the x, 1 minus theta to the n minus x. So theta to the number of heads, 1 minus theta to the number of tails. And then if we want to find the argument maximum of this function, it turns out it's definitely easier to maximize the log likelihood. And this is almost a general principle in statistics that when you have a bunch of independent things and you want to maximize a likelihood, you're better off maximizing the log likelihood. You know, because if you maximize the log of the function, you've maximized the function because log is an increasing monotonic function. And then in addition to that, the fact that you have a bunch of independent things means that you've multiplied a bunch of things to get the joint density or mass function. So if you multiply things, things get raised to powers and so on. And these are all kind of complicated things to work with. Addition is much easier to work with. So log kind of converts products into sums, and that's really quite useful. So x, which is a power, is no longer a power on the log scale, and you get x log theta plus n minus x log 1 minus theta, which is a much easier function to work with. But, in this case, you can do it either way. It's no problem. But one of the reasons it helps in general is that it takes care of the annoying products that you get from independence and multiplying a bunch of densities or mass functions together. If we take the derivative, we get x over theta, n minus x over 1 minus theta. And if we want to solve for the inflection point, we'd set this equal to 0, and we set it equal to 0, and I'm not going to churn through the calculations. If you actually set it equal to 0 and just bring the two terms on either side, it's pretty clear that theta equal to x over n solves that equation. You have 1 minus x over n times theta plus equal to 1 minus theta times x over n. It's pretty clear if you plug in x over n that you're going to get a valid equality there. But you could churn through the calculations and get to the fact that theta is solved at x over n. So in other words, the value of theta that makes the observed data most likely in IID Bernoulli trials is the proportion of heads. Now in below, I check the second derivative condition to make sure the likelihood is concave. So, this technically doesn't handle if you got all failures or all successes, but maybe just do those cases on your own. So what constitutes strong evidence? If we're going to treat the likelihood as our arbiter of evidence and likelihood ratios as measures of evidence, we would like to maybe build up some intuition. And, a friend and a faculty member here taught me this idea of, well, why don't we just use kind of coin flipping as the mechanism for building up our intuition with strength of evidence? So imagine an experiment where a person is considering three possible hypotheses with coin flipping. The coin has tails on both sides, in other words, theta equals 0. The coin is fair, theta equals 0.5, versus the coin has heads on both sides, theta equals 1. And so here we have hypothesis 1, hypothesis 2, and hypothesis 3. And now I have this table for the possible outcomes. So let's suppose I flip the coin and it's head. And I've done this experiment. Unfortunately, it's difficult to do this experiment in this setting, but I've done it in class, and you'll just have to take my word for it. On one coin flip, pretty much no one's willing to ditch the hypothesis that the coin is fair. So at one coin flip, let's suppose you get a head, right? The probability of a head, given the first hypothesis that the coin has tails on both sides, is 0. The probability of a head, given that the hypothesis that the coin is fair, is 0.5. And the probability of a head, given the hypothesis 3 that the coin is two-headed, then that's 1. So the likelihood ratio of hypothesis 1 to hypothesis 2 is 0, and the likelihood ratio for hypothesis 3 relative to hypothesis 2 is 2. And of course, this is exactly what we would hope to happen, right? If the coin is two-tailed, it can't produce a head, so that if we get one head, it should have a likelihood ratio of 0 for supporting the two-tailed hypothesis. Okay, so 2, there's twice as much evidence supporting the hypothesis that the coin is fair and the coin is two-headed, given a single coin flip that's a head. So it's clear that 2 is not terribly strong evidence, especially given either way. If you flip the coin once, something's got to happen. So the 50% probability of getting a head is not that compelling. So let's suppose we got 2 heads in a row. Okay, now I'm going to quit talking about hypothesis 1 because you can't get 2 heads in a row under hypothesis 1. But here I outline all the different possibilities that you could get: head, 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 tail, tail, head, tail, tail. And I go through the likelihood ratio for all of them. But in this case, it's 0.25 for 2 consecutive heads if the coin is fair, and it's 100% of getting 2 heads if the coin is two-headed, so the likelihood ratio is now 4. 4 times as much evidence supporting the hypothesis that the coin is two-headed than the hypothesis that the coin is fair if you get 2 consecutive heads. Now let's suppose we get 3 consecutive heads. And then the probability of getting 3 heads if the coin is fair is 0.125. Probability of getting 3 consecutive heads if the coin is two-headed is 100%. You get a likelihood ratio of 8. And in this case, that means that there's 8 times as much evidence supporting the hypothesis that the coin is two-headed relative to the hypothesis that the coin is fair. And so let me tell you what happens when I do this in a class. I have a two-headed coin and I play this game, and people are willing to keep considering the hypothesis that the coin is fair because most of the time people aren't aware that two-headed coins are easy to buy. So around 3 heads, a substantial fraction of the class has started to believe that the coin is two-headed now. 4 consecutive heads, which would then the likelihood ratio would be 16, of course. 5 consecutive heads, it would be 32, and so on. By 4 consecutive heads, the vast majority of the class is believing that it's two-headed. And then by 5 consecutive heads, basically 100% of the class always agrees that it's two-headed. And I've done games where I have a fair coin and an unfair coin, and I show the class that one of them's fair and one of them's unfair, jumble them up in my hand, and then they don't know which one I'm flipping so that they know I'm not trying to trick them. Well, I am trying to trick them, but not in an obvious way. I'm trying to trick them. Actually, you can kind of tell by the weight which one's fair and which one's not. So I always grab the unfair one. These create sort of useful benchmarks, right? So A8, is sort of being moderate evidence. So the idea behind this is to use this coin flipping, an easy experiment that we can understand, to build up context for what likelihood ratios mean. So 8, sort of moderate evidence, it's sort of like getting 3 consecutive heads on a coin, right? 16 is being strong evidence. This is like getting 4 consecutive heads and the evidence against the coin being fair. And then 32 is being quite strong evidence. And, these are, admittedly, the coin is useful context, but these are no more arbitrary, say, than the existing threshold that, say, is used on p-values, where people just arbitrarily pick 5% as their cutoff for type 1 error rates, if you're aware of this sort of thing. So at any rate, this is why, for example, I draw lines, likelihood plots at the value of 1/8. And so that way, parameter values above the 1/8 reference line are such that no other point is more than 8 times better supported given the data. That's the end of the kind of technical component of this lecture. I wanted to spend a little bit of time just talking about the consequences of kind of adopting this style of analysis. So pretty much every major paradigm in statistics, Bayesianism, frequentism, this likelihood paradigm, pretty much every paradigm in statistics agrees if you assume a probability model and act as if it's true, then the likelihood ratio is a central component to the theory. If you take enough mathematical statistics, you'll see this. The particular paradigm that I'm discussing today then goes beyond this relatively benign use of likelihood ratios that occur in the other areas. What I'm talking about today, right, is that not just that the likelihood ratio is useful, but that likelihood ratios measure relative evidence, and that given a statistical model and observed data, all of the relevant information is contained in the likelihood. And this has kind of far-reaching consequences to the field of statistics. If you go beyond just saying likelihoods are useful to going to say not only are they useful, but they have these properties, then it changes quite a bit of statistics. So for example, much of statistics is devoted to things like hypothesis testing and p-values and other variants of statistics where the interpretation of the statistics involves potentially fictitious repetitions of an experiment. So, for example, if you've ever heard of a confidence interval, the interpretation of a confidence interval is quite confusing, but it's something along the lines of, if you were to use this technique over and over again, you would obtain these intervals that contain the things that they're trying to estimate, say 95% of the time. Well, if you kind of adopt this strong variant of interpreting likelihoods, then that suggests that interpretation can't be valid because it involves potentially fictitious repetitions of the experiment, which do not depend on the likelihood for the data at hand. So it cannot possibly be useful, or it cannot have any additional evidence. So some of the things that get disputed if you adopt this paradigm are p-values, hypothesis testing, multiple corrections. And these are the big ones that come to the top of my head, which is very disputed because In many ways, these techniques seem very central to the idea of statistics. So I really just wanted at this point to introduce people to these concepts, state the consequences of this theory. I think for the purposes of this class, what I would hope you would know after this lecture is what the likelihood is. You would know that regardless of what kind of paradigm of statistics you're in, higher likelihoods generally refer to better supportive values of the parameter, and I would hope that you would understand about the principle of maximum likelihood. Thank you for listening. This was Mathematical Biostatistics Bootcamp Lecture 6, and I look forward to seeing you for the next lecture. Hi, my name is Brian Caffo. I'm in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health, and this is Mathematical Biostatistics Bootcamp, Lecture 7. In this lecture, I'm going to talk about some common distributions. So in this lecture, I'm going to talk about basically 3 distributions, and really 2 if you kind of think about it. So the Bernoulli distribution is one, the binomial distribution, which is a distribution based on the Bernoulli distribution. And then I'll talk about the Gaussian or normal distribution, which is a very important one as well. In fact, I think if all the distributions were to get together and nominate a king, it would definitely be the normal distribution. So the Bernoulli distribution is named after Jacob Bernoulli. We've already talked about it before, but let's formalize it a little bit and remind ourselves of some of the notation. So a Bernoulli random variable is just a fancy name for a coin flip. So Bernoulli random variable takes values 0 and 1 with probabilities p and 1 minus p, where p is some number between 0 and 1. So the probability mass function for a Bernoulli random variable we've seen before. It's the probability that x takes the specific value 0 or 1, and it's p to the x 1 minus p to the 1 minus x. The mean of a Bernoulli random variable is simply p, and the variance is p times 1 minus p. Facts that we've proven before, but we're just restating them now. And in general, for Bernoulli random variables, if you code a coin flip as a 1 or a head, it's often people call that a success and 0 as a failure, and they tend to do this regardless of whether the classification is actually something that's actually successful. So we might call a person getting side effects from a medication a success in terms of the Bernoulli coin flip. It's just a little bit of odd nomenclature, I guess. We've also already talked about the Bernoulli likelihood function. So if we have x1 to xn are observed data points, so the x1 to xn in this slide are numbers that we recorded, a collection of zeros and ones, then the likelihood is the product, because we're going to model these as independent coin flips, the product of p to the xi, 1 minus p, to the 1 minus xi. We've already talked about this equals p to the summation xi, 1 minus p to the n minus summation xi. So notice again that the likelihood only depends on the sum of the x's, so the total in each x is 0 or 1, so the sum of the x's is just the total number of successes. And then n minus the sum of the x's is the total number of failures. So if you know n and you know the total number of successes, then you know the Bernoulli likelihood. It doesn't matter what order the heads or tails occurred as far as information is contained in the data about the parameter p. Because n is fixed and assumed known, this implies that the sample proportion contains all the relevant information that you need to know about p insofar as the likelihood codifies it, simply because summation xi and summation xi over n are 1 to 1. You can get from one to the other easily by either multiplying or dividing by n. So the sufficiency result is basically that the proportion of successes is all the relevant information you need to make Bernoulli inference about a parameter. Now, again, this all depends on the model being correct, that you have correctly modeled the data as IID Bernoulli. We also, when we talked about maximum likelihood, we also showed that if you maximize the Bernoulli likelihood over p, then you obtain that p hat, which is summation xi over n, is the maximum likelihood estimator. And here's, we went over an example.
So here, just to give you an example of Bernoulli likelihoods and what they look like, imagine if we flipped a coin 4 times. So if we flipped a coin 4 times, there's only 4 possible sufficient statistics that we could obtain. We could get 0 heads, 1 head out of the 4 coin flips, 2 heads out of the 4 coin flips, 3 heads out of the 4 coin flips, or 4 heads out of the 4 coin flips. And here is the 4 possible likelihoods that you could obtain from this experiment. And they're all normalized to have height 1. So here's on the leftmost one is the likelihood you get if you had no heads. The second one, you see it shifted a little bit to the right? And its peak is going to be right at p hat at a quarter, okay? And then if you get 2 heads, then you see that peak, the MLE in this case, is right at 0.5, and the likelihood shifts a little bit to the right. And if you've gotten 3 heads, it shifts a little bit more to the right. And if you've gotten 4 heads, then it shifts closer to 1. Notice, even in the event that you get all tails or all heads, the likelihood is not entirely at 0 or entirely at 1, right? There's substantial uncertainty, right? The likelihood is correctly codifying the information that it's possible, even if the coin is, say, fair, here's the likelihood point right here, even if the coin is fair, to get 4 consecutive tails. And, it's just much less likely than if the coin is unfair towards some value closer to 0. So the likelihood, it's not entirely shoved up against the vertical line at 0. And it just gets closer and closer to that vertical line as you continue to flip and get tail after tail after tail. Binomial random variables are nothing other than the sum of IID Bernoulli trials. We've seen that the key variable from a Bernoulli experiment is the number of heads. So why don't we just create a random variable that is the number of heads? So in specific, if x1 to xn are IID Bernoulli, then the random variable x, defined as the sum of the individual xi's, is a so-called binomial random variable. And the binomial mass function is just the probability x takes any specific value is n choose x, p to the x, 1 minus p to the n minus x, where p is the probability from each of the Bernoulli coin flips. Here, the values that x can take are 0 if every single coin flip was a tail, all the way up to n, where every single coin flip was a head. Just to remind everyone, the notation n choose x, right, this parentheses n over x, n parentheses, this is n factorial over x factorial n minus x factorial. Here, 0 factorial we're going to treat as 1. And this formula counts the number of ways of selecting x items out of n without replacement, disregarding the order of the items. Okay, so let's consider an example. Imagine I have 10 neckties, and I pick out 3 and put them on my bed, let's say. And I'm not caring about what order on my bed from left to right or something like that. And so 10 choose 3 is the number of different configurations of ties that I could have obtained by picking 3 ties out of my 10 possible. So that's an example. I can't think of any reason why you would want to do this with your neckties, but whatever. So it's very easy, in fact. Certain special cases are very easy. So imagine if I was only picking 1 necktie, right? How many different combinations can I get? Well, intuitively, we know that that answer has to be 10, right? Because, there's only 10 possibilities. Well, if you plug into the formula, you have 10 factorial divided by 1 factorial, which is just 1, n minus x factorial, which is 10 minus 1, or 9 factorial. So we have 10 factorial divided by 9 factorial, which is just 10. Okay? Another quite useful one is choose 2. How many ways can you pick 2 things out of n objects? That one seems to come up a lot in my daily life for some reason. And so that's, in this case, would be 10 factorial over 2 factorial, which is just 2, right? 2 times 1. Then divided by 8 factorial, right? So that's 10 times 9 divided by 2. So, at any rate, the general rule is for n choose 2, you just want to take n times n minus 1 over 2. And at any rate, it's one of the ones that it's worthwhile just to memorize the formula for that special case because it seems to pop up a lot. So why is that factor? Why is n choose x the factor out in front of a binomial mass function? So let's now consider the possibility of getting 6 heads out of 10 coin flips from a coin with success probability p. Well, if you account for the order, if you say, what's the probability of getting tail, 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 that's 4 tails, then the remaining are heads, right, in that specific order, right? We know what that probability is. We would just plug into the multivariate Bernoulli mass function obtained by multiplying the Bernoulli mass function for each coin flip in order, and we would get p to the 6th, 1 minus p to the 4th. And as we know, because of the fact that it's only the total number of heads that is sufficient, that if it wasn't just the first 4 coin flips that were tails, if it was the last 4 coin flips that were tails, and the first 6 were heads, then we would get the same number. We'd get p to the 6th, 1 minus p to the 4th. And if we had the 4 tails sprinkled in any configuration of the 6 heads, then you will still get the same possible answer, p to the 6th, 1 minus p to the 4th. The result is that basically for any collection of instances where you get 6 heads and 4 tails, no matter what the order is, the probability is going to be p to the 6th. So what we need is to count how many such configurations there are. Well, in this case, there's 10 flips and 10 positions that could be heads, and we want to know how many different collections of positions we can obtain. And that's just 10 choose 6. It's just exactly the necktie problem, but now we're picking the position of the coin flip that is a head, right? And so in this case, there's 10 choose 6 possible orders of 6 heads and 4 tails. We don't actually have to go through the specific construction of the binomial distribution because I think that's a pretty clear demonstration. That's how you would wind up with the probability of the sum of a collection of 10 Bernoulli random variables being 6, right? You would sum over all the possible ways you could get 6 heads, and it turns out that they all have the same probability, p to the 6th, 1 minus p to the 6th. So we just need the number of things that go into that sum, and it's pretty clear that it's 10 choose 6. So yeah, we only did this for a specific instance here. I hope you can see that if 10 instead was n, and 6 instead was x, that you would wind up with the same answer. N choose x, p to the x, 1 minus p to the n minus x. So that's the motivation. And you can actually mathematically check that the binomial mass function sums to 1. In fact, it's actually kind of a relatively famous formula, the binomial sum. And so if you, for example, look up on Wikipedia the binomial sum, you'll see that it just exactly illustrates that formula by itself, tells you exactly that the binomial mass function sums to 1, but we're right now just going to trust that we did our calculation right. So let's just go through an example of using the binomial mass function. So suppose you have an intrepid friend that has 8 children, and it turns out that 7 of them are girls and none of them are twins. And so if you're very parsnickety, let's just forget about all the little parsnickety things that you could possibly think about related to this problem, like having twins. So let's just think about the problem in the conceptual way. We're going to think of every child from this family, its gender being a coin flip. And the question is, what's the chance of getting 7 out of 8 children that are girls if it really is the case that every child, their gender is independent from the other children and that there's a 50% probability at each birth of having a girl? And so what's the probability of getting 7 or more? Well, that's the probability of 7 or more is the probability of getting 7 girls out of 8 plus the probability of getting 8 girls out of 8. And so in this case, for the fair coin, it would be 8 choose 7, 0.5 to the 7th, 1 minus 0.5 to the 1. And then 8 choose 8, 0.5 to the 8, 1 minus 0.5 to 0. And, check with your calculator or even better with R, that you can get this number. It's about 4%. This is an example of using the binomial formula. I wanted to mention this particular example because this calculation is an example of a so-called p-value. And a p-value is always the probability under a null hypothesis of getting a result as extreme or more extreme than the one actually obtained. So the logic behind the p-value in this specific instance is that you have this evidence here that you think, wow, 7 girls out of 8 children, that seems pretty odd. Maybe the 50% chance of girls versus boys for this particular family is off for whatever the reason. So the p-value is saying, okay, well, why don't we calculate the probability, if the null hypothesis was true, of getting an event this extreme? And if that probability is very low, then maybe that's an indication that our hypothesis that the 50% is correct is not right. So, at any rate, we'll talk about p-values later. Well, I hope we'll get to talking about p-values later. But I just wanted to mention that that's where the intuition behind this calculation is coming from. Right now, we're only using it as an illustration of plugging into the binomial formula, but I wanted to foreshadow kind of an important statistical technique. And then here in this page is the likelihood associated with p for this particular binomial experiment, if we're willing to model births as if they were binomial. And so here you can see, 0.5 is in the 1/16th likelihood, but not in the 1/8th likelihood. And then you can see, that this likelihood is far more peaked around 7/8, or it reaches its maximum at 7/8, and then the curvature of it sort of gives you a sense of the relative evidence for the collection of possible values of p. So that's the binomial distribution. Let's talk about the most famous of all distributions, and probably the most handy of all distributions is the so-called normal or Gaussian distribution. The term Gaussian comes from the great mathematician Gauss. And it's kind of interesting to know, Gauss didn't invent the normal distribution. The invention of the normal distribution is kind of a debated topic. For example, Bernoulli had used something not unlike the Gaussian distribution as a probabilistic inequality, not formalizing it as a density. If you're interested in this, the book by Stephen Stigler on the history of statistics actually has a nice summary of exactly where and when and who came up with the Gaussian distribution. But it's clear that Gauss was instrumental in the early development and in use of the Gaussian distribution. So a random variable is said to follow a normal or Gaussian distribution with parameters mu and sigma squared if the density looks like this: 2 pi sigma squared to the minus 1/2 e to the negative x minus mu squared over 2 sigma squared. And so this density, it looks like a bell, and it's centered at mu, and sigma squared sort of controls how flat or peaked it is. And so it turns out that the mu is exactly the mean distribution, and sigma squared is exactly the variance of this distribution. So you only need 2 parameters, a shift parameter and a scale parameter, to characterize a normal distribution. So we might write that x is this little squiggle, then n mu sigma squared, as just sort of shorthand for saying that a random variable follows a normal distribution with mean mu and variance sigma squared. And in fact, one instance of the normal distribution is sort of the kind of root instance from which all the others are sort of derived, and that's when mu equals 0 and sigma equals 1. And so we would call that the standard normal distribution. It's centered at 0 and its variance is 1. And so all other normal distributions are simple shifts and rescaling of the standard normal distribution. But then again, you could pick a different root, maybe mu equal 5 and sigma equal 2, but it wouldn't be quite as convenient. You could still get every other distribution from that one by shifting and scaling appropriately, but it wouldn't be as convenient. This is the most convenient way to define a sort of root of the normal distribution. The standard normal density is so common that we often reserve a Greek letter for it. So the lowercase phi we usually use for the normal density, and the uppercase phi we would use for the normal distribution function. And standard normal random variables are often labeled with a z, and you sometimes will even hear introductory statistics textbooks and so on refer to them as z variables or z distributed or something like that, and that's because this notation has become so common. Here's the normal distribution. It looks like a bell. That's how it gets its name, the bell-shaped curve. And sort of here I've drawn reference lines at 1 standard deviation, 2 standard deviations, and 3 standard deviations, 1 above and negatives being below and positives being above. Now again here, so the 1, right, because this is a standard normal distribution, right, the 1 represents 1 standard deviation away from the mean. Here the mean is 0. 1 is 1 standard deviation away from the mean. 2 is 2 standard deviations away from the mean. And 3 is 3 standard deviations away from the mean. Instead of thinking of these numbers as just z values in the denominator, if we think about them in the units of the original data, right, and this representing 1 standard deviation from the mean, 2 standard deviations from the mean, and 3 standard deviations from the mean, it doesn't matter whether we're talking about a standard normal or a non-standard normal, they all are going to follow the same rules. So about 68% of the distribution is going to lie within 1 standard deviation, about 95% is going to lie within 2 standard deviations, i.e. between -2 and +2, and about almost all of the distribution, about 99% of it's going to lie within 3 standard deviations. We can get from a non-standard normal to a standard normal very easily. So if x is normal with mean mu and variance sigma squared, then z equal to x minus mu over sigma is in fact standard normal. Now, you could at least, given the information from this class, check immediately that z has the right mean and variance. So if you take the expected value of z, you get the expected value of x minus mu divided by sigma. You can pull the sigma out, and then you have expected value of x minus mu, which is just 0, because that's expected value of x minus expected value of mu. Mu is not random, so that's just mu, and mu is defined as expected value of x, so that's just 0. Then the same thing with the variance. If you take the variance of z, you get the variance of x minus mu divided by sigma, right? So if we pull the sigma out of the variance, it becomes a sigma squared, and we have variance x minus mu. And we learned a rule with variances that if we shift a random variable by a constant, say in this case subtracting off mu, it doesn't change the variance at all, so we get variance of x divided by sigma squared. Variance of x is sigma squared, so we get sigma squared divided by sigma squared, which is 1. So at the bare minimum, we can check that z has mean 0 and variance 1. By the way, there was nothing intrinsic to the normal distribution that occurred in that calculation, right? So we've also just learned an interesting fact, which is that take any random variable, subtract off its population mean, and divide by its standard deviation, and the result is a random variable that has mean 0 and variance 1. In this case, in addition, if x happens to be normal, then z also happens to be normal. Similarly, we can just take this equation where z equals x minus mu over sigma, and we can multiply by sigma and then add the mu and get that if we were to take a standard normal, say z, scale it by sigma, and then shift it by mu, then we wind up with a non-standard normal. You know, the top calculation goes from a non-standard normal and converts it into a standard normal, and the bottom equation starts with a non-standard normal and converts it into a normal. Another interesting fact is that the non-standard normal density can just be obtained as a plugging into the standard normal density. So if you take the standard normal density, phi, and instead of just plugging in z to it, say, you plug in x minus mu over sigma, and then divide the whole thing by sigma, then that is exactly the non-standard normal density. And this is a kind of a way to generate, just kind of as an interesting aside. Here, mu is a shift parameter. So all mu does is shifts the distribution to the left or the right, right? Just like whenever you subtract a constant from an argument in a mathematical function, it's just moving the function to the left and the right. And then sigma is a scale factor. And so basically, whenever you take a kernel density, some density, I guess it works for any density, but it makes most sense to do it with a density with mean 0 and variance 1. And then you create a new family where you're plugging in x minus mu over sigma and then divide the density by sigma, you wind up with a new family of densities that now have mean mu and variance sigma squared. So this is kind of an interesting way of taking a root density with mean 0 and variance 1 and then creating a whole family of densities that have mean mu and variance sigma squared. They're usually called location scale families. At any rate, we're only interested in this case in the normal distribution, and this formula right here is exactly how you can go from the standard normal density and use it to create a non-standard normal density by plugging into its formula. Let's just talk about some basic facts about the normal distribution that you should memorize. So about 68%, 95%, and 99% of the normal density lies within 1, 2, and 3 standard deviations of the mean, respectively. And it's symmetric about mu. So for example, take one standard deviation, about 34%, one half of 68%, lies from within one standard deviation on the positive side, and about 34% lies within one standard deviation below the mean. So each of these numbers split equally to above the mean versus below the mean. And then there's certain quantiles of the normal distribution that are kind of common to have memorized. So negative 1.28, negative 1.645, negative 1.96, and negative 2.33 are the 10th, 5th, 2.5th, and 1st percentiles of the standard normal distribution. And then again, by symmetry, so if we just flip it around, right? So if negative 1.28 is the 10th percentile, then 1.28 has to be the 90th percentile. So by symmetry, 1.28, 1.645, 1.96, 2.33 are the 90th, 95th, 97.5th, and 99th percentile of the standard normal distribution. One in specific I want to point out that you really need to memorize is 1.96. The reason it's useful is it's the point so that if you take negative 1.96 and positive 1.96, the probability of lying outside of that range, right, below negative 1.96 or above positive 1.96, well, that's 5%. So 2.5% below it and 2.5% above it. So that's 5%. So the probability of lying between 1.96, negative 1.96, and positive 1.96 is 95%. And so anyway, it's used to do things like create confidence intervals and these other entities that are very useful in statistics, and people have kind of stuck with 95% as a reasonable benchmark for confidence intervals, and 5% is a reasonable cutoff for a statistical test. And if you're doing two-sided, you need to account for both sides, and so you use 1.96. And then the other fact is that 1.96 is close enough to 2 that we just round up. So a lot of times things like confidence intervals, you might hear people talking about, well, just add and subtract 2 standard errors. They're getting that 2 from this 1.96 right here. So anyway, that one in specific you should memorize, but you should probably just memorize all of them. Let's go through some simple examples. So we'll go through 2, and you should just be able to do lots of these after I go through 2. So let's take an example. What's the 95th percentile of a normal distribution with mean mu and variance sigma squared? So recall, what do we want to solve for if we want a percentile? Well, we want the point x naught, so that the probability that a random variable from that distribution x being less than or equal to x naught turns out to be 95% or 0.95. Okay? And so, it's kind of hard to work with non-standard normals. So the probability that x being less than or equal to x naught is 0.95. Well, why don't we subtract off mu from both sides of this equation and divide by sigma from both sides of this equation. And on the left-hand side of this inequality, x minus mu over sigma, well, that's just a z random variable. Now, a standard normal random variable. So the probability that x is less than or equal to x naught is the same as the probability that a standard normal is less than or equal to x naught minus mu over sigma, and we want that to be 0.95. Well, if you go back to my previous slide, 0.95, 95th percentile of the standard normal is 1.645. So we just need this number, x minus mu over sigma, to be equal to 1.645 to make this equation work. And so let's just set it equal to 1.645, right? And then solve for x naught. So we get x naught equals mu plus sigma times 1.645. So now you could ask lots of questions with specific values of mu and sigma, but you'll wind up with the same exact calculation. And here, in fact,
we used 1.645 because we wanted the 95th percentile, but in general, x naught is going to be equal to mu plus sigma z naught, where z naught is the appropriate standard normal quantile that you want. And then you can just get them very easily. The other thing I would mention too is you should be able to do these calculations more than anything, just so you've kind of internalized what quantiles from distributions are and how to sort of go back and forth between standard and non-standard normals and the kind of ideas of location, scale, densities, and that sort of thing. In reality and practice, it's pretty easy to get these quantiles because, for example, in R, you would just type in Q norm 0.95 and then give it a mean and a variance. Or if you did Q norm 0.95 without a mean and a variance, it'll return 1.645, and you can do the remainder of the calculation yourself. But even that's a little bit obnoxious, so you can just plug in a mu and a sigma. So these calculations aren't so necessary from a practical point of view. Even very rudimentary calculators will give you normal quantiles, non-standard normal quantiles. The hope is that you'll kind of understand the probability manipulations. You'll understand, what a quantile means. You'll understand, what the goals of these problems are. And you'll understand sort of how to go backwards between a standard and non-standard normal. That's kind of what we're going for here. It's kind of clear. I think everyone agrees that you can very easily just look these things up without having to bother with any of these calculations. Let's go with another easy calculation. What's the probability that a normal mu comma sigma squared random variable is 2 standard deviations above the mean? So in other words, we want to know the probability that x is greater than mu plus 2 sigma. Well, again, do the same trick where we subtract off mu and sigma from both sides, and we just get the answer that that's the probability that a standard normal is bigger than 2. And that's about 2.5%. And so you can see the kind of rule here. If you want to know the probability that a random variable is bigger than any specific number, or smaller than any specific number, or between any two numbers, instead of take those numbers and convert them into standard deviations from the mean, right? And that can, of course, be fractional. It could be 1.12 standard deviations from the mean or whatever. And the way you do that is by subtracting off mu and dividing by sigma, and then revert that calculation to a standard normal calculation. So if you wanted to know what's the probability that a random variable is bigger than, let's say 3.1, just to pick out a random complicated sounding number. Let's suppose you're talking about the height of a kid and you want to, say what's the probability of being taller than 3.1 feet. What you would need is the population mean mu and the standard deviation sigma. Take 3.1, subtract off mu, divide by sigma. Now you've just converted that quantity, 3.1, which is in feet, right, to standard deviation units. And then you can just do the remainder of the calculation using the standard normal. So I would hope that you could kind of familiarize yourself with these calculations. And I recognize that, in a sense, they're kind of ridiculous to do because you can get them from the computer so quickly. And we'll give you the R code that you need to do these calculations very quickly on the computer. But I think it's actually worth doing them by hand some, just to get used to working with densities, to get used to what these calculations refer to. So let me just catalog some properties of the normal distribution. A lot is known about the normal distribution. And so I'll outline some of the simpler stuff, and some of the stuff, the lighter points, we probably won't get to in this class, but I thought I'd just at least say. So anyway, the normal distribution is symmetric and it's peaked about its mean, which means that the population mean associated with this normal distribution, the median, and the mode are all equal right at that peak. A constant times a normally distributed random variable is also normally distributed, and you can tell me what happens to the mean and the variance if, say, x is a normal random variable. What distribution does a times x have if I'm going to tell you that it's normal? What's the resulting mean and variance? It turns out that sums of normally distributed random variables are again normally distributed. And this is true regardless of the dependent structure of the data. So if the random variables are jointly normally distributed,
It's important that they're jointly normally distributed. They could be independent, they could not be independent, but they need to be jointly normally distributed. The sums or any linear function of the normal random variables turns out to be normally distributed. And again, you can calculate the mean and the variance. Sample means of normally distributed random variables are again normally distributed. Again, this is true regardless of whether or not they're jointly normal and possibly dependent, or if they're simply a bunch of independent normal random variables. This is true of sample means. However, let me just jump to point 7. It also turns out that if you have independent, identically distributed observations, properly normalized sample means, their distribution will look like a Gaussian distribution, not entirely, but pretty much regardless of the underlying distribution that the data comes from. So take as an example, if you roll a die and look at what the distribution of a die roll looks like, it doesn't look very Gaussian. It looks like a uniform distribution on the numbers 1 to 6. Now take a die, roll it 10 times, take the average, and then repeat that process over and over again and think about what's the distribution of this average of die rolls. Well, it turns out it'll look quite Gaussian. It'll look very normal. At any rate, that's the rule, is that random variables properly normalized with some conditions that we're probably going to gloss over will limit to a normal distribution. And that's how the normal distribution became the sort of Swiss Army knife of distributions, is that pretty much anything you can relate back to a mean of independent things tends to look normalish in distribution. And mathematically, formally, if they're independent and identically distributed you normalize the mean in the correct way, then you get exactly a standard normal distribution. That is an incredibly useful result. It's a very historically important result called the central limit theorem. So let's see, back to point 5. If you take a standard normal and square it, you wind up with something that's called the chi-squared distribution. You might have heard of that before. And if you take a standard or non-standard normally distributed random variable and exponentiate it, take e to the x, where x is normal, then you wind up with something that's log normal. Log normal is kind of a bit of a pain in the butt in terms of its name. A log normal means take the log of a log normal and it becomes normal. It doesn't mean the log of a normal random variable. It's a little annoying fact, right? And you can't log a normal random variable, by the way, because there's a non-zero probability that it's negative and you can't take the log of a negative number. The name makes it sound like a log normal is the log of a normal. It's not. Log normal means take the log of me and then I'm normal. Okay, let's talk about ML properties associated with normal random variables. If you have a bunch of IID normal mu sigma squared random variables, and let's assume you know the variance, so let's ignore the variance for the moment, then the likelihood associated with mu is written out right here. You just take the product of the likelihoods for each of the individual observations. And so you wind up with 2 pi sigma squared to the minus 1/2 e to the negative xi minus mu squared over 2 sigma squared. If you move that product into the exponent, you get minus summation I equal 1 to n's xi minus mu squared over 2 sigma squared. Remember, we're assuming that the variance is known. So the 2 pi sigma squared to the minus n over 2 that you would have gotten, we can just throw that out, right? Because remember, the likelihood doesn't care about factors of proportionality that don't depend on mu, in this case, because mu is the parameter we're interested in. By the way, this little symbol right here, this proportion to symbol is what I mean. That means I dropped out things, it's proportional to, I dropped out things that are not related to mu. And I'll try and use that symbol carefully where it's contextually obvious what I mean, what variable I'm considering important. Okay, so let's just expand out this square and you get summation xi squared over 2 sigma squared plus mu summation xi over sigma squared minus n mu squared over 2 sigma squared. Now, this first term, negative summation xi squared over 2 sigma squared, again, that doesn't depend on mu. So we can just throw it out, right? It's e to that power times e to the latter 2 powers. So that first part is a multiplicative factor that we can just chuck. Then the other thing here is it's a little annoying to write summation xi. Why don't we write that as nx bar, right? Because if you take x bar, the sample average, and multiply it by n, you get the sum. Okay, so the likelihood works out to be mu n x bar over sigma squared minus n mu squared over 2 sigma squared. So that's the likelihood. Let's ask ourselves, what's the ML estimate for mu when sigma squared is known? Well, as we almost always do, the likelihood is kind of annoying to work with, so why don't we work with the log likelihood? We take the log from the previous page, and we get mu n x bar sigma squared minus n mu squared over 2 sigma squared. If you differentiate this with respect to mu, you wind up with this equation right here, which is clearly solved at x bar equal to mu. And so what it tells us is that x bar is the ML estimate of mu. So if your data is normally distributed, your estimate of the population mean is the sample mean. That makes a lot of sense. We would hope that the result would kind of work out that way. But also notice, because this calculation didn't depend on sigma, this is also the ML estimate when sigma is unknown. It's not just the ML estimate when sigma is known. So we know what our ML estimate of mu is. Let me just tell you what the ML estimate for sigma squared is. The ML estimate for sigma squared works out to be summation xi minus x bar squared over n. And you might recognize this as the sample variance, but instead of our standard trick of dividing by n minus 1, we're now dividing by n, which is a little frustrating that there's this kind of mixed message that the maximum likelihood estimate for sigma squared is the so-called biased estimate of the variance rather than the unbiased one where you divide by n minus 1. Now notice as n increases, this is irrelevant, right? The factor that disputes the two estimates is n minus 1 over n, and that factor goes to 1 as n gets larger and larger. So I've had several colleagues tell me that they would actually just prefer this estimate, this maximum likelihood estimate, and their argument is something along the lines of, well, the n minus 1 estimate is unbiased, but this one has a lower variance. And what they mean is, this is the biased version of the sample variance. It's only a function of random variables, so it itself is a random variable. And as a random variable, it has a mean and a variance. The fact that its mean is not exactly sigma squared means that it's biased, but it has a variance, and its variance is slightly smaller than the variance of the unbiased version of the sample variance. And so this is an example that pops up all the time in statistics, that you can trade bias versus variance. In this case, one variance estimate is slightly biased, but will give you a lower variance. Another one is unbiased, but the variance estimate itself has a larger variance. And it's very frequent in statistics that you have this kind of trade-off. You can pick one. As you increase the bias, you tend to decrease the variance and vice versa. So the other thing I wanted to mention was, here we've kind of separated out inference for mu and inference for sigma. If you wanted to do kind of full likelihood inference, then you have exactly a bivariate likelihood, a likelihood that depends on mu and sigma. And it's a little bit difficult to visualize, but it is just a surface, right, where you have mu on one axis, sigma on another axis, and the likelihood on the vertical axis. Then it would just be a likelihood surface instead of a likelihood function. And it's a little bit hard to visualize these kind of 3D looking things. So there are methods for getting rid of sigma and looking at just a likelihood associated with mu, and getting rid of mu and looking at a likelihood just for sigma. And later on, we'll discuss methods for them. But for the time being, it's not terribly important. What I would hope you would remember is that if you assume that your data is normally distributed, then, we gave you the likelihood for mu if you assume sigma was known. We calculated that the ML estimate of mu was in fact x bar, and that the ML estimate of sigma squared was, pretty much the sample variance, off by a little bit from the standard sample variance, but pretty much the sample variance. And then, the ML estimate of sigma, not sigma squared, but of sigma is just the square root of our estimate for ML estimate for sigma squared.
Well, that's the end of our whirlwind tour of probably the two most important distributions. There's some other ones that we'll cover later. Next lecture, we're going to travel to a place called Asymptopia. And everything's much nicer in Asymptopia, and so I think you'll quite like it there. Hi, my name is Brian Caffo. I'm in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health, and this is Mathematical Biostatistics Bootcamp, Lecture 8 on Asymptotics. In this lecture, we're going to take a trip to Asymptopia. Asymptopia is a land where we have an infinite amount of data, so it should be fun. We're going to talk about limits, but limits of random variables. And so there's intricacies that you have to account for when you consider random variables instead of standard mathematical limits. And it's a quite difficult subject, but we're going to show that we have basically two tools, the law of large numbers and the central limit theorem, that are going to be our primary methods for looking at limits of random variables. So let me just review numerical limits first. And I'm not going to go into too much detail, and I'm going to kind of treat it heuristically. Just to illustrate, in case your asymptotics is a little bit rusty, suppose I had a sequence where A1 was 0.9, A2 was 0.99, and A3 was 0.999, and I hope you can get the pattern at this point. So clearly this sequence, in some sense of the word, converges to 1. It converges to 0.9999999. So that gets closer and closer to 1 as the element of the sequence gets larger and larger. Well, we can formalize this. The formal definition of a limit is for any fixed distance, we can find a point in the sequence so that the sequence is closer to the limit than the distance from that point on. So take, for example, this sequence. The distance between an and 1 is 10 to the minus n, where n is the point in the sequence. And so if we pick any distance, say epsilon, we can find an n so that 10 to the minus n is smaller than epsilon, and then because 10 to the minus n just keeps getting smaller as n gets larger, then it's smaller than epsilon from that point onward. So that satisfies our definition of a limit, so clearly this converges to 1. And it's kind of an interesting fact that an infinite sequence of 0.9s and 1 is the same number. But that's kind of an interesting fact that if you ever take a class on real analysis, they'll discuss that sort of thing at length. But anyway, I hope you get this basic sense of a limit. As n goes to infinity, the sequence converges or looks more and more like its limit so that the distance just gets closer and closer and closer and never gets bigger again. The problem with that is that only works for just a series of numbers, right? Now we want to talk about, say, limits of averages of coin flips. And then it gets much harder. So take, for example, the average. And now we're going to talk about an average comprised of n observations. So let's say xn bar, and now instead of saying x bar like we typically do, which is our average, we're going to annotate it by a subscript n to show that it's an average of the first n of a collection of IID observations. So for example, x bar could be the average of the result of n coin flips, which is the sample proportion of heads. Well, there is a limit theorem for averages, and we would say that xn bar converges in probability to a limit, and we relate this back to the ordinary definition of limit by saying, well, the probability that x is closer than any specific distance converges to 1. So in this case, probability xn bar minus the limit being less than any quantity epsilon that you fix, then that probability is a number, Pn, right? And the definition of convergence in probability is that sequence of numbers, Pn, converges to 1, right? So we've converted the problem of what does it mean for a random variable to converge? We've converted that back to the definition of convergence of a series of numbers. We've said convergence in probability implies a convergence of the collection of probability numbers in the standard sense of the definition of convergence. So now we have a way of talking about how random variables converge. So establishing that a random sequence of variables actually converges is
hard. As you can imagine, it's hard. If you look back at the previous definition, it's not the easiest thing in the world to think about. So we have something that makes it a lot easier for us, and that's called the law of large numbers. So if you've heard people talk about the law of averages, typically they don't know what they're talking about, but probably they're referring to the law of large numbers. And the law of averages, or the law of large numbers, basically says that if xn to x1 are IID from a population with mean mu and variance sigma squared, so in this case we're going to assume that the random variables have a variance. It's interesting to note that there are distributions where there is no variance. You try and calculate the variance and you get infinity or something like that. In this case, we're going to assume that there is a variance and that it's finite. Then the sample average of IID observations always converges in probability to mu. And that's called the law of large numbers. Probabilists make a lot of distinction over various kinds of the laws of large numbers, and they've worked very, very hard to get kind of minimal assumptions for the law of large numbers to work. And in fact, we're using a very lazy version of the law of large numbers. They would probably be upset at us for teaching this one, but it's okay. We don't care. The basic idea I want you to get is that averages converge to mu. Averages of IID observations converge to mu, the population mean that from which the observations were drawn. This is a good thing, right? This basically says if we go to the trouble of collecting an infinite amount of data, then we get the number that we want to estimate, mu, exactly, right? Which is good because collecting an infinite amount of data takes a lot of time, actually infinite amount of time. If you're willing to make this many assumptions, the x's all have a finite variance, it's pretty easy to prove the law of large numbers using Chebyshev's inequality. Which Chebyshev's inequality, if you remember, had a pretty simple little proof. So this kind of very complicated idea, it's amazing that it has a fairly simple little proof. So remember that Chebyshev's inequality states that the probability that a random variable is more than k standard deviations from the mean is less than 1 over k squared. So therefore, the probability that xn bar minus mu in absolute value is bigger than or equal to k standard deviation of x bar sub n is less than or equal to 1 over k squared. Now, let's pick an epsilon. Pick any distance epsilon, because remember, to establish the convergence of a limit of numbers, we have to pick an epsilon. And now to establish convergence in probability, we have to show that the probability that xn bar minus mu being bigger than epsilon goes to 0, or being less than epsilon goes to 1. Those two statements are equivalent. And so let's let k from our previous definition be epsilon divided by standard deviation of xn bar. K is not a random variable, right? Epsilon is a number that we pick, and standard deviation of xn bar is a random variable, but the standard deviation of it is sigma over square root n, okay? So this is just a number. There's nothing random in our definition of k. So if you plug that back in for k, right, you get the probability that xn bar minus mu being bigger than epsilon is less than or equal to the standard deviation of xn bar squared, which is the variance of xn bar, divided by epsilon squared. And we, from a previous lecture, already calculated what the variance of xn bar is. It's sigma squared over n. So this probability is less than or equal to sigma squared over n epsilon squared. Now, as n goes to infinity, sigma squared isn't changing and epsilon squared isn't changing, and the n's in the denominator, so this whole thing goes to 0. Okay, so the probability that the random average xn bar is more than epsilon away from the mean goes to 0 as n goes to infinity, or restated, the probability that xn bar is less than epsilon from the mean goes to 1 as n goes to infinity. So in either of those statements equivalently say that xn bar converges in probability to mu. I think it's kind of staggering that it's really basically 2 lines is all you need to establish this fairly complicated result. Now on the next page, I just have a simple example where I simulated random normals with a mean of 0, and I show the cumulative sample mean. So I took one random normal, and then I took that random normal and generated a second random normal, and then averaged it, and then generated a third random normal, and just averaged it with the remainder. And the iteration on the bottom is the number of observations that goes into that mean, right? And then on the vertical axis, it shows the value of the average. And you can see at first there's quite a bit of variability, right? Remember, the variance of the average is sigma squared over n, so the variability is going to 0, and this dashed line is the asymptote, right? And as you can see, this average, as we include more observations in it, is going to converge to this. You can see it already converging a little bit by 100 iterations to this dashed line. That's simply the law of large numbers. So let's cover some useful facts about the law of large numbers. One interesting fact is functions of convergent random sequences converge to the function evaluated at the limit. So this includes sums, products, differences. So for example, xm bar squared converges to mu squared, right? Because x bar converges to mu, and so this is just a function of x bar, so xn bar squared converges to mu squared. Something different is that average of the squared observations converges to a different entity, okay, right? Let's go through this a little bit carefully just because it's kind of an odd little point. So xm bar squared converges to mu squared, but if we sum up xi squared, the individual observation squared, and divide it by n, that no longer converges to mu squared. Well, why not? Well, it's the difference between the square of the average and the average of the squares. So in this case, it's the average of the squares. In this case, each xi squared is a random variable. So we could just call it y instead of xi squared. And then their average of these xi squareds, or average of these y's, is going to converge to the population mean of those y's. Well, we can calculate that. We know what the expected value of xi squared is because we can use the shortcut formula for the variance, which recall was expected value of xi squared minus expected value of xi quantity squared. We can just work that formula to solve for expected value of xi squared and show that that's equal to sigma squared plus mu squared. So the average of the squared observations converges to sigma squared plus mu squared, whereas the square of the average converges to mu squared. So it's kind of an interesting little point, but just remember that those things are different. And by the way, this little fact that we just showed, we can use this to prove that the sample variance converges to sigma squared. And we'll do that on the next slide. So let's actually go through this proof that the sample average converges to sigma squared. And I think you'll see in the process of the proof that it doesn't matter whether we divide by n or n minus 1, it's going to converge to sigma squared. So here we have the definition of the sample average. Summation xi minus xm bar squared, all divided by n minus 1. We're going to use the unbiased estimate of the sample variance. Well, recall there was a shortcut formula for the sample variance, and it worked out to then be the numerator had a shortcut formula that was summation xi squared minus n x bar squared. And so we're going to use that formula, and then we get summation xi squared over n minus 1 minus n bar squared over n minus 1. And let's just rearrange terms and multiply and divide by some n's because that n minus 1 is a little annoying. So we have n over n minus 1 times summation xi squared over n minus n over n minus 1 times xm bar squared. Well, let's look at each of these things in turn. And remember, from the previous slide, I told you, I didn't prove this and just have to take it as true, is that, if you multiply convergent sequences, they converge to the product of the limits. If you add and subtract convergent sequences, they converge to the difference of the limits and so on. So let's look at each of these terms one at a time. N over n minus 1, clearly that converges to 1. If you don't believe me, plug n over n minus 1 in for a very big value of n in your computer, and you'll see that it gets closer and closer to 1. Probably the easiest way to see this is it's 1 over 1 minus 1 over n, and that 1 over n clearly goes to 0. Okay, we just on the previous slide talked about how summation xi squared over n converges to sigma squared plus mu squared. So the second term converges to sigma squared plus mu squared. Then we have minus n over n minus 1, which again converges to 1. And then xm bar squared converges to mu squared. We talked about that on the previous slide. So we have this expression right here, sigma squared plus mu squared minus mu squared, which is just sigma squared. So that proves that the sample variance
converges to sigma squared, and then of course the sample variance if we happen to divide by the biased sample variance, if we happen to divide by n instead of n minus 1, also converges to sigma squared. And then we can square root the sample variance and get the sample standard deviation and see that it converges to sigma as well, just by the rule from the previous page where we said that functions, in this case the square root function of convergent random variables, converge to the function of the limit. So what we've found is we have our law of large numbers, and with a couple of rules that we just stipulated, we've got that the sample mean of IID random variables converges to the population mean that it's trying to estimate. The sample variance converges to the population variance that it's trying to estimate. The sample standard deviation converges to the population standard deviation that it's trying to estimate. And in all these cases, you see the pattern that the sample entity converges to the population quantity that it's trying to estimate, basically saying that if you go to the trouble of collecting an infinite amount of data, then you actually get the value that you want to estimate. You don't get it with noise, you get the actual value. We give this name a property, and we say that an estimator is consistent if it converges to what you want to estimate. And the law of large numbers is basically saying that the sample mean is consistent. And then we now know that the sample variance and the sample standard deviation are consistent, and it doesn't matter whether you're dividing by n or n minus 1, they're all consistent. But also remember that the sample mean and the sample variance are unbiased as well. And by the way, the sample standard deviation is not unbiased. Consistency, by the way, is a very weak property. So the sample standard deviation is biased, unlike the sample mean and the sample variance. Consistency is a very weak property. Saying that an estimator is consistent is not even really a necessary property. It seems like it should be necessary, but if something converges to mu plus epsilon, where epsilon is a minuscule number that is of no importance, then that estimator is not consistent. So it's fair to say that consistency is sort of a kind of a weakly necessary, but definitely not sufficient property for an estimator to be useful. We've also seen that being unbiased is neither necessary nor sufficient for an estimator to be useful either. For example, we talked about the bias variance trade-off, that estimators can be slightly biased, and you can want that because you improve on the variance. So what we're winding up with is a collection of properties that describe estimators, and you really need to think about the collection of properties as a whole to evaluate an estimator. And these various mathematical concepts are useful, but they never in isolation tell the full story on the utility of an estimator. They might be useful for eliminating really dumb things. If something's definitely not consistent in a way that it doesn't converge anywhere near the estimate, probably that's not something that you want to use. But apart from those kind of stark circumstances, these properties you need to take as a collection to try and decide which estimators are the right ones to use. So let me give an example of an estimator that's consistent but not very good. So take the data and only take the first half of the collected observations. So we have, instead of xn bar, we have xn over 2 bar, right? That estimator is, of course, consistent as n goes to infinity. It just has fewer observations than if you took all of them, but still the n is going to infinity. In this case, it's just n over 2. So that estimator is consistent, but it's got an obvious better estimator right in front of you, basically the estimator using all of the data. So there's a particular example of an estimator that's not consistent where there's a better estimator that comes to mind. Here you have to actually account for the fact that the estimate with all of the data has a lower variance than the estimate with half of the data. So that's enough discussion of limits and the law of large numbers. Next, we're going to go on to the central limit theorem, a very important theorem in statistics. Hi, welcome back to this lecture on asymptotics. We're going to talk about the central limit theorem, one of the most important and celebrated theorems in statistics. The idea behind the central limit theorem is very neat. It gives you a way to perform inference with random variables. We actually don't know what distribution they come from. And basically what the CLT states is that the distribution of averages of IID variables, properly normalized, becomes that of a standard normal as the sample size increases. It's basically saying is if you want to evaluate error rates associated with averages, it's often enough to only compare them relative to a normal distribution. And the CLT applies in an endless variety of settings. And with a collection of various asymptotic tools, people have figured out a way to apply the central limit theorem in so many cases. The majority of inference you do, if you've used statistical software and calculated a p-value or a confidence interval, probably the underlying motivation of what you're doing is asymptotics in most cases. Maybe not all cases, but definitely not all cases. But in most cases, you're probably appealing to some use of the central limit theorem, especially if you have larger sample sizes. Let's actually just state the central limit theorem, at least as far as we're going to use it. So let's let x1 to xn be a collection of IID random variables. They come from some population with mean mu and variance sigma squared. And let's let xn bar be their sample average. Then probabilities, and in this case, let's look at the distribution function. The distribution function of the normalized mean, so we take xn bar, subtract off its expected value, mu, and divide by its standard deviation, sigma over square root n. So this whole quantity here has mean 0 and variance 1. So this probability that this z random variable is less than or equal to the specific point z is the standard limits to the standard normal distribution evaluated at that point z. Okay, so what does this say? This basically says that probabilities associated with sample means look like probabilities associated with normals. And if you standardize the sample mean so that it has mean 0 and variance 1, then the probabilities look like standard normal probabilities. So I wanted to reiterate the form of this normalized quantity here. It's xm bar, an estimate, minus the population mean of the estimate divided by the standard error. Okay? And this is something that you can practically bank on, is if you take any statistical estimate based on IID data and subtract off its population mean and divide by its standard error, that quantity is most likely going to wind up limiting to having a standard normal distribution. Let's just go through an example. And this is kind of a neat example, and I'll explain why in a minute. Imagine if you were stuck on a desert island. And bear with me. Imagine if you needed a standard normal random variable. You had to generate a standard normal random variable because you were kind of going crazy. And all you had was a die. So you were thinking, I need a standard normal random variable, and I have a die. Let's roll the die a bunch of times and then take the standardized sample mean and see how well that works as a standard normal by applying the central limit theorem. So remember that for a die, the expected value of a die roll is 3.5. If you don't remember, we went through this calculation a couple lectures ago when we covered the variance. The variance of a die roll is 2.92. And the standard error is square root 2.92 divided by the number of die rolls going into the average. So that's 1.71 divided by square root n. And so the standardized mean would just be the average of the die rolls minus 3.5 divided by 1.71 divided by square root n. On the next slide, basically what I've done is I rolled the die, let's say one time, and I did that over and over and over again. So an average of 1, and I standardized the average of 1, right? So in this case, for an average of 1, it would be a die roll minus 3.5 divided by 1.71. So now we have a distribution that's centered at 0 and has variance 1. And I plotted the standard normal density in gray in the back, and I plotted the histogram of my die rolls. And of course, it can only take 6 possible values, and you see those 6 spikes at 1 to 6. And it's not perfectly discrete because the software I'm using to plot the histogram assumes the data is continuous. So you see the 6 spikes basically from the fact that one die roll, if we plot a histogram of a bunch of 1 die rolls, they're going to look like a bunch of spikes at 1 to 6. And in this case, because it was normalized, they're going to look like the numbers 1 to 6, where you subtract off 3.5 and divide by 1.71. Okay, now imagine if I just took 2 die rolls. I took a die, I rolled it once, I rolled it a second time, I got my average, I subtracted off 3.5, and I divided by 1.71 divided by square root 2. And I repeated that process over and over and over again, and I plotted a histogram of the result of a lot of averages of 2 die rolls. And so the histogram is going to give me a good sense of what the distribution of the average of 2 die rolls is, the standardized average of 2 die rolls is. And in the background, we have the normal distribution, and on top of it, we have the distribution of the average of 2 die rolls. And I think you'll agree that it's already, just by 2 die rolls, looking pretty good, amazingly good. And now imagine if you had 6 die rolls. So I rolled the dice 6 times, right? Took the average, subtracted 3.5, and then divided by 1.71 divided by square root 6, right? And then I did that process over and over and over again, and I got lots of normalized averages of 6 die rolls, and I plotted a histogram, and you can't even see the standard normal distribution in the background because the distribution of the average of 6 die rolls looks so similar. So if I was on my desert island and if I needed a standard normal, I think I could probably get away with 6 die rolls and taking an average, subtracting by 3.5 and dividing by 1.71 divided by square root 6. And the reason why I bring this up is because it's an interesting fact. The famous statistician Francis Galton, who was quite a character, you should look up Francis Galton if you get a chance. He was Charles Darwin's cousin. And he's a very brilliant guy. He needed standard normals, but he was trying to get to simulate standard normals prior to having computers. So how did he do it? Well, he basically rolled dice and applied the central limit theorem to get standard normals, which is really quite clever. And he had, because it was a pain in the butt, and he wasn't on a desert island, so he had time constraints, he actually invented dice that made it a little bit easier for him to do. I think he took standard dice and kind of wrote on the corners and stuff like that, so there was more values than 1 to 6. But the basic idea is that the distribution of averages looks like that of a normal distribution. And with kind of just about in any sense, regardless of what the underlying distribution of the data is, there's some assumptions there. We assume that the variance was finite and some other things like that. But for the purpose of this class, it's basically any distribution that we can probably think of. So let's take another version of the central limit theorem, or another instance of the central limit theorem from flipping coins. So now instead of a die, I have a coin, and I want to evaluate the average of a bunch of coin flips. So let's let xi be 0 or 1 result of the ith coin flip of a possibly unfair coin where the p is the true success probability of the coin. And the sample proportion, say p hat, is just the average of the coin flips, right? The p hat is, in this case, the percentage of ones, and the average of the xi is the same thing, of course. So remember that the expected value of the xi's is p, right? The true success probability of the coin. And the variance of the xi's works out to be p times 1 minus p. And then the standard error of the mean in this case is the variance divided by square root n. So it's p times 1 minus p divided by n square root the whole thing. So then what this says is that if we take a sample proportion, p hat, we subtract off the population proportion, the success probability, the probability of getting ahead, and divided by square root p times 1 minus p divided by n, that'll be approximately normally distributed. And things look worse than the die roll in this case. Let's take a fair coin and generate some plots. So if you take a fair coin and flip the coin and record either 0 or 1, depending on whether it's heads or tails, subtract off 0.5, and divide by square root 0.5 times 1 minus 0.5, and do that over and over again and get a histogram of the results. You only get 2 possible values, right? They're not 0 or 1 because you've normalized them. And here in this first plot, you see it doesn't look normal at all, of course. After 10 coin flips, so here now we're flipping the coin 10 times, taking the sample proportion of heads, subtracting off 0.5, and then dividing by 0.5 times 1 minus 0.5 divided by 10, square root of that whole thing. And we repeat that process over and over and over again and get a histogram of the results. We see that the distribution of the normalized average of 10 coin flips looks pretty normally distributed, but still it's very discrete compared to the normal distribution. Once you get to 20 coin flips, it's looking pretty good. It's overlaying the standard normal distribution pretty well. And it turns out in the coin flipping example, it converges to normality quick if the coin is fair. If the coin is unfair, if you see the bottom row of plots, here we have a coin that's unfair where it's more likely to get a tail than a head. I think it's 0.7, 0.3, I believe is what I used for the simulation. Then you see that, at the start, it's much more likely to get the 0 value than the head value, the 1 value. These aren't 0 and 1 because they've been normalized. If you look at the distribution of averages of 10 coin flips, it doesn't look very normal at all. 20 coin flips, it still doesn't look very normal. So it takes a lot longer. So this is a problem with the central limit theorem that generally doesn't get a lot of play. The central limit theorem says basically if you have IID random variables and you take an average, the distribution of the normalized average converges to that of a Gaussian distribution. But it doesn't tell you how fast it does that, right? It just tells you that it does eventually. So for some distributions, it might take thousands of observations going into the sample mean for the distribution of sample means to behave like that of a Gaussian distribution. And for others, like the die roll, we saw that it only took 6, and then it was nearly overlaying the standard normal distribution. So, it's an unfortunate fact that the central limit theorem can't give you any guarantees on how quickly things converge to normality. Oh, and I wanted to point out one last thing on this coin flipping example. So if you've ever been to a science museum and you've seen these machines where, say, a ping pong ball is dropped and it goes through like kind of a pachinko collection of left-right decisions kind of randomly, that's exactly a binomial experiment. Every time the ping pong ball hits a nail, basically, it can either kind of with a 50% probability go left or right. And so by the end of the process, it's had a bunch of coin flips. And so the position it is at the bottom is exactly the sum of a bunch of Bernoulli trials in principle. You have to actually create it so that it approximates the coin flipping well. For example, if it was tilted to the side, it wouldn't be a fair coin anymore. But as it gets towards the bottom where the ping pong balls are collected, it's a sum of a bunch of Bernoulli random variables. Well, the distribution of averages is approximately Gaussian, so of course the distribution of sums is then approximately Gaussian because sums are just averages multiplied by n. So what you'll see in the Science Museum is that in the bottom they'll have traced out a Gaussian distribution, and you'll see that if they run this ping pong ball machine long enough, the balls tend to fall in a bell-shaped curve. And that's just an application of the central limit theorem saying that for this particular value of n, the central limit theorem approximation of the sum of a bunch of coin flips is pretty good. And this ping pong ball device is actually called a quincunx, and it was invented by Francis Galton, who we talked about earlier, the cousin of Charles Darwin. So it's kind of a very interesting little tidbit. So the next time you're at the Science Museum, you can explain this to whoever you're with. So the reason we use the central limit theorem in practice, it's useful as an approximation, basically saying that the normalized mean, it has a distribution that's approximately like the standard normal distribution. So let me give you an example. So remember that 1.96 is a good approximation to the 0.975th quantile of a standard normal. And so negative 1.96 is a pretty good approximation to the 2.5th percentile. So what the central limit theorem then says is that 95% is about the probability that a standardized mean lies between basically -2 and +2. So let me just repeat that. So it's about 95% the probability that a standardized mean lies between the values -2 and +2. And then so let's take the interior of this probability statement and just rearrange terms a little bit, making sure that if we multiply everything by a minus sign, we flip the inequalities. And we get that xm bar plus 1.96 sigma over square root n is bigger than or equal to mu, which is greater than or equal to xm bar minus 1.96 sigma over square root n. That probability is about 0.95. What that's saying is that the random interval xm bar plus or minus 2 standard errors contains mu, the non-random entity, with about 95% probability. In this case, we wanted let's say a 95% interval. So we took 5%, divided it by 2, and got 2.5 in the 97.5th quantiles. basically add and subtracted those xm bar plus or minus that quantile times the standard error. So that's 95%, but if we wanted something other than 95%, why don't we just say the standard normal quantile z at 1 minus alpha over 2. So in this case, it was 1 minus alpha is 0.05 divided by 2. That's 0.025, so that would be 0.975. So that would be z 0.975, which is 1.96. So that's where we got the 1.96 from. But we could do it for another value. Imagine if you wanted a 90% interval, right? Then we would have z, the quantile for the probability, 1 minus alpha in this case, which would be 0.1 divided by 2. So 0.1 divided by 2 is 0.05. So we need the 95th percentile to plug in there if we wanted a 90% interval. Okay, so this is the idea that we can create so-called confidence intervals, random intervals that contain the quantity that they're trying to estimate with 95% probability, with 1 minus alpha over 2% probability. We can create such quantities by taking the estimate plus or minus a standard normal quantile times the standard error. And in this case, it's the sample mean. But we'll find that we can kind of trick and play games with the central limit theorem and the law of large numbers and get this kind of interval to work in a lot of cases. So tons of the intervals that you're going to look at in your statistics classes are going to be exactly of the form estimate plus or minus standard normal quantile times standard error. Anyway, this is called a 95% confidence interval. It's a mainstay of statistics, and especially so-called frequentist statistics. And it's basically an estimate for mu that has some acknowledgement of the uncertainty from the fact that we have data that we're treating as if it's random. So that's what a confidence interval is. If we just give xm bar, we just give the sample average as an estimate, that has no acknowledgement that there's random variation and that we're not accounting for. So in this case, we're saying, well, if we take xm bar and we're willing to assume that the data is independent and identically distributed with a finite variance, then we can apply the central limit theorem. And the central limit theorem says that, well, if the distribution is cooperating and n is large enough, then the interval contains mu with probability 95%. Now, unfortunately, I'm going to pontificate a little bit. It's an unfortunate fact that confidence intervals are kind of really horribly hard to interpret. And this is just a byproduct of so-called frequentist inference. So the interval, if we actually get data and calculate a confidence interval, then we just have two numbers. Those two numbers either contain mu or they don't. So the standard frequentist logic says that the probability that that interval contains mu or not is either 0 or 1. It either contains it or it doesn't. So what the real interpretation of a confidence interval is that this procedure, when applied over and over again, creates confidence intervals that will contain mu 95% of the time. So that's actually the real interpretation of a confidence interval if you are a hardball frequentist. And it's unfortunate that that interpretation is so hard. So let me just repeat it because it is kind of tricky. It's basically saying that the confidence interval procedure, given that the central limit theorem applies and all of our assumptions apply, the confidence interval procedure creates intervals that if we are to repeat the procedure over and over and over again on repeated experiments, let's say for 95% intervals, about 95% of the time the intervals will contain the value that they're trying to estimate. That's a very confusing statement, and that's one of the main criticisms of confidence intervals, that if you're strict about their interpretation, which not everyone's strict about it because the strict interpretation is so hard, that it's actually quite difficult. Maybe I'll try and dig up some examples when a confidence interval makes its way into some very important problem and show you how the press is basically incapable of interpreting intervals this way. And to their credit, it's because it's hard and it's kind of a crazy interpretation. There is, in fact, a different way of creating intervals that gives you a better interpretation. There's another trick. If you happen to be taking a statistics test, there's a trick to get around this mental games associated with fictitious repetitions of experiments and so on. The trick is just to say, we're 95% confident the interval contains mu. And statisticians have said, well, that's enough hedging to count as a legitimate instance of the strict definition. So if you're taking a statistics test, don't say there's a 95% chance that the interval that I just calculated contains mu, because your teacher might yell at you about that. But if you say you're 95% confident, they'll begrudgingly give you credit. Let me give you another formula that I find super useful, a super useful instance of the CLT, because it's a kind of quick back of the envelope type calculation. So by the way, we're going to spend much more time calculating specific confidence intervals and so on. Right now, we just wanted to give you the theory behind why confidence intervals work. But there's a specific instance of confidence intervals that's really quite useful. So for sample proportions, remember the variance is p times 1 minus p. And so the confidence interval, just plugging in, takes the form p hat, the sample proportion, plus or minus the standard normal quantile, times square root p times 1 minus p over n. Now, in all of the intervals, p is what we want to estimate, so we obviously can't plug into this formula. We need to replace p with an estimate. If we replace p with the sample proportion, p hat, 1 minus p hat, you get a so-called walled interval, and as I stated in this previous slide but didn't really talk about, you generally replacing the unknown parameters in the standard error calculation with their estimates will usually work with something that's called Slutsky's theorem. And that will usually work and will create an interval that's asymptotically valid. Let's try and, instead of doing that right now, we'll talk a lot more about walled intervals and that sort of thing. Let's actually talk right now about quick back of the envelope bounds. So remember that the worst that p times 1 minus p can be, the biggest it can be, is if p is a half. So this thing is less than or equal to a quarter, as long as p is between 0 and 1, which is our restrictions because we're talking about a proportion or a probability. So in this case, if we let alpha be 0.05 so that the standard normal quantile is 1.96, which is close enough to 2, among friends, let's just call it 2, then the standard error, the whole kind of margin of error part of the confidence interval, 2 square root p 1 minus p over n, works out to be 2 times square root a quarter divided by n, and so you wind up with 1 over square root n. So if you want a quick back of the envelope confidence interval estimate for a sample proportion, just take the sample proportion and add and subtract 1 over square root n. And that's a really handy little formula. And it kind of tells you sort of when you calculate a proportion about how accurate it is. So for example, if I have a proportion of 100 coin flips, we know that the accuracy is going to be about 1 over square root 100 or 0.1. So it's a very useful little back of the envelope calculation. Just remember p hat plus or minus 1 over square root n. Well, that's the end of today's lecture on asymptopia. I hope you enjoyed your visit to asymptopia. It's a very nice place. When you have an infinite amount of data, things tend to work out. I look forward to seeing you next time. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 9 on confidence intervals. In this lecture, we're going to talk about confidence intervals, mostly in the setting where we're going to assume that our data come from a Gaussian distribution. So we'll talk about confidence intervals for variance, we'll talk about Gosset's t distribution, and we'll use Gosset's t distribution to create confidence intervals for means. And we'll touch on the subject of profile likelihoods. In the last lecture, we talked a little bit about the central limit theorem, and we talked about using the central limit theorem to create a confidence interval. I think in that example, we created a confidence interval for a binomial proportion. Now we'll discuss the creation of better confidence intervals for small samples using Gosset's t distribution, small samples where we're willing to treat the data as if it's continuous. So to get to that point, and Gosset's t distribution is often called student's t distribution, and we'll explain why in a little bit. So to discuss the t distribution, we first have to go through what the chi-squared distribution is, and so we'll develop that first. And at any rate, what you'll probably hopefully have noticed whenever we create confidence intervals, there seems to be some kind of prevailing logic that we use. Basically, we try to create a probability statement, and then we, in a sense, manipulate that probability statement to generate an interval. Well, this strategy is codified here. So basically, we create a pivot or a statistic that doesn't depend on the parameter of interest.
I should say we create a pivot or a statistic whose distribution doesn't depend on the parameter of interest. So, for example, if you use the central limit theorem, if you take a sample mean, subtract off the population mean that you're interested in, and divide by the standard error, well, that statistic clearly depends on the parameter of interest, but the distribution of that statistic, at least in the limit, doesn't depend on the parameter that you're interested in, the sample mean. And then after we've created that pivot, we solve the probability that the pivot lies between bounds for the parameter. And so that's the kind of general strategy we'll go through. You don't have to really know or really understand this strategy at a very general level, but just in case you're wondering, why does it always seem like we're generating confidence intervals using basically exactly the same technique? It's because we're employing a strategy kind of like this. So let's talk about the chi-squared distribution. So remember that S squared is the notation we've been using for the sample variance. And let's further assume that the data that comprise the sample variance are all IID, normal with mean mu and variance sigma squared. Well, then n minus 1 times the sample variance divided by sigma squared is a random variable that we call a chi-squared distribution, and the chi-squared distribution has an index, something that differentiates between different kinds of chi-squared distribution, and we call that index the degrees of freedom. So this statement right here will be read: the normalized sample variance follows a chi-squared distribution with n minus 1 degrees of freedom. So the chi-squared distribution is a skewed distribution, and it, of course, since the sample variance has to be positive, it has support between 0 and infinity. And the mean of the chi-squared distribution is its degrees of freedom. And we can see that very directly because we recall the sample variance is an unbiased estimator. That's why we divide by n minus 1 instead of n. So if you look at this equation, when you take the expected value of s squared is sigma squared, you can see that expected value of n minus 1 s squared divided by sigma squared, the sigma squareds would cancel out and you'll get that degrees of freedom are its expected value. The variance of the chi-squared, by the way, is twice the degrees of freedom. As an aside, we're not actually going to spend a lot of time doing this, but as an aside, you can use this idea to create a confidence interval for the variance. So imagine if I were to draw a chi-squared density, and chi-squared n minus 1 alpha is the alpha quantile from that distribution. Then imagine taking the, say, alpha over 2, let's take alpha to be 0.05, for example, the 2.5th percentile and the 97.5th percentile from the chi-squared distribution, and looking at the probability that this chi-squared random variable n minus 1 s squared over sigma squared is between those two quantiles, well, that has to be 1 minus alpha, just by the definition of those being the 2.5th and 97.5th quantiles of the chi-squared distribution. So this equality holds the equality that 1 minus alpha equals this probability. So this statistic, n minus 1 s squared over sigma squared, is our pivot. Let's solve for the parameter that we're interested in, sigma squared, and you do that, keep track of your inequalities, being sure to flip them if you invert everything and that sort of thing, and you wind up with the following probability statement. There's a 1 minus alpha probability that the random interval n minus 1 s squared divided by the upper quantile and n minus 1 s squared divided by the lower quantile contains sigma squared. So we call this interval, the n minus 1 s squared divided by the two quantiles, we call that interval a confidence interval for sigma squared. And because the probability that the random interval contains the parameter it's estimating is 1 minus alpha, we call it, say, a 100 times 1 minus alpha percent confidence interval. So as an example, alpha might be 0.05, and so you then wind up with a 95% confidence interval for the parameter sigma squared. Now we should talk a little bit about what this confidence interval means. It's the interval that's random. In the paradigm that we're sort of thinking about here, the interval is random and the parameter sigma squared is fixed. So when you actually collect data and you form this confidence interval, it either contains sigma squared, which you don't know, or not. There's no probability with that statement anymore. It's either 1 or 0. It either contains sigma squared or not. So what's the actual interpretation of a confidence interval? Well, if you take an intro stat class, they make a lot of hay out of this point,
And they basically say, okay, the confidence interval is a procedure that if you were to repeatedly do the experiment and form confidence intervals, 95% of the confidence intervals, say if you're creating 95% confidence intervals, 95% of the confidence intervals would contain the parameter that you're interested in. And you could, as an example, do this in R. You could generate normal data. You could, from a normal, let's say mu is 0, from a normal 0 sigma squared distribution, you could formulate this confidence interval from the sample variance. You could check whether or not that interval contained the sigma squared that you used for simulation. And then you could repeat that process over and over and over again. And you will find that about 95% of the intervals that you get, if you construct 95% confidence intervals, will contain the sigma squared that you used for simulation. And that's the logic behind confidence intervals. And they're a little notoriously hard to interpret if you go for this sort of hardball interpretation. They're notoriously hard to interpret. Kind of a much weaker interpretation of the confidence interval that's a little less specific is you get two numbers out, and these two numbers are an interval estimate of the parameter that you want to estimate, but the interval estimate incorporates uncertainty. So let's go through a couple of comments about this interval. So one thing is this interval is not terribly robust to departures from normality. So if your data is not normal, then this confidence interval tends to not be that great. Also, if you want a confidence interval for the standard deviation instead of the confidence interval for the variance, you just square root the endpoints of the interval. The probability statement 1 minus alpha equal to the probability that the random interval contains sigma squared, well, you can still say that that's 1 minus alpha is equal to the probability that the square root of the endpoints of the interval contains sigma, and you haven't mathematically changed anything. So if you want an interval for sigma, you just square root the endpoints. So you might be wondering, okay, well, if this is heavily requires normality, do we have any other solutions other than this interval if we want a confidence interval for the variance? And it turns out the answer is yes, and there's several ways, but bootstrapping is kind of the way that I prefer. But we're not going to talk about bootstrapping in today's lecture. So today we're only going to talk about this confidence interval when you happen to be willing to stomach the assumption that your data is exactly Gaussian and you are willing to live with the consequence that the interval that you obtain is not going to be terribly robust to departures from that assumption. So the other thing I wanted to mention, it's kind of a nifty little point, is suppose you wanted to create a likelihood for sigma. And in this case, the underlying data is Gaussian with mean mu and variance sigma squared. So it's hard because you have two parameters. The likelihood is a bivariate function, right? It has mu on one axis, sigma on the other axis, and then the likelihood on the vertical axis. So there's a little trick you can use to create, I guess, what I would call a marginal likelihood for sigma squared. It turns out, and we're not going to cover the mathematics behind this, but that if you don't divide by sigma squared, n minus 1 s squared, and then don't divide by sigma squared, well, first of all, that can't be chi squared. Let me just logic through that real quick. That can't be chi squared because the chi squared density doesn't have any units, right? So s squared has whatever units the original data has, say it's in inches, it has inches squared units. So you haven't divided by anything that's in inches squared. So n minus 1 s squared has inches squared units. And so it can't follow a distribution that's unitless like the chi-squared distribution. That's one of the reasons why you have to remember to divide by sigma squared to get the chi-squared distribution, is you get rid of the units. Well, let's suppose we don't divide by sigma squared. Then you wind up with a gamma, and a so-called gamma distribution. And the gamma is indexed by two parameters, its shape parameter and its scale parameter. In this case, the shape parameter is n minus 1 over 2, and the scale parameter is 2 sigma squared. And either way, what you have is data. You have a single number, n minus 1 s squared. And if you're willing to assume the data points that comprise that number are Gaussian, then you can take the gamma density and plug in the data and view it as a function of the parameters and plot a likelihood function. So I'll go through an example of doing this. So in our organo-lead manufacturing workers example that we looked at before, there was an average total brain volume of 1,150 cubic centimeters with a standard deviation of 105.977.
And let's assume normality of the underlying measurements, which is not the case, but let's do it. And let's calculate a confidence interval for the population of variation in total brain volume. I give the R code here. So I gave the standard deviation. So our variance is 105.106 squared. Our N in this case is 513. Confidence interval, we want a 95% confidence interval, so our alpha is 0.05. The quantiles that we want, we can just use the Q chi SQ function to grab those quantiles. This function right here just grabs the two quantiles. And then our interval is just n minus 1 s squared, the s squared divided by the quantiles. And then this puts it out from bigger to smaller. I want it from smaller to bigger, so I use the REV function to reverse it. I think if I had just input my quantiles in the reverse direction, I would have been okay, too. And then here, just take the square root of that interval for an interval for the standard deviation, and we get the interval is about 100 to 113. So this interval, 100 to 113, is created in a way such that if the assumptions of the interval are correct, namely that the underlying data are IID, normal with a fixed variance sigma squared and a fixed mean mu, then the procedure, if repeated over and over again, 95% of the intervals that we obtain would be intervals containing the true standard deviation that we're trying to estimate. Let's actually plot the likelihood as well using this kind of likelihood trick that I gave. So sigma vals is the sequence that I want to plot. And actually, I don't have to guess this because I just created this confidence interval on the previous page that went from 100 to 113. So let's, for good measure, go from 90 to 120, and I want to plot 1,000 points. In R, you kind of have to actually be pretty specific about the range that you want to plot and how many points you want going into your plot. And then I just give you the code here for evaluating the gamma likelihood. It says basically plug in the data, n minus 1 s squared, right? And remember the likelihood views that as fixed. The shape doesn't involve anything other than things we know, n minus 1 over 2. And then the scale is the part that varies, 2 sigma squared. And here we're going to evaluate it over all the sigma vals that I assigned in the previous line. So this will evaluate that likelihood over 1,000 points and return a vector of length 1,000. I want to normalize my likelihood, and I'll just kind of, mostly approximately do that by taking this vector and dividing by its maximum value. And then I'll plot it. Type equals L means plot it as a line instead of as a bunch of points. And then these two lines commands adds the 1/8 and 1/16 reference lines. And then on the next page, you actually see the marginal likelihood for sigma. That's a whirlwind tour of creating confidence intervals and likelihood plots for variances when you're willing to assume your data is exactly Gaussian. I hesitate to say this, but kind of those slides aren't exactly terribly useful material. You won't find a lot of people plotting marginal likelihoods for sigma. I just gave it to you because it's kind of a nifty little result. And to be honest, the Gaussian confidence interval for variances, you don't see them as much. People just would tend to do bootstrapping these days instead, or some other more robust technique. So this material, it's neat, and it's the primary thing to do was actually introduce the chi-squared distribution. So next, we're going to talk about something that's incredibly useful, probably one of the single most used distributions and techniques in all of statistics. Okay, welcome back, troops. We're going to start talking about student, or as I like to say, Gosset's t-distribution. So the reason I call it Gosset's t-distribution is it's usually called student's t-distribution because Gosset published under the pseudonym student in 1908. So it was actually Gosset's distribution. He laid the groundwork for the actual distribution, and then I believe Fisher actually proved the mathematics, some of the finer scale mathematics. But I wanted to talk a minute about Gosset because he's a pretty interesting character in the annals of statistics. So Gosset was a researcher, and he worked at the Guinness Brewery in Ireland. And when he created the t-distribution, he was actually working for Guinness. And at the time, he had actually several really brilliant researchers working for him, and he wouldn't let them publish under their real names. So that's how Gosset wound up publishing under a pseudonym and made this sort of landmark discovery as a researcher. It's interesting. So the reason he came up with this distribution is because for him, the central limit theorem just was simply not rich enough to describe the problems he was looking at. So he was working with these small batches in the science of brew making, and it wasn't adequate to assume that things were heading to infinity. So he came up with this distribution, and we're all the more fortunate for it. One thing I really like about Gossett is whenever you read about him, he was apparently a tremendously nice guy, extremely humble. He made several major discoveries in statistics. He came up with one of the first uses of the Poisson distribution. And then he also, in the Guinness company, he rose up pretty high. He was a head brewmaster at I think it's London brewery by the time he had retired. So anyway, he's a really interesting character. And if you get a chance, you should read about him. At any rate, so he came up with this wonderful distribution called, as far as I'd like it to be called, Gossett's t-distribution. And the t-distribution is really kind of used when you have smaller sample sizes. It assumes your data is Gaussian, but it tends to work even if your data is non-Gaussian. And so the t-distribution, it has degrees of freedom. It's indexed by something called degrees of freedom. And the t-distribution, which looks like a normal distribution where someone kind of squashed it down at its tip and all the extra mass went out into its tails, well, it looks more and more like a standard normal as the degrees of freedom get larger and larger. So how do you get a t-distribution? Say you wanted to simulate it on a computer. You would take a standard normal, say z here, and you would divide it by an independent chi-squared divided by its degrees of freedom. So where z and chi-squared here are independent standard normal and chi-squared random variables, that's how you wind up with a t-distribution. So how's this useful? On the next slide, we'll look at how we apply this. Well, let's suppose x1 to xn are IID normal mu sigma squared. Then x bar minus mu divided by sigma over square root n is, of course, standard normal, right? Because linear combinations of normal random variables are themselves normal. So in this case, x bar is normal. And because they're IID, we know exactly what the standard deviation of x bar is. It's sigma over square root n, and we know that its mean is mu. And so when we shift and scale our non-standard normal by mu and divide it by its standard deviation, sigma over square root n, we get a standard normal. Hopefully this should not be news to you at this point in the class. And then we also know from earlier on in today's lecture that n minus 1 s squared over sigma squared is chi squared with n minus 1 degrees of freedom. So if we take n minus 1 s squared over sigma squared and divide it by an additional n minus 1 and square root the whole thing, we get s over sigma, and we've taken a chi squared and divided it by its degrees of freedom. So s over sigma is the square root of a chi squared divided by its degrees of freedom. Therefore, if we take x bar minus mu divided by sigma over square root n, and then divide the whole thing by s over sigma, which if we do the arithmetic works out to be x bar minus mu divided by s over square root n, we wind up with a standard normal divided by a square root of a chi squared divided by its degrees of freedom. Now, there's one small thing that we're kind of fudging over. We haven't showed that the x bar and s are independent, right? They're from the same data, so it doesn't seem obvious that they're independent. They are. It's just not immediately clear. And let's sweep that under the rug. So forget about that for the time being. Take my word for it. X bar and s are independent, so this exactly has Gossett's t-distribution with n minus 1 degrees of freedom. And notice what it basically accomplishes. So we saw previously in constructing confidence intervals that x bar minus mu divided by sigma over square root n, that's, you know, a nice kind of pivotal statistic to work with. It's useful for generating confidence intervals. We'll see that it's useful for doing hypothesis tests. And all we've done is replace sigma by s. And it's basically saying that we can take the unknown population variance and replace it with the known sample variance, and we get a statistic whose distribution we know, okay? And by the way, this statistic, x bar minus mu s over square root n, it also limits to a standard normal as n goes to infinity, which, you know, of course, the Gossett's t-distribution is the degrees of freedom goes to infinity. If you look at it, if you plot it, it looks more and more like a normal distribution as n goes to infinity. So we haven't violated the central limit theorem or anything like that in the process of doing this stuff. So let's actually use this distribution to create a confidence interval. It's a statistic who, under the assumption of normality of the underlying data, does not depend on the parameter mu that we're interested in, and therefore we can use it to create a confidence interval for mu. So let's let t df alpha be the alphath quantile of the t distribution. So t n minus 1, 1 minus alpha over 2 is, say, the upper quantile from the relevant t distribution, and t n minus 1 alpha over 2 is the lower quantile from the relevant t distribution. And so this probability statement here, 1 minus alpha, is equal to the probability that this statistic lies between those two confidence intervals, is then, of course, true, right? So the probability that this t random variable lies between the alpha over 2 lower quantile and the 1 minus alpha over 2 upper quantile is exactly 1 minus alpha. Oh, and I should note here, by the way, because the t distribution is symmetric, the alpha over 2 lower quantile is equal to the negative of the 1 minus alpha over 2 upper quantile. This is because the t distribution is symmetric about 0. So that's why here, instead of writing alpha over 2, I wrote negative t n minus 1, 1 minus alpha over 2. And you'll see why I do that in a second. So anyway, this probability statement applies here. So we can just rearrange terms and keep track of flipping our inequalities around when we multiply by a negative sign. And we get that x bar minus a t quantile times the standard error is less than mu, and x bar plus a t quantile times the standard error is bigger than the mu. That random interval contains mu with probability 1 minus alpha. But if you look at the form of this interval when I wrote it out this way, that happens to be x bar plus and minus the upper quantile from the t distribution times the standard error. And that's why I took only the upper quantile. That way we can write it as plus minus. Okay, so that's how we wind up with these intervals. Estimate plus or minus quantile times standard error. And that's where it comes from. This interval assumes that the data are IID normal, though it's very robust to this assumption. You know, whenever the data is kind of roughly symmetric and mound-shaped, the t confidence interval works amazingly well. And if you want, if you have paired observations, people before and after a treatment, for example, you can subtract them and then create a t confidence interval on the difference. So often paired observations are analyzed using this exact confidence interval technique by taking differences. And often differences tend to be much more Gaussian looking. They tend to be nice and symmetric about 0. And then for large degrees of freedom, the t quantiles become the same as the standard normal quantiles. And so this interval just converges to the same interval that you get as the CLT. Some more notes. For skewed distributions, the kind of spirit of the t-interval assumptions are violated. You could probably show that it still works kind of okay. And the reason is because those quantiles, the t n minus 1, 1 minus alpha over 2, the quantiles are so far out there. The t distribution is a very heavy tailed distribution that shoves those quantiles way out there. That makes the interval a lot wider, and then it tends to work kind of conservatively in a broad variety of settings. But for skewed distributions, you're kind of violating the spirit of the t-interval, and you're often better off, trying some things like taking a natural log of your data if it's positive to get it to be more Gaussian looking before you do a t confidence interval. And we'll spend an entire lecture on the consequences of logging data, so you can wait for that. But I would just say for skewed distribution, it kind of violates the intent of the t-interval, so maybe think of things like doing logs to consider it. And also I would say for skewed distributions, maybe it doesn't make as much sense to center to the interval around its mean in the way that we're doing with this t-interval. We're centering it right around the mean. And then the other thing, for discrete data, like binary data, again, you could probably, I bet you could do simulation studies and show that the t-interval, actually probably works okay for discrete data like binary data. But, we have lots of techniques for binary data that make direct use of the binary data. And you're better off for those using, for example, things based on chi-squareds or exact binomial intervals and that sort of thing, because you're so far from kind of the spirit and intent of the t-interval that it's not worth using. Regardless,
The t-interval is an incredibly handy tool. And I'm sure actually in some of these cases it probably works fine, but you're so far from the kind of assumptions at that point that you're better off using all these other techniques that have been developed for these other cases. That's enough discussion about the t-confidence interval. Let's go through an example. So maybe take a break, go have a Guinness, and we'll be back in a second. Okay, so welcome back. So we're going to talk about Guinness's original data, which involves sleep data. So try not to fall asleep while we're talking about it. So Gossett's original data appeared in this journal called Biometrica, with a K. And Biometrica, interestingly enough, was founded by a person called Francis Galton. So Gossett was an interesting character. If you really want to read up on another, absolutely brilliant, interesting character, read up on Gossett. He was Charles Darwin's cousin. He invented the term and the concept regression. He, invented the term and the concept correlation. And he invented lots of other things, some good, some bad. And he was just a generally rather interesting character. So anyway, Biometrica was founded by Francis Galton, and that is where Gossett's original paper appeared, and that's where this sleep data occurred. So at any rate, the sleep data shows the increase in hours slept for 10 patients on 2 sleeping drugs. So R treats the data as 2 groups rather than paired, and I have to admit I haven't taken the time to go through and figure out exactly why there's a discrepancy between when you read Gossett's Biometrica paper, which treats the data as paired, and R treats it as 2 groups. And anyway, I haven't gone through the details, so I'm going to treat it exactly like Gossett's data. So here's what it looks like as Gossett's data. So we have patient 1 to up to 10. We have the 2 drugs and the difference. And here's the code I used to get it that way. So the mean would be the mean of the difference, and here I just put in a comment the value that it comes out to be. It turns out to be 1.67. And this is, remember, everything's normalized relative to 10 hours. And then the standard deviation was the standard deviation of the collection of differences is 1.13, and we had 10 subjects. So our confidence interval is the mean plus or minus the t quantile at 0.975 if we want a 95% confidence interval, because remember we put 2.5% in either tail, times the standard error, which is s divided by square root n. And this will give you our confidence interval manually, but if you want to go the easier way, R actually has a function, of course, to do the t confidence intervals because it's one of the most popular statistical procedures. So if you do t dot test, and here difference is the name of the vector that contains the differences. And then this $ here grabs the relevant output. So in this case, I want the confidence interval. So it's $conf.in. If you omitted the $ when you hit return, it would give you lots of information, including the confidence interval. Here, it just returns exactly the confidence interval. And you get 0.7 to 2.5, basically. We've talked a lot about likelihoods, so I wanted to talk about how you can use the t-distribution to create a likelihood for not mu. So remember, we're in this kind of hard setting where we have a data that have 2 parameters, mu and sigma. The likelihood inherently is a 2-dimensional object. And we showed, you can get a trick and figure out how to get a likelihood for sigma. And here I'm going to say, well, here you can do another trick and get another likelihood for a single parameter, but the single parameter is a function of the 2 parameters. So in this, the single parameter is mu divided by sigma, which is actually quite an important parameter. Mu divided by sigma is the mean in standard deviation units. So it's a unit-free quantity, and it's often called the effect size. And this is a nifty little trick to create a likelihood for the effect size. So if x is normal mu sigma squared, and then this chi-squared random variable is a chi-squared random variable with df degrees of freedom, then if you take x divided by sigma and divide it by the square root of a chi-squared divided by its degrees of freedom, then notice we forgot to subtract off mu in the top. So x over sigma still has a mean. In this case, its mean is specifically mu over sigma. So we've not taken a standard normal and divided by an independent square root of an independent chi-squared divided by its degrees of freedom. We took a non-standard normal and divided by a square root of an independent chi-squared divided by its degrees of freedom. Well, so it can't work out to be a t random variable because we haven't satisfied the definition of a t random variable. So it's what's called a non-central t random variable. And in the specific case when mu is 0, we wind up with a t random variable. And this non-central t random variable also has degrees of freedom, but then it has a second parameter called the non-centrality parameter. In this case, the non-centrality parameter is mu over sigma. So just to put this in context, x bar is normal mu with variance sigma squared over n minus 1 s squared over sigma squared is a chi-squared with n minus 1 over n minus 1 degrees of freedom. So square root n x bar divided by s works out to be a non-central t with non-centrality parameter square root n mu divided by sigma. At any rate, we can use this fact to create a likelihood for mu over sigma, the effects, basically what is called the effect size. And we can plot a one-dimensional likelihood without having to do any further tricks. And then after this, I'll talk about how you can do a trick to avoid all these little, figuring out a likelihood for the effect size and figuring out a likelihood for the variance are sort of, you'd have to kind of take a math stat class to figure those out. What we'll talk about next in profile likelihood is a quick way to always generate a likelihood in any setting in a fairly automatic way. So anyway, here's how you would create the interval. So here our t statistic is square root n times the mean divided by s, just using the code from the sleep data. The effect size values that we want to plot is, let's say we go from 0 to 1 and our length is 1,000. Our likelihood values are then the t density. In this case, r's dt function, t density function, has an argument ncp, which stands for non-centrality parameter. So here we have our t density. We plug in our t statistic. Our degrees of freedom are n minus 1. And then we loop over all of our non-centrality effect sizes. And that creates a collection of likelihood values. And then we want our likelihood values to be peaked at 1. So instead of figuring out what the exact maximum likelihood is, let's just divide by the maximum when we grid searched over 1,000 points. And let's plot our effect size values by our likelihood values. Let's make sure it's aligned by doing type equals L. And let's draw lines at 1/8 and 1/16. And we wind up with this plot. So this plot is a likelihood not for mu, but for mu divided by sigma. And it has all of the same interpretations of any likelihood. Higher values indicate better supportive values of mu over sigma. Lower values of likelihood indicate worse values. And where the two lines intersect the likelihood represent intervals for the effect size. So that's maybe enough about the effect size, and that's a fairly specific thing. That's not something you'll see in many, say, introductory stats textbooks. I just thought I'd give it because it's kind of neat. Next, we'll talk about a way for creating a likelihood when you have a multivariate likelihood, creating a univariate likelihood to look at. So welcome back. The final thing we're going to do in today's lecture is to talk about the profile likelihood, which is a method for creating univariate likelihoods from multivariate likelihoods. And in this case, we're going to look at the bivariate normal distribution, which has two parameters, mu and sigma. And we're going to figure out how to get likelihoods for mu alone, and you could equivalently do it to get likelihoods for sigma alone. And here's the idea. The multivariate likelihood is a bivariate surface. It has mu on one axis, sigma on another axis, and this surface above it. And to obtain a likelihood for mu, profiling is basically like, let's imagine we took a lamp and shined it along the sigma direction and looked at the shadow that the likelihood placed on the plane defined by the mu direction. And that's exactly what it gives. So its name is exactly indicative of the technique. And then now we'll just go through how do you actually execute the mathematics to do that. So in other words, we want to shine a light on this bivariate likelihood, and we want to get the function that you obtain onto, say, the wall where the shadow occurs. Okay, so let's pick a particular value of mu naught, and we want to know what's the value of this curve in the shadow at mu naught. Well, basically, the light will go through all values above the likelihood and will get stopped anywhere on the likelihood and up until the maximum value. And so what we basically do is we maximize the joint likelihood for sigma with mu fixed at mu naught. And then this process is repeated for lots of values at mu naught. So let's actually go through it. So the joint likelihood with mu fixed at mu naught is just the Gaussian density, and then we have independent data, so we take a product out front. So it's sigma squared to the minus 1/2, e to the minus xi minus, and we're fixing mu naught squared divided by 2 sigma squared. And collect all the terms and you get the next line. With mu naught fixed, then the maximum likelihood estimator for sigma squared, and you can go through this, log the likelihood, take derivatives, solve for sigma squared. So maybe just so you don't accidentally take the derivative with respect to sigma, replace sigma squared, say, by theta, so that you remember that you're fixing sigma squared as the parameter, not sigma as the parameter. If you accidentally take derivatives with respect to sigma, you'll get the square root of this answer, of course. So then you wind up with a summation I equals 1 to n, xi minus mu naught squared divided by n. That's actually a nice result, right? If you fix mu at a particular value, then your MLE for sigma squared is the sample variance, but instead of plugging in the sample mean and subtracting deviations around the sample mean, you're subtracting deviations around that specific value of the mean. So it's a nice little result. So at any rate, with mu naught fixed, the maximum likelihood estimator for sigma squared is this generalization of the variance right there. So that's the peak of our likelihood, all right? That's the point where the light switches from being able to not go through the likelihood to the point right above it where the light is actually, passes over the likelihood. And that's that point. That's that point that gets shadowed onto the wall at mu naught. And so we want to plug this back into the likelihood, and we get this function right here. Summation xi minus mu naught squared over n raised to the minus n over 2 power, and then e to the negative n over 2. And this e to the negative n over 2 is irrelevant because it doesn't involve mu naught. So that's for one mu naught, and if we did that for every mu naught, we would get a function. And so here's our profile likelihood is this function, summation xi minus mu squared raised to the negative n over 2. That function is our profile likelihood. And then again, this function's clearly maximized at mu equal x bar. You can, of course, solve it. But in general, one nice property of the profile likelihood is that the maximizer of the profile likelihood, the maximum profile likelihood estimate, is also your MLE for the parameter. So in this case, the maximum of the profile likelihood for mu is going to be x bar, the same as the maximum likelihood for the complete value. So if we wanted to divide this by its peak value, we would simply divide it by the same thing, and with instead of mu there, plug x bar in, and then that would normalize this function so it tops out at 1. So let's actually go through the R code to generate this function, our mu for the sleep data. So our mu vals, we're going to go from, say, 0 to 3 and do 1,000 of them. So we'll plot a function of 1,000 mu naught values. Our likelihood values, and then so it would just be this sum, xi minus mu squared sum raised to the minus n over 2 power. So that's this term right here, raised to the negative n over 2 power. But I want it to be maxed out at 1. So normally I create the likelihood and then divide by its maximum value. But in this case, I know exactly what the exact maximum value is. It's when you replace mu by the mean. So instead I divide it by the mean right here. And this sapply is just a loop. It says loop over mu values and do this function. And then I'll plot them and connect them together with type equals L. And then I'll put the likelihood values above 1/8 and above 1/16, and then I get this plot. So that is my profile likelihood for mu. That is the function that I get if I take the bivariate likelihood for mu and sigma, place a light along the direction of the sigma axis, and look at the shadow on the wall. This is the outline of that shadow, and that's called the profile likelihood. And there's many theoretical properties of the profile likelihood, but most importantly, you can kind of treat them as if they were a standard univariate likelihood. So you would treat this just like a regular likelihood for mu. The higher values are better supported. The peak is where the maximum likelihood estimate occurs, and you could draw horizontal lines to get likelihood-based intervals for mu. Well, that's the end of today's lecture. We gave you many ways to create confidence intervals. We gave you methods for creating T confidence intervals. We gave you a method for creating a confidence interval for a variance, maybe not the most useful one, but we did it. We also showed you lots of really neat, kind of well-known among statistics circles, but not generally well-known techniques for generating likelihoods when you have Gaussian data. And so all of these techniques you could use in practice if you have data and you're willing to assume that it's Gaussian. All of the techniques would apply. The specific technique of the T confidence interval is a very robust interval. As long as your data looks roughly mound-shaped, then you're going to be okay. The last thing I always mention is a question I always get about the T confidence interval is basically the T confidence interval and the standard normal confidence interval look the same except with the T quantile replaced by a standard normal quantile. And people always ask me, at what point do I switch, what sample size do I switch between a T confidence interval and a standard normal confidence interval? But the point is that the T confidence interval limits to the standard normal confidence interval. So my answer to that is just always do a T confidence interval. Just never do a standard normal confidence interval. And then you don't even have to worry about it, because if your sample size is big enough, that T quantile looks just like a normal quantile anyway. So hopefully that answers that question. And I look forward to seeing you next time, where we'll expand on confidence intervals for more general settings where we have multiple groups. Hi, my name is Brian Caffo. This is Mathematical Biostatistics Bootcamp, Lecture 10 on T confidence intervals. So in this lecture, we're going to go through group T intervals, whereas the last lecture we did T intervals for a single mean, or you could do those intervals for a group where the observations were paired. But now we're going to talk about instances where we have two independent groups. We'll briefly talk about a method to construct a likelihood, and then we'll talk about what you do if you have unequal variances. Let me motivate the problem a little bit. Suppose that we want to compare the mean blood pressure between two groups in a randomized trial, those who received treatment to those who received placebo. Unlike last week, where people would have had to have been matched, say, comparing the same person before and after receiving a treatment, these groups are entirely independent, the group that received the treatment and the group that received the placebo. So we can't use the same procedure. We can't take pairwise differences between measurements. In fact, they might have different sample sizes in the two groups, and then we definitely couldn't do it. So this lecture, we're going to talk about ways for investigating the differences in the population means between groups when we have independent samples. But we'll see that the methodology works out to be very similar to what we did last week. The motivating ideas will be nearly identical. So let's go through some assumptions that we're going to use for our first variation of the T interval. So our first collection is the x1 to xnx is a collection of IID random variables. They have some mean and they have some variance, and y1 to ny are IID normal, and they have a different mean, but the same variance. Right now, we're going to assume the variance between the two groups is the same. So we might think of X as the treated group and Y as the control group, or X is one group and Y is another group. So let's let X bar, Y bar, SX, and SY be the means and standard deviations for the two groups. And our goal is to estimate, say, the difference, mu X minus mu Y, or of course, you could do mu Y minus mu X. I'm going to get the negative of the answer. We would like to estimate that, but we'd like to have a confidence interval to quantify our uncertainty in estimating that parameter. So the obvious estimator of, say, mu y minus mu x is y bar minus x bar. I think everyone would agree that the interval needs to be centered at that point, or that point has to be central in the construction of the interval. But we also need to figure out some way to create a confidence interval to incorporate our uncertainty. Well, let's think, can we do something that's along the lines of estimate plus or minus a T quantile times a standard deviation? Well, we want a standard error of this estimator y bar minus x bar. If you churn through the calculations, and I would hope that everyone in this class could do this calculation at this point, under the assumptions that we've made, the variance of y bar minus x bar works out to be sigma squared times 1 over nx plus 1 over ny. And there's a really good estimator of that entity in this setting. In fact, it's a maximum likelihood estimator or close to it. And that's the pool variance estimate, S sub p squared. And that works out to be nx minus 1 times sx squared plus ny minus 1 times sy squared divided by nx plus ny minus 2. And this works out to be a good estimator of sigma squared. Let's talk about this estimator really quickly. If you take nx minus 1 and you divide it by nx plus ny minus 2, you get a number that's between 0 and 1. And if you take ny minus 1 and you divide it by nx plus ny minus 2, you get 1 minus that number. You can check the calculations to make sure that I'm right about that, but I'm right. So this estimator, S sub p squared, is nothing other than a weighted average of the two group variances, right? So it's a weighted average of the variance for group X plus the variance for group Y. If nx and ny are equal, if you have the same sample size in both groups, then you can calculate nx minus 1 over nx plus ny minus 2 works out to be 0.5, in which case the pooled variance estimate works out to be the arithmetic average of the two variances. On the other hand, if the group X contains a lot more data, right? Nx minus 1 is a lot larger than ny minus 1, then nx minus 1 over this denominator is going to be much bigger, and you'll get a much bigger weight on sx squared over sy squared. And in that case, the weighted average does exactly what you would hope, is it takes whichever of the two groups that has more measurements associated with it and weights the variance estimate from that group more heavily, which is exactly what you would hope. There's more data. This variance estimate is going to be estimated a little bit better since it has more data. So it makes sense that a good estimator would place more weight. And so that's basically what this pool variance estimate is. It's nothing other than an average. It's just, say, what we would call simplicial average rather than an arithmetic average. Okay, so just to reiterate some of these points, the pooled estimator is a mixture of the group variances placing bigger weight on whichever one has a larger sample sizes. If the sample sizes are the same, it's really easy. All you have to do is average the two variances. And then the pooled estimate is unbiased. We can show that really quickly. If you take the expected value of S sub p squared, you just use the fact that both of the individual group variance estimators are unbiased, and then you wind up with the result. I'm not going to show this because it's kind of complicated to do, but the pooled variance estimate turns out to be independent of y bar minus x bar. But the reason is, if you stomach this fact that I didn't show before, that x bar is independent of sx, and y bar is independent of sy, well then x bar minus y bar is going to be independent of xx minus sy because all of the collections of things are independent. Then because of that, it should be independent of any function of sx and sy, which S sub p squared is a function of sx and sy. So I'm not going to dwell on this point, but take it as given that y bar minus x bar is independent of the pooled variance estimate. And hopefully you can kind of get a sense of where I might be going with this calculation. What I'd like to do is create a t confidence interval. And remember, what did I need to create a t confidence interval? I needed to figure out a way to get a standard normal and divide it by the square root of a chi-squared divided by its degrees of freedom, an independent chi-squared. So I'm hoping that some function of the pool variance will be chi-squared. And I just stated without proof that it'll be independent of the difference in the sample means. Well, it turns out, another fact that I'm not going to prove, but one that you can certainly take to the bank, is that the sum of independent chi-squared random variables is again chi-squared, and the degrees of freedom just add up. So let's take nx plus ny minus 2 times the pooled variance divided by sigma squared. Well, that works out to just be nx minus 1 times the x group variance divided by sigma squared, and y minus 1 times the y group variance divided by sigma squared. And we know from before that this first term is chi-squared with nx minus 1 degrees of freedom. The second term is chi-squared with ny minus 1 degrees of freedom. And so if you believe my fact above that the sum of two independent chi-squareds is again chi-squared with the degrees of freedom added, that would mean that when we add this chi-squared with nx minus 1 degrees of freedom and this chi-squared with ny minus 1 degrees of freedom, we get a chi-squared with nx plus ny minus 2 degrees of freedom. And of course, we're happy assuming that the two chi-squareds are independent, because the entire presumption of everything we're talking about is that the two groups we're looking at are independent. This is sort of independent group analysis. We're assuming that group X and group Y are independent. Okay, so now we can construct our t-statistic. So we take y bar minus x bar, subtract off its mean, mu y minus mu x, and divide by its standard error, sigma times 1 over nx plus 1 over ny square root. And then divide that whole thing by nx plus ny minus 2 s sub p squared over sigma squared, which is a chi-squared, and then that is divided by its degrees of freedom, nx plus ny minus 2. So if you look at that, that top part is a standard normal. So the original data for the two groups are Gaussian, so that we know that the sample means are Gaussian, so that we know that the difference in the sample means is Gaussian. And if we take a Gaussian and subtract off its mean and divide by its standard deviation, we wind up with a standard normal. So the top is a standard normal. We're stating that the top is independent of the bottom. And then the bottom we know is the square root of a chi-squared divided by 2 degrees of freedom. So the whole thing has to be a t random variable with nx plus ny minus 2 degrees of freedom. And then if you collect terms and work with the arithmetic a little bit, you see that this left-hand side works out to be y bar minus x bar minus mu y minus mu x, whole thing divided by s of p times 1 over nx plus 1 over ny square root, which is basically just the statistic we'd like to use, which is the observed difference in means minus the population difference in means divided by the standard error, but with sigma replaced with our data estimate of sigma. So sigma replaced by S sub p. Okay, so it's just like before, where we took our statistic that we normally had, replaced the unknown standard deviation with its estimate, and what would normally be a Gaussian random variable turns into a t random variable. And again, notice the form of this is estimator minus true value divided by standard error, estimated standard error again. And then I'm hoping that you should be able to use the same logic from the previous lecture and how we constructed that confidence interval to just say, okay, well, the confidence interval for the difference in means is now just churn through these same calculations, and we get y bar minus x bar plus or minus the appropriate t quantile times the standard error. Okay, let me repeat that again. The estimate plus or minus the appropriate t quantile times the standard error. So again, the interval works out to be the estimate plus or minus the appropriate quantile from the appropriate distribution times the standard error. Okay, remember, what big assumption in this is that there was equal variances in the groups, and we'll talk about that later. I guess one thing I'd like to mention about the equal variance assumption now while we're on it is there are actual tests for equality of variances between independent groups. They work out to be F tests. But those tests are kind of notoriously bad. So I think some textbooks will do things like suggest testing equality of the variances. If the variances are equal, then do this confidence interval, and if they're unequal, do the confidence interval that we're going to talk about in a slide or two. But I don't like that procedure at all. I think you should look at graphs, look at the data, and make assessment as to whether or not the variants are equal or unequal, and use that to decide. If you really must estimate the ratio of the variances in the groups, then I would suggest using bootstrapping would be my suggested technique for doing it, unless maybe the sample sizes are very small. But another safe thing to do is just always assume that the variances are unequal. So if you're worried about this assumption, just always do the conservative thing and assume that the variances are unequal. It's a little maybe above the discussion in this class on how to get a likelihood for mu y minus mu x. But it turns out that getting a likelihood for mu y minus mu x divided by sigma, which is still a single parameter, is very easy. And the reason is that this statistic, y bar minus x bar divided by its standard error, that follows a distribution which is called a non-central t-distribution, and the non-centrality parameter depends on mu y minus mu x over sigma, and then something involving the n's that we know. And so you can use this fact to create a likelihood, not a profile likelihood or anything like that, just an honest-to-goodness likelihood for mu y minus mu x over sigma. I should say what mu y minus mu x over sigma is. I think of it as kind of an effect size type measurement, but it's the difference in the mean standardized relative to the intergroup standard deviation. So it's the difference in the means in standard deviation units, which is a very useful thing if you want to calibrate your difference in the means across studies, right? If you want to say, oh, well, this difference in the means is kind of big. Well, what does big mean? You know, in one case, it's measured in inches. In the other cases, it's measured in tons or something. And in other cases, it's measured in centimeters. So if you look at different experiments, the units are all different. The context is very different. And it's impossible to compare, say, mu y minus mu x across experiments. But there is some hope for comparing mu y minus mu x over sigma across experiments because you've gotten rid of the units and everything is expressed in intragroup standard deviation units. So it's a meaningful parameter, and it's easy to create a likelihood. So I'll show you how to do it. But say this is not a tremendously common technique. On the other hand, the comparison of the two groups using a standard t confidence interval with a pooled variance is an extremely common technique. So let's go through an example of actually constructing this interval. And by the way, this is just a special case of what's called ANOVA estimation, just where you happen to have two groups. Rosner has this great book called Fundamentals of Biostatistics, and I got this example from page 304 of his textbook. And he looked at an example where they were comparing systolic blood pressure for 8 oral contraceptive users versus 21 controls. There was some concern, I guess, in this study over whether or not oral contraceptive use increased the systolic blood pressure measured in millimeters of mercury. So the X bar for the oral contraceptive users was 132.86. The standard deviation for the oral contraceptive users was 15.34. The mean systolic blood pressure for the control subjects was 127.44, and so on. So the pooled variance estimate takes the weighted average of the two variances, and so you'll see the formula right here. It works out to be 307.8. One of the most easiest mistakes, if you happen to be doing these calculations by hand, is to forget and to pool the standard deviations instead of the variances. You should pool the variance, not the standard deviation. So if I took out these squares, I would get the wrong answer. I would get a pooled standard deviation instead of a pooled variance. But you'd really mess up if you treated that number as if it was a variance, because it would be on the wrong order of magnitude even. So the biggest mistake you can make is to not square those things. One way to check when you do this, by the way, is it's an average, right? So in this case, it's going to be an average of 15.34 squared and 18.23 squared. So it has to be between those two numbers, the 15.34 squared and 18.23 squared. So then when you square root it, that number has to be between 15.34 and 18.23. So if that hasn't happened, you've really screwed up. Okay. So we've got our pooled variance, and if we square root that, we'd get our pooled standard deviation. And then we need the appropriate t quantile. So we need the t quantile for 97.5 if we want a 95% confidence interval. And we need 27 degrees of freedom, which is, if I'm doing my arithmetic correctly, 8 plus 21 minus 2. And in R, you can just get this number as the QT, Q standing for quantile and T standing for t-distribution. 0.975, because we want the 97.5th percentile, and degrees of freedom equals 27. It'll just return 2.052, maybe plus some other decimal places. And so the interval is 132.86 minus 127.44, plus or minus our t quantile times our pooled variance times 1 over 8 plus 1 over 21. This works out to be negative 9.52 to 20.36. One of the most important things to look for, because it's a difference in means, is whether or not the interval contains 0, right? Because if the interval contains 0, then that would say a reasonable estimate for the difference in blood pressures between the two groups is that they're identical. And in this case, it does contain zeros. So, there's evidence to say that there is no difference. In other words, that this oral contraceptive use doesn't appear to be presenting evidence that there's an associated increase in blood pressure. Turns out that evaluating whether or not zero in this interval turns out to be equivalent to a two-sided hypothesis test. And we'll talk about a hypothesis test later on. So you have to be careful in how you interpret hypothesis tests. Right now, we might as well just say negative 9.5 to 20.4, say, is a reasonable estimate accounting for the uncertainty in the measurements for comparing the average systolic blood pressure between oral contraceptive users and controls. Now, by the way, another thing to keep track of whenever you create these intervals is what order you've subtracted things in, right? In this case, we did contraceptive users minus controls. I think you should pick a rule and stick with it. So I always use, say, treated minus control. And it doesn't matter. Of course, you just get the negative of the interval if you do it the other direction. But in interpreting it, let's say this interval was entirely above zero, then you would be saying that oral contraceptive users had an estimated higher systolic blood pressure than controls. But if you forgot the order and thought that you had subtracted controls minus oral contraceptives, you would get the exact opposite interpretation. So anyway, my point being, just remember what order you subtract things in, because it's an easy mistake to make. Here on the next slide, I just have a likelihood plot for the effect size using the non-central t distribution. And I got, a rough idea of the range of values to plot, by the way, as I took my confidence interval, negative 9.52 to 20.36, and I just divided it by the pooled standard deviation, and that gives me about negative 0.54 to 1.16. And so, I plotted, I think, from negative 1.5 to positive 1.5. So, I got at least a rough idea of the range of things to plot from looking at the interval. This, by the way, negative 0.54 to 1.16, is not a valid interval for the effect size because we haven't accounted for the uncertainty in estimating this S sub p here in the denominator. Later on, we'll talk about an effective way for generating confidence intervals for nearly any statistic that you can dream up using bootstrapping. So finally, I just want to briefly mention, what do you do if you're not willing to assume the variances are equal? Well, we can calculate the variance in the unequal case. Y bar minus X bar is still, of course, normal. Its mean is still, of course, mu Y minus mu X, but now its variance has changed. We can't factor out the sigma squared, so it works out to just be sigma squared X divided by NX plus sigma squared Y divided by NY. And the statistic we'd like to use to generate our confidence interval would be Y bar minus X bar minus mu Y minus mu X divided by this variance with the estimated variances plugged in, Sx squared over Nx plus Sy squared over Ny, all raised to the 1/2 power. Unfortunately, that doesn't exactly follow a t-distribution. But there's a smart idea, right? And the idea was, well, it's maybe not a t-distribution, but people could simulate and kind of figure out what its distribution looks like. And they said, well, it looks an awful lot like a t-distribution, but, we can't seem to get the degrees of freedom exactly right to make it perfectly a t-distribution. And they said, well, why don't we find the best degrees of freedom to make this look like a t-distribution? And they said, well, we could have that degrees of freedom depend on the data, on the variances, for example, and we could have it be a fractional degrees of, not have to be a whole number. And everyone said, that's great. That's a great idea. Why don't we do that? And so they came up with this crazy formula for the degrees of freedom by trying to figure out the best degrees of freedom that makes it look like a t-distribution. And that's what you can do. You basically evaluate the statistic with the empirical variances plugged in the denominator, and then act like it's t-distributed with these kind of impossible to remember but easy to plug into degrees of freedom formula. And that's all you have to do. And that confidence interval works really, really well. So our confidence interval is just going to be Y bar minus X bar plus or minus the appropriate t quantile with these crazy degrees of freedom, 0.975 quantile for a 95% interval, times the estimated standard error, and then we have a t interval. So let's go through that really quickly for our example. We're going to compare our 8 oral contraceptive users versus our 21 controls. I just re-put all the numbers here just to remind you. In this case, if you directly plug SOC and SC into this formula from the previous page where you have, SX squared in this case would be SOC squared and SY squared would be SC squared, and NX would be NOC, and NY would be NC. Just plug those directly into that formula, and you get 15.04 degrees of freedom. And that if I plugged into the formula correctly, maybe everyone double check me. I think with 10,000 people double checking me, we should get it right. The T quantile for that turns out to be 2.13. So you just construct the interval. Difference in the means plus or minus the appropriate T quantile plus the variance, 15.34 squared over 8 plus 18.23 squared over 21, square root the whole thing, and you get this confidence interval right here. So you interpret the confidence interval in the same way. You're obviously interested in whether zero, in this case, and whether zero is in the confidence interval. And if you want kind of a safe thing to do, you just would always do this interval instead of assuming equal variance. Well, that was a quick lecture today, and I hope using the kind of thought process from this lecture and the previous one that you should be able to sort of create confidence intervals at a whim now. If there's any case where you can figure out what the standard error is of a statistic, then you more or less think, well, I'll get a confidence interval by taking estimate plus or minus some quantile from some distribution times the standard error, and maybe that quantile will usually either be a T quantile or a standard normal quantile. And I think you'll notice that the vast majority of confidence intervals that we cover in this class and the vast majority of confidence intervals that you encounter in practice will be exactly of this form. So I look forward to seeing you next time, and next time we're going to have a very light lecture. We're going to talk about plotting. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 11 on plotting. So in this lecture, we're going to have kind of a very different sort of lecture than what we've been doing for the most of the class, and we're just going to talk about plotting your data. And the reason I held off on talking about plotting your data till now, which might as well be the most important aspect of data analysis, is because I wanted to demonstrate that some of these plots are estimators. They're multivariate estimators, but they estimate things like densities, and we couldn't really introduce plotting to estimate densities unless everyone knew what a density was. So let's get right to it. One of the most well-known forms of plot is just simple histograms. Histograms just display a sample of the estimate of a density or mass function, and they're basically just bar graphs of the frequency or proportion of times that a variable takes specific values, or bins of values for continuous data. So it's probably easier to explain this with examples than with words. So the data set islands in R is a package that contains the areas of all land masses in thousands of square miles. So you can just load it into R by just typing in data islands. And you can view the data by typing islands, and it'll just show you the list of numbers. And we can create a histogram with the command hist of islands. And if you just do $hist, it'll give you the options for the command hist, which includes things like bin lengths and how you break up the histogram. Picture, we see that we had 41 islands that had this range of area. You can see this is a very crummy histogram. It doesn't tell you much information. And the reason is because most of the islands are really small, and there's only a handful of big ones. And so maybe there's something more informative we can do. Well, so here in this picture, we see that we had 41 islands that had this range of area. You can see this is a very crummy histogram. It doesn't tell you much information. And the reason is because most of the islands are really small, and there's only a handful of big ones. And so maybe there's something more informative we can do. Well, let's talk about the pros and cons of histograms first. So histograms are useful, they're easy, they make sense, they work on discrete and even unordered data. You can make a histogram of M&M colors or hair colors or whatever. They're just bar plots of frequencies. There's some problems with them. They use a lot of ink and space to display not so much information. You could replace them with a table of the frequencies pretty easily. And it's a little bit difficult to compare several at a time. And then, as I pointed out before, the specific use of the histogram for this data set isn't very good. You should maybe log the data to spread things out a little bit. In this case, I did log base 10, so it gives you orders of magnitude. And then if you look, the histogram is much better. And so the numbers now on the horizontal axis are log 10. So you're looking at orders of magnitude, which is probably a lot better to look at in this case. Stem and leaf plots are just another way of really quickly on the fly, if you ever need to create a histogram and all you have is a pen and a piece of paper, then a stem and leaf plot is definitely what you want to do. And it was created by John Tukey, who is a famous statistician that created lots of inventions. He was one of the co-inventors of the fast discrete Fourier transform and many, many other statistical and signal processing techniques. A stem and leaf plot is basically what you do is you have to pick a digit that you're going to kind of break the data on. And then you put the digits to the right of that, you stack them up. So here it's probably easier to just show this than to actually describe it. So I type in stem log 10 of islands, and the decimal point is at the horizontal line here, which in this case is a bunch of pipe characters. So when we look at the one on the left, the one on the right means that's 1.1. One island had land area 10 to the 1.1, because remember we took log 10. And then we can count. Let's see, how many is there? There's 1, 2, 3, 4, 5, 6, 1. So there were 6 islands that had log area 1.1. And then because there were so many in those bins, they broke the one bin up into those below 5 and those above 5. So at any rate, you can see how you could do this really quickly. You just pick the decimal place, and then you just, the rounded number immediately after the decimal place, you just start stacking them up, and then they wouldn't be in order, so then maybe you do it again where you reshuffle the numbers on the right so that they're in order. And it makes for a very convenient plot. It gives you a quick histogram, it's a quick density estimate, and you can do it on the fly really easily. Another useful plot is a dot chart. Dot charts just display the entire data set, one dot per point. And you might say, well, that seems like a pretty uninformative plot, but it's usually quite informative, especially if you can order the dots well. So the ordering of the dots and the labeling the axes can display a lot of information. And so the dot charts show an entire data set. You could, in principle, reconstruct the data set from a dot chart. So it has really high data density. But, there's problems with them. They may be difficult to construct and difficult to interpret for data sets with lots of points. You may get overplotting and stuff like that. So if you look at this dot chart where I did the dot chart for the log 10 area, so it's log 10 square miles, you see it just plots all of the data. It's the same thing before, but it gives you a good idea of the density of points. And you could see, you could probably make this chart a lot. You could really improve on this chart, for example, by maybe grouping land masses together, Pacific Islands, maybe put all of those together, for example, and so on. So you could get a lot more information out of it. But at any rate, that's a dot chart. They're good to make. So yeah, just on the next slide, I mentioned that I ordered everything alphabetically, which is the default for the dot chart. But you could play around with it. Playing around with plots is the key thing you want to do. You want to just keep doing them until you get kind of informative information. Another nice thing about dot charts is, if you have kind of a small number of points, you can compare groups very easily. You can add horizontal lines and vertical lines to detect means and medians and spread and that sort of thing. And you can show confidence intervals and interquartile ranges. And to avoid plotting, you can just jitter the points, add a little uniform noise. So let me give you an example. The insect sprays data set is a rather morbid data set that contains counts of insect deaths by insecticides, 6 insecticides labeled A, B, C, D, E, and F. Unless it's mosquitoes, then they deserve what they got. And you can obtain this data set with the command data insect sprays. And then I give you the code for actually creating this plot there. Maybe some of the fancier parts of the plots I omitted here, but this is the basic gist of how I created the plot. If you can generate better code to do this, I'd love to see it. But anyway, then you look at the plot on the next page, and the nice thing about these plots is it displays every single data point. You get a very good sense of what's going on. You can see that the sprays C, D, and E appear to be different than the sprays A, B, and F, for example. You have the confidence intervals for each of the groups, and you have the mean for each of the groups, and they display a lot of information. For example, for group F, you can see these kind of bimodality of the distribution. You can see this sort of outlier in group D, or maybe it's not an outlier, but nonetheless, you can visualize these things quite easily with a dot chart. And because every group only has, a handful of points, it would be a shame to aggregate them into something else that obscured the data. But what you might ask yourself, but what if instead of having like 10 or 15 or 20 points per group, what if I had 10,000 points per group? What should I do? Well, then maybe don't do a dot chart anymore, because you're going to get so much overplotting that you're not going to be able to see anything meaningful. Maybe do something like a box plot. So box plots were also invented by Tukey, and they basically just show the distribution in terms of quantiles. So the center line of the boxes in a box plot represent the median, while the box edges correspond to quartiles. So the boxes give you some information about the density, represented there only by 3 numbers. And then the whiskers extend out to a constant times the interquartile range, which is the difference between the 75th and 25th percentile of the data, or they cap them off at the max value. And that constant was given, Tukey did it by kind of relating it relative to standard normal. And then sometimes outliers are denoted by points beyond the so-called whiskers. And you can see skewness in the data by the center line being near one edge of the box or one of the other edges. So if we just take the same insect spray data and did a box plot, we get, in this data set, you probably don't want to do that, but you do get the same relative picture. You've lost some detail, you've lost information about that bimodality for the density for insect spray F, but you do notice, maybe something's going on there. That distribution is very skewed towards higher values, so you might investigate it more and discover that kind of little 2-group clustering. It does kind of catch these outliers for C and D, but sometimes you have so many data points that the outliers are just a constant mash of outliers, and then there's no point in plotting them. But at any rate, this is a box plot. I think for this particular data set, you're better off doing the dot chart, but if you had lots and lots of observations, the box plot seems like a pretty reasonable thing to do. There's been improvements on box plots. People say, why do it as a box? Why not do it as, something that uses a lot less ink? And what's this constant times the IQR business? That's maybe a little bit difficult to interpret. And so there's been lots of, kind of refinements, but these are your plots ultimately when you create them, so you can use them to investigate the things that you really want to look at. But it's a very reasonable idea to create, in this case, vertical summaries of group data that are based on distributional properties like means, medians, quartiles, and so on. If your boxes get too squished, try logging your data if it's positive, or maybe you could do a cube root if it's positive and negative. For data with lots and lots of observations, you often want to omit the outliers because you get this big mash of black from overplotting that you can't see individual points, and there's no point in calling them outliers anymore if there's hundreds of them. Here's an example of a bad box plot. I just give you some R code to generate a bad box plot, right? It's all squished together. The outliers, there's too many outliers being displayed, and the fact that there's so many outliers means that all the interesting aspects of the kind of meat of the data are obscured by a handful of outliers. So that's box plots. So box plots, kind of give you a density estimate by grabbing a bunch of quantiles and using them from the data. Kernel density estimates, on the other hand, are direct density estimates in the same way histograms are direct density estimates, but kernel density estimates maybe are a little bit better. And the idea is that you're weighting observations according to a kernel. In most cases, that kernel is a Gaussian density. And then you have to pick a parameter that determines how kind of smooth or jiggly your density estimate is going to be. It's called the bandwidth. And your density estimate is itself a statistical estimate. It has variability that you should probably investigate as well. And you should investigate how the bandwidth impacts that variability and the estimate itself. But it's not like this is something that's just unique to kernel density estimates. For example, if you take a histogram, the width and construction of the bins in a histogram play the same role as the bandwidth. So you still have that tuning parameter you have to work with. And again, the width and the number of bins in a histogram can impact what it looks like. But in addition, the histogram is also an estimate with noise. So both kernel density estimates and histograms and so on, they all are statistical estimates that have variation. And it's maybe unfortunate that I'm going to do this as well, that when you plot these things, you don't explicitly acknowledge the uncertainty in the density estimation. So that is kind of a problem, but maybe the solutions to it are a little bit above the discussion from this class. So anyway, the R function density can be used to just create density estimate. So here's the weighting in eruption times in minutes between eruptions of the Old Faithful geyser in Yellowstone National Park. So you can grab this data by just doing data faithful. In D is the density estimate. And this bandwidth parameter here gives a specific rule for selecting the bandwidth of the density estimate. And then the plot creates the plot. So there's our density estimate. And it actually gives you the specific bandwidth it used. And you can see there's an incredibly obvious feature in this data set at 4.5 minutes, let's say, that the eruptions seem to occur in 2 time periods. But you also get a sense of the variation around those eruption times as well. So anyway, kernel density estimates are nice ways to estimate a density and maybe are an improvement over a histogram, I think, by smoothing out the data. Here's another example. I took an MRI and I took a single axial slice and then I disregarded the spatial location. So I just have a bunch of color intensities that are on a grayscale. So here's the image. You can see this is an axial slice. Here's the ventricles. Here's gray matter. Here's white matter. Here's the skull. And if you were to just take these collection of numbers where the intensities are the numbers and disregard where in the image they are and just treat them as a list of numbers, and put that into a kernel density estimate, you might get something like this, where you can see kind of specifically where you have this lots of background voxels, you have kind of a hump for gray matter voxels, a hump for the white matter voxels, and so on. And this is a pretty common technique. In fact, it's so common that it's built into your camera, right? Your digital camera, if you have one, often will have a histogram estimate built into it. You can actually look at the image histogram. And if you don't do it on a digital camera, certainly whatever image processing software you have will actually give you a histogram of the intensity values from the image. And this is exactly what they're doing. And if they do a kernel density estimate, they're smoothing out that histogram. If they do boxes, then they're just discretizing the histogram. Quantile plots are extremely useful for comparing a distribution to a theoretical distribution. So a great example of this is if you want to suggest that your data is normally distributed, you might want to compare your empirical quantiles from your data to the theoretical quantiles of a normal distribution. So if there's a significant departure from a line, then that's going to tell you that the quantiles of your empirical data don't look like the quantiles from a theoretical normal distribution. Then it's a useful diagnostic tool. And the reason it's useful is, unlike histograms, you could do a histogram plot of your data and then compare that, overlay it, say, on a standard normal plot. The reason is that QQ plots are good is that they kind of focus exactly in on the comparison between the two distributions, quantile by quantile. And they really tend to highlight the differences much more effectively than, say, overlaying 2 histograms. It's kind of hard to tell. So here, here's why you want to check for whether or not it's a line. So let's let x of p be the pth quantile from a normal mu sigma squared distribution. It's non-standard normal. Then by definition, probability x being less than or equal to x of p is p. Then clearly the probability that z standard normal is less than or equal to x of p minus mu over sigma is also p, by rules that we've talked about at length in the class already. So we've just basically converted the x random variable to a z random variable. So then you can go back and forth between the x quantile, x of p, is mu plus the z quantile, z sub p, times sigma. So again, I put here, this should not be news to you, that you can convert between non-standard quantiles and standard quantiles by either standardizing the non-standard quantiles or by doing mu plus sigma times the standard quantiles. So at any rate, the result is quantiles from any non-standard normal distribution should be linearly related to standard normal quantiles. So what a normal QQ plot does, for example, is it plots the empirical quantiles of your data versus theoretical standard normal quantiles. And in our QQ norm, it does a QQ plot, and then QQ plot just basically plots your empirical quantiles versus theoretical quantiles from any distribution. And here's an example of a normal QQ plot. And in this plot, it's basically saying that at the high end, your sample quantiles are too large. And at the low end, your sample quantiles are too small, negative. So in this case, it means that your data is heavier tailed than a standard normal. It has excessively large upper quantiles and excessively small negative lower quantiles. In this example, your upper quantiles are too large, right? And your lower quantiles are all smushed up at 0. And that would be indicative of an instance where your data follow some right-skewed distribution rather than a standard distribution. I think in this case, to generate this plot, I used a gamma and compared it to a standard normal. And then here's an example where I generated data from a normal distribution and plotted the quantile plot versus the actual normal distribution. And of course, it looks pretty good. Again, with the QQ plot, the theoretical quantiles are, of course, exactly right, but the sample quantiles are measured with noise. So the normal QQ plot, again, doesn't account for the uncertainty in estimating those quantiles. And so really, you should have, for these QQ plots, maybe some gray lines to indicate the uncertainty around the plot itself. And later on in the class, we'll talk about some methods to actually generate lines like those. Almost everything we've talked about up to this point was continuous data. And for discrete data, we've basically given you one technique, which is a histogram. But what if you had two variables, not a single variable, and you wanted some plot of the bivariate distribution for two discrete random variables? Well, here's Fisher's data on hair and eye color, right? So we want to talk about the distribution of hair and eye color. I mean, Fisher was looking at people from a particular area. And here's the contingency table down here, and you see the different hair and eye colors. And one plot that you could do to look at this is a so-called mosaic plot. Mosaic plot just sort of breaks everything up into squares and rectangles, where the size of the rectangles represents the size of the counts. And so it gives you a pretty immediate way to look at the bivariate distribution of the two variables. It's sort of like getting at a two-dimensional bar chart. It's a quick display. Another thing you could do perhaps is some sort of 3D bar chart. But what's nice about this is it doesn't require extending it out to a third dimension, and gives you a quick way to look. You can see the low counts for red hair, for example, across all eye colors. And you can see that really quickly and obviously in the large green being very consistent across eye colors, for example, but that fair hair seems to change with eye color quite a bit. So you can pick out these patterns really quickly. And so mosaic plots are nice, if maybe a little underused, techniques in plotting. So that was a whirlwind tour of some basic plotting techniques that you can use, and hopefully will get you up to speed and running really quickly with plotting. I wanted to mention at the end, though, that you should really not constrain yourself when you're plotting your data. Think of these techniques, or anything's fair game. Plotting exploratory data analysis is an essential component of applied statistics, and you can't really do any of the probability modeling that I'm suggesting unless you dive into the data a little bit first. It'll give you a sense of whether your probability modeling is ridiculous before you even start. So it's an essential part. And today we just gave you a handful of techniques. But when confronted with a problem, you should attack the data with as many plots as you can think of, and they tend to be very informative. I think Tukey called it intraocular content. In other words, that the conclusions sort of hit you right between the eyes. And that's what plots can do for you that probability models can't do anywhere near as well. So I hope you liked today's lecture, maybe a little bit lighter on the math than usual, but next time we'll pick right back up. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 12 on Bootstrapping. Today we're going to talk about the tool of bootstrapping, which is an incredibly useful, handy result in statistics that you can use in a variety of settings. It sort of coincided with the personal computer revolution, and so it gives us a way to avoid an awful lot of mathematics in biostatistics. Before we talk about the bootstrap, we're going to talk about the jackknife, which is a precursor to the bootstrap. That is, as its name suggests, a handy little tool. So let's talk about the jackknife here briefly before we go into the bootstrap. The jackknife is exactly as its name suggests, a handy little tool. The bootstrap, on the other hand, is like an entire workshop of tools. The key idea in both the jackknife and the bootstrap is to use the data, so-called resampling of the data, to get at quantities that are difficult to get at otherwise. For example, variances and biases and that sort of thing. Now, we don't need either the bootstrap or the jackknife for something like the sample mean, where we know all of its theoretical properties. But for other less obvious statistics, we need something that does it for us. And, it'd be preferable if that something didn't require a year of mathematics just to get us to the starting point. In contrast, the bootstrap is you dream up a statistic or something like that, and you want to estimate a standard error with it, you can start bootstrapping it immediately. So let's talk a little bit about what the jackknife does before we begin with the bootstrap, because sort of historically the jackknife came first. The first use of the jackknife was by the statistician, I'm going to butcher his name, but I think it's pronounced Quinui. And he used the jackknife to estimate bias, I believe. Then the jackknife was really popularized and further refined by the extremely well-known statistician John Tukey, who we talked about a little bit in the lecture on plotting. Tukey had numerous inventions, including the fast discrete Fourier transform. He coined the term bit for binary digit. He was the first person to do that. Anyway, he did lots of things, invented the box plot. I think when you see it, you'll conclude along with me, the jackknife's a handy and an incredibly clever thing for someone to think of. So the idea behind the jackknife, and similar to the idea behind the bootstrap, is you have something that you don't know, like the bias in a statistics or the standard error of a statistic, and the idea is to use the data to get a sense of it. Well, what the jackknife does is it says, okay, well, one way to get at these quantities is to take one of the observations out and then formulate the statistic on the remainder and see how well the statistic does, at estimating that one pulled out observation. And this is very related to the idea that you frequently hear of in machine learning and statistical prediction of so-called cross-validation. The jackknife tends to have a different goal, in that the goal of the jackknife tends to be bias estimation or variance estimation, but the principle is very similar in that you're deleting observations. Leave one out cross-validation is typically used as an estimate of prediction error. So anyway, let's just focus on the jackknife, and if you take classes in machine learning or something like that, you'll talk about cross-validation. The jackknife deletes one observation and calculates whatever estimate you're thinking of based on the remaining n-1 of them. And then it uses this estimate based on n-1 of them, in which you get n estimates having left out one observation one at a time. It uses these n estimates to do something like estimate biases and standard error. And again, note, we don't need this for the sample mean. We know that the sample mean is unbiased under certain assumptions, and we know exactly what the standard error of the sample mean is under the standard setting. So the jackknife isn't necessary for those settings, but it's maybe necessary for other ones. So let's just consider the jackknife for univariate data, and let's let x1 to xn be a collection of univariate data points where we want to estimate a parameter theta. And so let's let theta be the estimate based on the full data set, and then let's let theta hat sub I be the estimate of theta that you obtain where you use the n-1 observations obtained by deleting observation I. And then let's let theta bar be the average of the leave one out estimates. So with that notation in mind, the jackknife estimate of the bias of our statistic theta hat is just n-1 theta bar minus theta hat. So let's kind of consider the principle of this before we get to why in the world that n-1 is there. So theta hat is our estimate looking at how close it is to the averages of estimates where we deleted an observation each time is exactly going to give us a sense of kind of population level bias. And then you might wonder, where in the world does this n-1 come from? It's a factor that's based on for example, the sample variance, where you would estimate the bias of the sample variance. It would give you the correct answer. The n-1 is sort of calibrated by statistics that we actually know. So again, this estimate is really related to how far the average delete 1 estimate is from the actual estimate. And then this n-1 is just a factor that was sort of a good estimate of what is the appropriate multiplier to have to get the bias to be an estimate of the true bias. And then the jackknife estimate of the standard error is n-1 over n times the sum of the squared deviations of the leave one out estimates around the average of the leave one out estimate. So it's sort of like the square root of n-1 times the variance of the leave one out estimates. So again, the rationale for this factor out front, the extra n-1, why not just take the variance of the leave one out estimates as an estimate of the standard error of the statistic? Well, it turns out that the leave one out estimates, because they have the majority of the data, they have n-1 of the data points included, they tend to be quite close to one another, and excessively close to one another. So the variance by itself is not a good estimate of the standard error of the statistic. So we need a fact, and they calibrated that n-1 is a reasonable factor to do that. And the same thing is true with the bias, that the leave one out statistics tend to be a little too close to one another. Unless you sort of multiply this bias estimate by a little bit, you don't get a reasonable estimate. So let's go through an example. So we had 630 measurements of gray matter volume from workers from a lead manufacturing plant. The gray matter volume wound up to be about 589 cubic centimeters, and we want to estimate the bias and the standard error of the median. And then I'll come back to this discussion of jackknifing the median, because that's where we're going to move forward to the bootstrap. So, for example, the gist of the code to do this, now you don't actually have to execute the code. I'll show you in a page how to do it, but you could do it in any language, not just R. You just have to figure out how to delete observations one at a time. So let's let n just be the number of observations we have. Theta hat is the median of these gray matter volumes. And then the jackknife estimates are the median that I obtain each time where I delete the ith observation, and this sapply function is exactly that. Then theta bar, just exactly from the notation from the previous couple of slides, is just the mean of these leave one out jackknife estimates. Then my bias estimate is going to be n-1 times the difference between theta bar and theta hat. And the standard error is going to be the square root of n-1 times the average squared deviation of the jackknife estimates around the average of the jackknife estimates. And then on the next page, it's a lot easier to do this if you want to just use the software. In the Bootstrap library, you can jackknife out is the jackknife function of my list of gray matter volumes, and the function I want to calculate the jackknife estimate of is the median, and then I assign that to a variable out. Then I pick out the standard error and the bias calculation. Both methods yield an estimated bias of 0 and a standard error of 9.94. And there's an odd little fact. The jackknife tends to work well for sort of smooth functions, and empirical quantiles often don't satisfy that requirement. The median is an example. So there's an odd little fact. The jackknife estimate of the bias for the median is always 0 when the number of observations is even. So the median is an example where the jackknife isn't that good of a thing to do. In general, if your function of the data is a nice smooth function, the estimate that you're getting is a nice smooth function of the data, then the jackknife will work fine. But if not, then it tends to work pretty poorly. And that there was a very well-known paper by Efron, the inventor of the bootstrap, that illustrated this quite starkly. And the jackknife has been shown to be a linear approximation of the bootstrap. So if you're in some setting where it's going to be difficult to program up the bootstrap, then doing a jackknife, which is a pretty simple thing to do, is a handy little tool to use. And then just to remind you, don't use the jackknife for sample quantiles. It's a handy procedure and it works in a lot of settings, but maybe not for sample quantiles like the median, as it's been shown to have some poor properties. And what could you possibly use then? Well, why not try to use the bootstrap? So let's move on to the bootstrap, which is maybe a little bit more of a complete toolbox, but is certainly a little less compact of a tool than the jackknife in exactly the way the analogy to the tools sounds like. By the way, the term bootstrap comes from this idea of pulling one up by one's own bootstraps, right? Of course, this has been discussed a lot. It's kind of an unfortunate title for a statistical procedure because it makes it sound like the information is coming from nowhere, right? Because you can't pull yourself up from your own bootstraps. It's physically impossible. But, there's been plenty of theoretical work that shows where the information is coming from the bootstrap and sort of when it is applicable. Another thing I would note is this idea of pulling oneself up from one's own bootstrap is from the fable of Baron Munchausen. And so there's a great movie called The Adventures of Baron Munchausen, and it was done by some of the people who made the Monty Python series. If you get a chance, you should, in honor of this lecture, watch the Baron Munchausen movie. But anyway, from that fable is where the term pulling oneself up from one's own bootstrap comes from, and then that's where they got the idea for the name for this procedure. Any rate, back to the jackknife. So another way to think about the jackknife is this idea of so-called pseudo-observations. So if you take n times theta hat minus n minus 1 times theta hat sub I, you can kind of think of these as whatever observation I contributes to the estimate of theta. And then notice if theta hat is the sample mean, then these pseudo-observations are exactly the data themselves. So it's sort of this idea of taking what worked in a very neat and tidy sense for the sample mean and trying to extend the idea to other statistics. And then the sample standard error of these observations is the jackknife standard error. And the mean of these observations is a sort of bias-corrected estimate of the parameter that you're interested in. So it takes your ordinary estimate and attempts to correct the bias. I have to admit, for my thinking about the jackknife, I kind of prefer to think about it this way in terms of the pseudo-observations than in the sort of classical development of it. So now let's get to the bootstrap. So the bootstrap is this tremendously useful tool. It's useful for creating confidence intervals, standard errors, basically anything that's involved in the distribution of a statistic where you don't know that distribution. The bootstrap is an incredibly useful thing to use. As an example, we said before on the previous page that, well, the kind of jackknife standard error calculation for the median doesn't appear to be working that well, or the bias didn't seem to be working that well, and maybe that raises some question about the standard error calculation for the median using the jackknife. Well, how about deriving a confidence interval for the median? Or you come up with a generic statistic. You want to look at the log difference of two variances. How do you come up with a confidence interval for the log difference in two variances? Well, the bootstrap procedure follows from this so-called bootstrap principle, and you can do things like create confidence intervals for parameters based on kind of difficult to work with statistics. And the bootstrap principle basically follows along the following lines. Suppose that I have a statistic that estimates some population parameter, but I don't know that it's sampling distribution. So take the median. We actually know a lot about the sampling distribution of the median, but let's suppose you don't know anything about it. Then you would say, well, I'm stuck. Well, the bootstrap principle says, well, why don't we just take the distribution defined by the data to approximate the sampling distribution of the median? So what's the distribution defined by the data? The distribution defined by the data, if you're not putting any constraints on it, puts probability 1 over n on every data point. That is a distribution. It's a discrete distribution, right? It's a discrete distribution that it puts probability 1 over n on each data point, and it's a weird distribution because the data points, are of course generally have fractional amounts, and it's a weird kind of discrete distribution in that it's not sort of like a die roll where it's on the integers, but nonetheless, it's a nice discrete distribution, and its mean is of course the sample mean. So it's it's kind of, at any rate, this empirical distribution is a reasonable distribution to work with. And so why don't we look at the sampling distribution of the median based on the empirical distribution from our data, where we place probability 1 over n on each data point. And that's the bootstrap principle. It's saying, well, I don't know what the population distribution is. And so without that and without some tool like the central limit theorem, I can't figure out what the distribution of my test statistic is. Well, why don't I take my distribution given by my empirical distribution and figure out what the distribution of sample medians are like from that distribution? Because I know that, right? It's just a distribution that's 1 over n on each data point, and I can work with that. So that's a really nifty principle, and it can be executed in a kind of parametric way or a non-parametric way. Today we'll be talking about the non-parametric bootstrap, where the empirical distribution that we work with is just places 1 over n on each data point. If we want to figure out things about this distribution, it's actually not very convenient to work with. Say you have 100 observations, and you're saying, well, the distribution I'm working with now places probability 1 over 100 on every data point, and I want to know what the distribution of medians of 100 observations from that distribution is. That's actually kind of a hard thing to work with. You couldn't actually work that out on pen and paper. Maybe if you had, 5 observations, then there's only 32 combinations to work with. But in general, it's a little hard to work with. People said, well, why don't we just use simulation? Forget about it. Why don't we just use simulation? And then the process of bootstrapping has this kind of interesting resampling interpretation. So what do people wind up doing? The general procedure follows by taking the data set and simulating complete data sets with replacement. So we put all of our data points in a bag. Let's say we have 100 data points, and we pull out a new data set of 100 data points, but we sample with replacement. So once we pull out a point and record it, then we put that observation back in the bag, mix it up again, and pull out another point, and it could possibly be that same point again. If we sampled without replacement, we would just get a permutation of our original data set. So the bootstrap distribution is sampling with replacement. So what is that? That is exactly drawing IID samples from a distribution that places probability 1 over n on each data point. And so for every one of these resamples, right, that's the idea. It's resampling from the observed data. You're creating fictitious data sets by resampling from the observed data. That's why it's called a resampling procedure. So let's say we have 100 observations. We draw with replacement complete data sets of size 100 from our observed data. From each of those complete data sets of size 100, we calculate the statistic that we're interested in. Say, for example, the median. We would calculate the median then for every resample. So we draw a sample of size 100, calculate the median. Redraw a sample of size 100, calculate the median. Redraw a sample of size 100, calculate the median. We repeat that process over and over and over again. Let's say we did that 10,000 times. We would get 10,000 resampled sample medians. And we would use those 10,000 resampled sample medians to talk about the empirical distribution of the sample median. And that seems to make a lot of sense. The first time you encounter this, you might think this is the strangest thing I have ever heard in terms of a statistical procedure, but it does make a lot of sense. So let me drone on about this for another couple minutes. So think about if you actually knew the distribution and could sample from it, how you would get to know the distribution of, say, something like the median if you couldn't do the math, which, for most statistics, you can't do the math. Even mathematicians can't do the math. So let's say, for example, I create a distribution. Let's say I have a 100-sided die, and that 100-sided die has probability 1 over 100 for each side of the die. And let's make it at least a little bit interesting. So the die is shaped a little bit funny, so it's not exactly probability 1 over 100 for every number. So you have a distribution on the numbers between 1 and 100. And you wanted to know, what's the sampling distribution of the median of 10 die rolls from this 100-sided die? Well, that's a hard problem. It's difficult to think about how you would work that out on pen and paper. But what you could do is roll the die 10 times, get a sample median, record it, then roll the die 10 times again, get a sample median, and record it. and then roll the die 10 times again and get a sample median, record it. And you could do that thousands of times if you had patience. Let's say, you were waiting for something. And then if you did it enough, you would get exactly the distribution of the sample median. Okay, so you would get exactly the distribution of the sample median of 10 die rolls. And if you wanted to know what the sample distribution of the median of 20 die rolls, well, you'd have to roll the die 20 times, get a sample median, repeat that process over and over again, and that would do it for you. Okay, so now we know if we can actually sample from the population distribution over and over and over again, how we would get the sampling distribution of a statistic. But when we're confronted with real data, we can't roll the die, right? We don't know what the population distribution is, so we can't do it. But what we can do is roll from a die where every side of the die we've put on the number associated with an observed data point. Then we're not drawing from the population distribution, we're drawing from the empirical distribution, okay? And if we had 10 data points and we want to know what the distribution of the sample median of 10 observations is, well, we can't draw from the population distribution, but what we can do is draw samples of size 10 from the distribution defined by the data we observed and look at what the distribution of the sample median is for those. And that is exactly what the bootstrap does, is it basically says, well, the bootstrap in practice via resampling, it basically says, well, we know exactly what we would do if we actually knew what the population distribution was. Why don't we just do that and use the sample distribution and see how that works? And it's sort of a really nifty idea. So again, let's just take our 630 measurements of gray matter volume from workers at a lead manufacturing plant. Then the median gray matter volume is about 589 cubic centimeters. And we want a confidence interval for the median of these measurements. How do we do that? So here's our bootstrap procedure for calculating confidence interval for the median of a data set of n observations where we know nothing about the sampling distribution of medians of 10 observations. So we would sample n observations with replacement from the observed data, resulting in one simulated complete data set. We would take the median of this simulated complete data set. That would give us one bootstrap resample and one bootstrap resampled sample median. Then we would repeat this step b times, let's say, resulting in b simulated medians of n observations, those n observations having been drawn with replacement from the collection of observed data. Then these medians, well, let's say they're approximately draws from the sampling distribution of the median of n observations. And they're exactly draws from the sampling distribution of the median of n observations from the distribution of the observed data, but we're going to say that's approximately equal to the sampling distribution of the median of n observations drawn from the population distribution. That's the leap of faith we're making, is that this bootstrap process approximates if we, instead of drawing from the observed data, we're drawing from the actual population distribution. Then we could take these b sample medians and draw a histogram of them. And then say we wanted to know, a confidence interval, why not take the 2.95% confidence interval? Why not take the 2.5th and 97.5th percentiles and call that a confidence interval for the median? And that's exactly a so-called bootstrap percentile confidence interval. So it's hard to describe, and I know I'm butchering it, and if I were Efron, I'd be doing a much better job at doing this, but unfortunately you have me and not Efron. And it's difficult to describe, for me at least. On the next page, I'm showing you the R code for doing this, and even I've neatened up the R code a little bit, so it's probably a little bit longer than it needs to be. You could do this in about 4 lines. So here, B is my number of bootstrap resamples. I said, let's just do it 1,000 times, but you want to set this number B to be big enough so you don't have to worry about the error in your Monte Carlo resampling. You don't want the number of times that you've rolled the die to be a factor in what you're doing. You want to do it a ton. So here I did 1,000, but crank it up until you're tired of waiting at least. There is a science to how you pick B, but we're not going to talk about it in the class. So N is the length of the number of observations that I have. Okay, then our resamples is this code right here just draws with replacement from the collection of N observations. It draws B complete data sets of size N from that distribution. The replace equals true means that we're sampling with replacement. And then here, this resamples, I dump them all into a matrix so that every row is a complete data set. So there's B rows and N columns. And then I go for every row and I calculate the median in this next line. And that's then B medians, where each median was obtained from resample of N observations from the observed data. And then if you take the standard deviation of these medians, then that is a bootstrap estimate of the standard deviation of the distribution of the sampling mean. If you take the quantiles, the 2.5th and 97.5th quantile, you get 582 to 595. That is a bootstrap confidence interval for the median of gray matter volumes conducted in a non-parametric way. And it's always informative in the bootstrap to plot a histogram of your resampled, in this case, medians. Okay, so in here is my histogram of my resampled medians, and then the 2.5th and 97.5th quantiles of my bootstrap resampled medians are drawn here in dashed lines, and so that 95% of my resampled medians lie between these two lines, and so we're going to call that a bootstrap confidence interval. Now, I'm going to give you some notes on the bootstrap. So for both the bootstrap and the jackknife, today's lecture is really just a teaser. As you can probably guess from my description, they're sufficiently difficult techniques to where, you don't want to take these lectures and view them as enough knowledge to just run out and use them willy-nilly. I just wanted to give you a teaser so that if you hear the terms, you know what people are talking about. So the bootstrap, the one that I described today, is non-parametric. It makes very little assumptions about the population distribution. And the kind of theoretical arguments proving the validity of the bootstrap tend to rely on large samples. So there's a question about when and how you can apply it, but I find it to be a very handy tool in general. The confidence interval measure that I gave you, these percentile confidence intervals, they're not very good. You can improve on bootstrap confidence intervals by correcting the endpoints of the intervals. And the bootstrap procedure, the one I would recommend is the so-called BCA confidence interval. The bootstrap package in R will calculate these for you directly if you'd like. That's what these better, when I say here, better percentile bootstrap confidence intervals correct for bias. And then there's lots and lots of variations in the bootstrap procedures. There's parametric bootstrapping. There's bootstrapping for time series. You have to do something different for bootstrapping for time series. There's all sorts of different ways to think about the bootstrap and data resampling in general. And the book called An Introduction to the Bootstrap by Efron and Tibshirani, for anyone who's taken this class, absorb the material in it. It is at a level that you should be able to understand. It's beautifully written. It's a wonderful treatment of the subject. And then in addition to this, there's lots and lots of other books on the topic of the bootstrap, probably too many good ones to name, some of them unbelievably theoretical and other ones quite accessible. I think this Efron and Tibshirani book makes a very nice balance between, giving you the why things work and the how to do things combination. And it also covers the jackknife and other data resampling procedures. The last thing I wanted to mention is I gave you the exact code that you could use to generate for yourself the bootstrap sampling distribution. You could, of course, use the bootstrap package in R, which takes about as many lines of code in this case as programming it up yourself. And just on this last slide, I go through actually using the bootstrap package. But the nice thing about the bootstrap package is that it will actually give you this bias corrected interval. In this case, you can see that the bias corrected interval is nearly identical to the percentile interval, so it didn't make a big difference. But you can, of course, come up with instances where the bias corrected interval is a little bit better. So that's the end of today's lecture. That was a teaser on the idea of bootstrap resampling and a little bit on the use of the jackknife. I hope this inspired you to go learn a little bit more about these tools. They are among the kind of a wide class of tools that became available as modern computing came about, and the idea of being able to use our data, and especially when we have large data sets, to use the data more fully and to use the data to come up with things like sampling distributions instead of using mathematics and assumptions and that sort of thing. So it was a neat idea brought about by the computational revolution, and it's a very nifty technique. Well, next time will be our last lecture, and I look forward to talking about it with you. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 13 on binomial proportions.
In this lecture, we're going to talk about confidence intervals for binomial proportions using frequentist techniques. We're going to talk about why the standard frequentist interval has a little bit of problems, and we're going to give you a simple fix for it. And then we're going to use confidence intervals for binomial proportions to motivate Bayesian analysis, and we'll go through very simple conjugate Bayesian analysis as it relates to estimating the success probability of a coin flip. So when a variable x is binomial with n trials and success probability p, we've learned several things in the class so far. The first is that the MLE for the success probability of the coin from the Bernoulli trials is p hat, the sample proportion of successes. So x over n is the MLE for p. We know that the MLE is unbiased in this case. Expected value of p hat is p. And we know that the variance of p hat is p times 1 minus p over n. We also know from the central limit theorem, because p hat is simply an average of Bernoulli trials, that p hat minus its mean, p, divided by its standard error, square root p hat 1 minus p hat divided by n, that this follows a normal distribution for large values of n. In a previous lecture, we inverted this statement. We said the probability of this test statistic lies below the upper and lower alpha over 2 quantile leads to a confidence interval for p that is of the form p hat plus or minus the relevant normal quantile times the standard error. This interval is so-called Wald interval, named after a mathematical statistician named Wald, of course. There is one problem with this interval, is that it performs very badly. So remember, the fact that we grab the appropriate normal quantile means that asymptotically, via the central limit theorem, the coverage of the interval is, say, 95% when alpha equals 0.05. But coverage varies wildly for finite sample sizes, and it can be very low for certain values of n, especially when p is near the boundaries. And it can even happen when p is near 0.5, though the coverage is best when p is exactly 0.5 for values quite close to p equal 0.5. And in fact, I give you an example here. When p is 0.5 and n is 40, the actual coverage of a 95% interval is only 92%. Then it's also true when p is small or large, meaning small near 0 or large near 1, the coverage can be very, very poor, even for extremely large values of n. And I give an example here. When p is 0.5% and n is 1,876, the actual coverage rate of a 95% interval is 90%. I got these numbers from a paper in the journal Statistical Science by Brown, Kai, and Dasgupta, and you can see the reference here. So because the Wald interval performs poorly, we need some sort of fix. There's quite a few fixes you can actually use. I'm going to present a particularly easy one. And the idea is to add 2 successes and 2 failures, and simply then create the interval as if that were the data. So in specific, let p tilde be x plus 2 over n plus 4. Then the interval I'm proposing is p tilde plus or minus the standard normal quantile times square root p tilde 1 minus p tilde over n. And I call this the Agresti-Cool interval. Some textbooks call it the Wilson score interval, but I like to call it Agresti and Cool because those guys are my friends, though I'm sure Wilson's quite nice too. So why do we do the interval this way? It turns out that there's a reason related to hypothesis testing as to why we can construct the interval this way. It turns out this interval is exactly the so-called inverse of a score test. But I don't think in this class we're going to get a chance to cover hypothesis testing or score tests to cover that. A more heuristic motivation is when p is large or small. We saw an example in the lecture on the central limit theorem that the distribution of p hat winds up being very skewed. It's not a symmetric distribution. The distribution is very symmetric when p is 0.5, but as p heads towards 0 or 1, the distribution is skewed. And then at that point, it doesn't necessarily make sense anymore to center the interval right at the MLE. We might want to pull it towards 0.5 because if p is close to 0 or close to 1, then
distribution will be skewed high if the p is near 0, or skewed towards low value if p is high. So it makes sense in either case to shrink it towards 0.5. So later on we'll show that this interval is related to something we do with Bayesian posterior intervals, and it's often the case that Bayesian procedures perform very well in terms of their frequentist performance. If this confidence interval is an example of Bayesian thinking, that it has reasonable frequentist properties. So let's go through an example. Suppose that in a random sample of an at-risk population, 30 out of 20 subjects had hypertension, and you wanted to estimate the prevalence of hypertension in this population. In this case, p-hat is 0.65, 13 divided by 20, n is of course 20. P tilde from the Agresti-Cool interval is 0.63, so that's 15 divided by 24, and n tilde is 24. The 97.5th quantile from the normal distribution is 1.96, of course. Then you wind up with a Wald interval of 0.44 to 0.86. You wind up with an Agresti-Cool interval of 0.44 to 0.82. And you wind up with a likelihood interval of 0.42 to 0.84. So in this case, any of the techniques seems to give roughly about the same value, which is good. And here on the next slide, I show you the likelihood for p and draw the 1/8, 1/16, and 1/32 likelihood reference lines. But we see the likelihood is, of course, peaked right at the MLE of about 0.65. And we get a rough sense of the spread in our uncertainty in estimating p. So this problem is particularly useful for motivating so-called Bayesian analysis. And we've spent a lot of time in this class talking about frequentist analysis in the form of confidence intervals, and we've spent a fair amount of time talking about the likelihood, probably more time devoted to the likelihood than most introductory statistics courses do. So we need to give at least some time to talk about Bayesian statistics. So here's how Bayesian statistics works. So Bayesians have to posit a prior on the parameter of interest. The prior is a density or mass function. It's a probability distribution on the parameter, where the probabilities, at least in the classical Bayesian sense, represent our beliefs about that parameter. And then the likelihood is the component of the Bayes equation that depends on the data, the objective part, and then the posterior we're going to obtain as the likelihood times the prior. So this is exactly like if you remember back when we were thinking about diagnostic tests. We had, say, for example, some prior belief that a person had the condition that the test was trying to diagnose. We have the data, which is the result of the test, and the posterior odds of the person having the disease or whatever the test is testing wound up being related to the likelihood ratio times the prior odds. And so there's the same exact sort of relationship here. Posterior equals likelihood times prior. Now I have to put a proportional to sign here because it's not exactly equal to. We're off by a constant of proportionality. But it's easiest to think of as this way. We take our likelihood, we multiply it by our prior, and we get our posterior. The rub in Bayesian statistics is very neat and conceptually clean way to think about statistics. The rub is really in here, specifying the prior. That's where we get into trouble in Bayesian statistics, and we'll talk maybe a little bit about that. But mostly in this class, we're just going to talk about the mechanics of how you go about performing a Bayesian inference, and then you can take later classes to delve into the specifics of all the different ways in which Bayesians can think about doing analysis. So let's talk about how we can specify a prior for our binomial proportion. So remember, our binomial data is discrete. It can take only values between 0 and n, but the proportion that we're trying to estimate is a number that, let's say, we're going to treat as if it's continuous. So if we're going to specify a probability distribution on that parameter, it's going to have to be a continuous distribution. So we need a continuous distribution that's bounded from below by 0 and bounded from above by 1. And ideally, it would be a nice distribution that's easy to work with. Well, there is one such distribution. It's called the beta distribution. So the beta distribution winds up being kind of a default prior for binomial proportions. And the beta density depends on two parameters, alpha and beta. Don't confuse the alpha here from the alpha earlier on in the lecture that was related to the coverage rate of the confidence interval. So it depends on two parameters, alpha and beta, and the beta density looks like this. It's this so-called gamma function, gamma of alpha plus beta, divided by gamma of alpha times gamma of beta, and then p raised to the alpha minus 1 times 1 minus p raised to the beta minus 1. And here p is allowed to range between 0 and 1. This constant term out front, gamma of alpha plus beta divided by gamma of alpha times gamma of beta, that's simply the constant of proportionality that you have to obtain to get this integral p to the alpha minus 1, 1 minus p to the beta minus 1, to integrate to 1. So you had some problems very early on in the class where if you had a kernel of a density, in this case p to the alpha minus 1, 1 minus p to the beta minus 1, that had a finite integral, what you had to do was divide that function by its integral over the whole range of values, and you get a proper density. And that's exactly what people did to get the beta density. So here's this density. It does integrate to 1, and maybe it's a little bit beyond the scope of this class to verify that it integrates to 1. So let's talk about some of the properties of the beta density. So the mean of the beta density is alpha over alpha plus beta. And remember, alpha and beta are positive, so alpha over alpha plus beta has to be a number between 0 and 1. So we're good that the mean of the density lies in the range of values for which the density is greater than 0. The variance of the density works out to be alpha times beta divided by alpha plus beta squared, alpha plus beta plus 1. And we've seen special cases of the beta density before. Take the special case when alpha equals beta equals 1. Well, then p to the alpha minus 1, 1 minus p to the beta minus 1, that all just goes away, and this density is just a constant between 0 and 1. And we may not know what the gamma function of alpha plus beta over gamma of alpha times gamma of beta is, but you don't need to because you know that the density is a constant density between 0 and 1. It has to be exactly the uniform density then. So the uniform density is exactly a special case of the beta density. Here on the next slide, I plug in a bunch of different values of alpha and beta, and I show you the shape of the uniform density. So if I plug in alpha equal to beta equal to 0.5, then I get something that looks like a U shape, and it heads off to infinity, height of infinity at both the 0 and as it heads towards 0 and 1. If alpha equals 0.5 and beta equals 1, it looks like this shape right here. And then as beta gets larger and larger, the rate at which it drops down to 0 as p approaches 1 gets faster. And then, of course, it just reverses itself if beta is 0.5 and alpha is 1 or alpha is 2. Again, here's the uniform distribution when alpha and beta are both 1. If you plug in an alpha of 1 and a beta of 2, you just get a line pointing downward. If you plug in an alpha 2, a beta of 1, you get a line pointing upward. Probably the most kind of typical looking cases of the beta is when alpha and beta are both greater than 1, and then you get a hump-shaped density. If they're equal, it's centered right at 0.5, and as alpha and beta get bigger and bigger, it gets more peaked around 0.5. But by allowing alpha to be bigger than beta or beta to be bigger than alpha, you can get this to be a distribution that's skewed towards 0 or skewed towards 1. So you can get quite a few shapes from the beta density by playing around with alpha and beta. So if you're a Bayesian, what you need to do is you need to pick values of alpha and beta that represent where the shape of the density represents your beliefs about the parameter p. And then once you do that, then you can start doing Bayesian analysis. So here on the next slide, we need to choose values of alpha and beta so that the beta prior is indicative of our degree of belief regarding p in the absence of data. And then we're going to use the rule that the posterior is the likelihood times the prior. And again, because we're talking about constants of proportionality, we'll throw out anything that doesn't depend on p. So in this case, the posterior is proportional to the likelihood, which is p to the x, 1 minus p to the n minus x. And here when I say proportional to, I mean proportional to in the parameter p. So p to the x, 1 minus p to the n minus x, that's the likelihood. And we threw out the binomial constant n choose x because that doesn't depend on p. And then we have p to the alpha minus 1, 1 minus p to the beta minus 1, and we threw out the ratio of gamma functions because that doesn't depend on p. And then we multiply those together and we get p to the x plus alpha minus 1, 1 minus p to the n minus x plus beta minus 1. And the posterior is a density that has this form. Now we know it's proportional to that. But remember, it's proportional to that. But look, this density that we see here is exactly just a beta density, right? It's p raised to some power minus 1, 1 minus p raised to another power minus 1. In fact, the alpha is just now x plus the prior alpha, and the beta is just the number of failures plus the prior beta. So we can even tell you what the ratio of gamma functions you would have to make this posterior proper density to normalize the posterior. But we don't need to do any calculations or integrals to do that. We can do that just by looking at it and saying, oh, well, if I take a binomial likelihood and multiply it times a beta prior and think of that as a posterior density, then that posterior density has exactly the form of the kind of core part of a beta density so that I know that it's a beta density. So if the posterior is a beta density with parameter alpha tilde equal to x plus alpha and beta tilde equal to n minus x plus beta, we know lots of its properties. As an example, we know what the posterior mean is. So what do I mean by posterior mean? So the posterior is the distribution of the parameter given the data, right? So the likelihood is the probability of the data given the parameter. The prior is the probability of the parameter disregarding the data. So the posterior winds up being the probability of the parameter given the data. So we can calculate, as an example, the expected value of the parameter p given the data. And because p is in the posterior a beta density, this works out to just be the expected value of a beta distribution, which we learned earlier as being the alpha parameter divided by alpha plus beta. So in this case, it's alpha tilde divided by alpha tilde plus beta tilde. Well, let's just plug in alpha tilde equal to x plus alpha and beta tilde equal to n minus x plus beta. And here I do some manipulations and show that you can get down to the point where it works out to be x over n times n divided by n plus alpha plus beta plus alpha over alpha plus beta times alpha plus beta divided by n plus alpha plus beta, which is a mouthful, but let me go through each term. X over n is the sample proportion. It's the MLE. It's p hat. So x over n is p hat. Let's take this second term, n over n plus alpha plus beta. That's a number that has to be between 0 and 1 because n's positive and alpha and beta are positive. So we have n divided by something that's bigger than n. And then notice, okay, so we have this number that's between 0 and 1. Let's call it pi. Okay, and then alpha over alpha plus beta is the prior mean. Okay, and then this term right here, alpha plus beta over n plus alpha plus beta, you can check yourself. That's 1 minus pi, where we defined pi just a second ago. So this equation works out to be an average of the MLE and the prior mean. Okay, now it's not an average in the sense that it's 0.5 on both things, right? It's a simplicial average, so pi can be between 0 and 1, and then hence 1 minus pi is the opposite. But that's exactly an average. It's an average of the MLE. So let me try to state that in English. The posterior mean is the average of the MLE and the prior mean. Now the average is a very specific kind of average where it weights the MLE different than the prior mean. So let's look at these weights. So here, let's suppose n is really big. Then what happens to n over n plus alpha plus beta? Well, this term pi gets very big, gets much closer to 1, and hence 1 minus pi gets much closer to 0. So then when n is very big, this mixture weights the MLE a lot more than it weights the prior mean. In other words, as you collect more data, your prior means less and the data means more. What happens, on the other hand, as alpha and beta get very big and n remains constant? Well, as alpha and beta get really big, then we get alpha plus beta over n plus alpha plus beta. This 1 minus pi part goes to 1. That gets very big. So 1 minus pi gets very big, and pi gets very small. So what happens as alpha and beta get big? What does that mean in terms of our prior? Well, if you remember back from a couple of slides ago, the shape of the beta density as alpha and beta got bigger and bigger, the shape of the beta density got more concentrated around the mean. And what that entails is that it's saying that our prior belief was a lot more confidence in a specific value of p. And so what that implies is if we're incredibly certain in our prior, then that swamps the data, right? If we're incredibly certain in our prior, that swamps the data. Our MLE has very little weight and our prior has a lot of weight. And this actually explains a lot of politics for you, for example, right? So here your opinion is a mixture of the data and your prior beliefs. If you're immovable off your prior beliefs, then it doesn't matter how much data you collect, right? On the other hand, of course, if you're, in this case, if your alpha and beta are quite low, then you wind up that the MLE dominates the posterior mean. So let me just rehash this because it's an important point. The posterior mean is a mixture of the MLE, p hat, and the prior mean. As pi goes to 1, as n gets large, and for large n, the data swamps the prior and the MLE dominates. For small n, then the prior mean dominates. So when you have very little information, you rely on your prior knowledge. The idea behind Bayesian statistics is that it should sort of generalize how science is ideally working. As data becomes increasingly available, prior beliefs should matter less and less. And then again, a prior that is degenerate at a value, so as alpha and beta go to an infinity, you wind up with a prior that is 100% on a specific value of p, then no amount of data can overcome that prior. So let's also look at the posterior variance. The posterior variance takes a nifty form as well. So let's look at the variance of p, the posterior variance, given the data. So p in absence of the data was beta, with parameters alpha and beta. P given the data via the Bayesian calculation was also from a beta distribution with parameters alpha tilde and beta tilde. So we can just calculate the variance as directly the variance from a beta with alpha tilde and beta tilde plugged in for alpha and beta. And here you see I plug in for alpha and beta x plus alpha for alpha tilde and n minus x plus beta for beta tilde, and you get this form. So let me let p tilde equal x plus alpha over n plus alpha plus beta and n tilde equal n plus alpha plus beta. Then you wind up with the variance of p given x works out to be p tilde 1 minus p tilde divided by n tilde plus 1, which is interesting because it's not quite but very similar to the binomial variance. The binomial variance being p times 1 minus p over n. And so the sample binomial variance would be p hat 1 minus p hat over n. So it's an awful lot like that. So it takes this very, very convenient form. And in fact, let's go back to an earlier point. If alpha and beta were both 2, then the posterior mean works out to be p tilde x plus 2 divided by n plus 4, and the posterior variance works out to be p tilde 1 minus p tilde divided by n tilde plus 1. So this is exactly the sample proportion that we used in the Agresti-Cool interval, and the posterior variance is almost the same with the exception of this plus 1. So what's a plus 1 among friends? So we'll just say it's roughly the same variance as the Agresti-Cool interval. So this is one way to motivate the Agresti-Cool interval. It is centered at the posterior mean, and its standard error is not exactly, but almost the posterior variance. So you could view it as a normal approximation to a posterior interval. And so that's one way to motivate the Agresti-Cool interval, is just to say alpha and beta equals 2 from a Bayesian analysis, and you get something that's very, very similar. So let's go back to our previous example and just do some of the Bayesian calculations. Let's say x equals 13 and n equals 20. So now let's consider a uniform prior, alpha equal beta equal 1. In that case, the prior is just 1, a constant between 0 and 1. What's interesting in this case about the uniform prior is that the posterior is equal to the likelihood, right? Because you have posterior equals likelihood times prior. In this case, the prior is just a constant 1, so the posterior equals the likelihood. Now, you can't always get away with doing this. This is particular to the fact that the parameter that we're interested in is bounded between 0 and 1. For example, if your parameter was anything between minus infinity and plus infinity, you can't put a prior of 1 on that and have a finite integral. Now, people have looked into that, actually, and they said, well, maybe you can do it, and that's for harder classes. For this class, it's kind of nice to note that in this case, if we set alpha equal to beta equal to 1, we get a proper density, exactly a uniform density, and our posterior is exactly equal to the likelihood, which is interesting. If instead we were to set alpha equal to beta equal to 2, remember this prior just looks like a hump right at 0.5, then the posterior works out to be p to the x plus 1, 1 minus p to the n minus x plus 1. And so the very classical way to do Bayesian analysis is you say that the prior is sort of governed by expert knowledge. And the likelihood then is, of course, the objective part that's governed by the data. And, of course, to say that it's the objective part is a little bit misleading because someone had to subjectively elect to model the data as if it's binomial. So there is, of course, a subjective part to the likelihood itself. But, let's put that aside. We have the supposedly objective part in the likelihood. We have the subjective part in the prior, and then the posterior is the mixture of how you update your subjective beliefs with your objective prior knowledge. That's the kind of classical Bayesian inference. But people said, well, it's in many cases, many cases, people don't want statistics that depend on expert opinions to start with. So this idea of a subjective prior is really just not palatable to the idea of science. So then Bayesians went back and thought hard about it, and they said, well, maybe we can come up with priors that are sort of go-to priors for us, things that we can just use where we don't have to think about how to specify the prior, so-called objective priors. And because of that, the collection of Bayesian techniques then sort of ballooned into a variety of different ways of thinking about how to be a Bayesian. The only thing in common they have is that they utilize the Bayesian machinery, that the posterior is equal to the likelihood times the prior, but then they have lots of different ways of thinking about it. And one way of thinking about it is the so-called Jeffreys prior, where people said, well, maybe we could pick a prior that has these specific mathematical properties, and for this particular problem, the Jeffreys prior sets alpha equal to beta equal to 0.5. The uniform prior is another nice one that's somewhat objective, because you could say, well, why don't we put a constant prior, that way the likelihood is the posterior. That seems pretty objective to me. There are problems with doing that. The point is that uniformity on one scale is not uniformity on another scale. So the fact that the prior is uniform for p means that it's not uniform for p squared, for example. You calculate the distribution of p squared, it's no longer uniform. So a uniform distribution doesn't adequately represent absence of belief. The problem with that is there's no probability density that measures absence of belief about a parameter. If you've written down a density, you've specified belief. You've completely characterized its probabilistic behavior. So anyway, these are very technical problems with Bayesian analysis, and they all kind of revolve around how in the world do we set this prior. But in this case, I think people would say the uniform prior seems pretty reasonable, the Jeffreys prior seems pretty reasonable, and putting a prior that's humped at 0.5 because, shrinking everything towards 0.5 also seems pretty reasonable. All of those things don't seem so bad. And the benefit is no matter what you choose, someone else could pick a different prior. As long as you gave them the likelihood, someone else could pick a different prior than you. So the idea that you could just pass around the likelihood and everyone could pick their own prior is also quite palatable way to do Bayesian inference. So I'm going to go through some pictures just to show you, and I fudged a little bit. I'll tell you how I fudged a little bit on the pictures. So here, I normalized everything so that it's 1, but then here in this first one, the problem is that the prior heads off to infinity near 0 and near 1, so if I were to normalize it, I'd just get I can't divide by infinity, so I fudged a little bit. So this U-shaped curve looks different than the U-shaped curve that I'm plotting here. So in order to get it on the same plot, I fudged a little bit. So if you try and do this, you'll see how I fudged. But okay, so the U-shaped curve isn't to the right scale, but I put it on the same scale as the posterior and the likelihood, which both of those I normalized so that its peak was at 1. So the blue is the prior, in this case, the Jeffreys prior at alpha equal to beta equal to 0.5. The green is the likelihood, and the red is the posterior. So you see what happens when you multiply the green times the blue, and then renormalize, you get a red curve that looks an awful lot like the likelihood. So in this case, the Jeffreys prior doesn't move us off our likelihood very much, and the posterior inference, which is entirely based on this red curve, is pretty much exactly identical to the likelihood. Then, of course, on the next slide, if the prior is completely flat, the posterior and the likelihood are identical, so there is no green curve in this case. It's exactly underneath the red curve. Now let's look at alpha equal beta equal 2. Then my prior is this hump shape at 0.5. You can see that my likelihood is the green shape and my posterior is the red shape. And you can see it's ever so much shifted towards 0.5. So the red shape is the mathematical compromise between the knowledge codified by my blue prior and the objective part codified by the likelihood. Again, I should put objective in quotes. Now let's make it more extreme to kind of show you what's happening. Let's put alpha equal to 2 and beta equal to 10. And then the blue curve gets shifted a lot towards 0. As beta gets much bigger than alpha, the prior becomes more pushed up towards 0. As alpha becomes much bigger than beta, it becomes pushed up towards 1. And then if alpha and beta are equal and they get larger and larger, it gets more peaked around 0.5. So anyway, now we're all pushed up towards 0. And you can see here we have the blue curve is the prior pushed up towards 0 because beta is much larger than alpha. And it has a finite maximum because both of them are bigger than 1. And then we have the green likelihood, which has been constant through every one of these pictures. And then we have the red posterior, which is the compromise between the evidence represented by our data and the assumed likelihood, and our blue prior, which represent our knowledge, our prior knowledge. And so the red curve is the appropriate mathematical compromise between these two opposing positions. In this case, let's say you had a prior belief that prevalence of hypertension was very low. You thought it was on the order of 0.1. Your data says, no, it's very high. It's on the order of 0.65, right? And so your likelihood is that compromise to say, well, your data has moved me very far away from my prior towards the MLE of 0.65, and that's how the mathematics works out. And if as n goes to infinity, this green curve, the likelihood, will get more and more peaked around whatever the true value is, and it'll just grab this red curve and pull it increasingly towards it. So what happens in politics, for example? Well, people have their blue curve is very spiked, right? They're dead set in their opinions, and no amount of data is going to move them off of it. So here is an example where I have alpha equal to 100 and beta equal to 100. What happens then? Alpha and beta are equal, so the beta distribution centered at exactly 0.5. But as alpha and beta goes to infinity, the variance of the beta distribution gets really small, so our prior, we're quite sure, according to our prior, that beta is exactly 0.5. So then we collect our data, and it says, I don't think so. Beta is not 0.5. It's somewhere above 0.6, more likely. Right? And then what happens to our posterior? Our posterior says, well, I don't know, you were very sure. I'm going to kind of ignore the data because of how sure you were. So this is, of course, the problem with extremely informative priors, right? No amount of data is going to knock you off them. Here, the red curve almost overlaps with the blue curve. So the red curve in the previous examples is the posterior. The posterior is the distribution of the parameter given the data. In Bayesian statistics, that's everything. If you give someone the posterior, that's it. You've given them everything. That's the summary of evidence as far as a Bayesian is concerned. But it's a curve. It's hard to work with. You can only look at it in graphs. And then if you have multiple dimensions, it gets even worse. So, we want to summarize it. Well, one way to summarize that curve is by its mean, right? The associated mean, the posterior mean. Another way to summarize it is by its variance, the posterior variance. But we might want something analogous to a confidence interval. But a confidence interval is a frequentist property. It talks about supposed fictitious repetitions of experiments. That's not within the Bayesian ideology, really. So we need something that's analogous to a confidence interval. For a likelihood, we had something that was analogous to a confidence interval. We called it a likelihood interval. So the Bayesians created something, and they called it a credible interval. So the Bayesian credible interval is just the analog of a confidence interval. So a 95% credible interval, A to B, just satisfies that the probability that the parameter lies in that interval given the data, is 95%. Really simple. If you believe in the Bayesian inference, higher values of the posterior represent kind of better supported values of the parameter. So just like the likelihood, you're better off chopping off the posterior with a horizontal line and figuring out exactly what values of A and B that entails to force it to be 95%. And that's called the highest posterior density interval. And I have a picture here where I kind of do that. So if you can imagine this horizontal line, the red area would vary as we moved it up and down. As we moved it down, the red area would get bigger and bigger. As we moved it up and up, the red area would get smaller and smaller. So you want to keep moving that horizontal line up and down until the red area is exactly 95%, right? And this is a density, so that would be the area under the curve is exactly 0.95. So once you hit that perfect point where it's exactly 0.95, then see where it intersects the curve and then drop down to the horizontal axis, and those 2 points are your A and B. So the probability P lies between that A and B is, of course, just the integral between those points, which is exactly the red area. So you wind up with a credible interval. In this case, it works out to be 0.44 to 0.84, which should be no surprise. And in R, you can do that with the binom package. In this case, binom.Bayes, 1320, 13 successes, 20 trials. And you have to do type equals highest, and that gives you the 95% credible interval, and it uses a Jeffreys prior. As I said earlier, Bayesian credible intervals, even though they're constructed using Bayesian thinking, if you turn around and evaluate them with frequentist performance, they tend to perform very well. Just like our Agresti-Cool interval, which wasn't exactly a Bayesian confidence interval, but was close enough among friends, that actually has much better performance than the directly CLT constructed Wald interval. The other thing I want to mention before I go through the final bit of this lecture is that another way to create a confidence interval would be to pick A to be the lower 2.5th percentile of the posterior distribution and pick B to be the 97.5th percentile of the posterior distribution, and that would give you exactly a 95% interval, for example. But the posterior height of the lower point and the posterior height of the upper point would be different. So that is potentially a problem. On the other hand, if you do the HPD interval, you got to vary this line. You have to solve a root equation to obtain them. So it's a little bit annoying. And finding the percentile interval, the so-called percentile interval, the lower 2.5th percentile and the upper 97.5th percentile as an example to get a 95% credible interval is very easy. So another way to construct a Bayesian credible interval is just to take the lower and upper percentile and run with it that way. I think you're better off doing the HPD interval if you can. So I want to end with one nice aspect of the Bayesian credible interval if you're hardcore about these things. So let me just say for a minute about what I mean by being hardcore. So probably many of you have taken an introductory statistics class, and probably many of you have seen the baffling interpretation associated with frequentist confidence intervals presented as a test question. And that is just, kind of hardball frequentist, and it's accurate. I don't want to criticize it. It's accurate. And so here's an example. We have a Wald interval. It works out to be 0.44 to 0.86. And let's assume that the 95% coverage of the Wald interval is good enough. The CLT is kicked in this case, and we're fine. And we're not worried about the mathematical performance of the confidence interval. We're interested in just the strict interpretation, assuming that the coverage is correct. Then the fuzzy interpretation is that we're 95% confident that P lies between 0.44 to 0.86, but that's not the actual interpretation. The actual interpretation is the interval 0.44 to 0.86 was constructed such that in repeated independent experiments, 95% of the intervals obtained would contain P. That's the actual confidence interval interpretation. It's this idea, performance frequentist refers to frequency, i.e. the definition of probability of being entirely entwined with fictitious repetitions of experiments or lifetime batting averages for success probabilities and that sort of thing. That's what frequency interpretation is. The actual interpretation is almost exactly no one interprets frequentist confidence intervals this way because it's such a mouthful. Everyone just kind of thinks, well, my interval 0.44 to 0.86 is an interval that accounts for uncertainty at a kind of control rate of about 95%, where that control rate has a contextual meaning with respect to frequentist statistics, and I understand that, but I don't spit it out every time I interpret the confidence interval. Every now and then a confidence interval makes its way into the news, and news people never interpret it right because it's hard to interpret. So the likelihood interval, let's go on to the next one. The likelihood interval was 0.42 to 0.84, the 1/8 likelihood interval. And the fuzzy interpretation for the likelihood interval is that the interval 0.42 to 0.84 represents plausible values of p, here plausible defined by the 8-fold likelihood ratio associated with the endpoints relative to the MLE. So yeah, that's okay. And so the fuzzy interpretation is okay. It's no worse than the frequentist fuzzy interpretation. But the actual interpretation, let's go through it. The interval 0.42 to 0.84 represents plausible values for p in the sense that for each point in the interval, there is no other point that is more than 8 times better supported given the data. Again, yikes, this is a mouthful. And, anyone who constructs a likelihood interval is not going to interpret it that way. They're going to say, it's an interval. It accounts for uncertainty. It's based on the likelihood. The calibration is based on sort of 8-fold likelihood ratios, and I understand what it means, but I don't spit it out every time I use the interval. The nice thing about the Bayesian interval is you could spit out the actual interpretation every single time you use it because the interpretation is very easy. So the Jeffreys 95% credible interval was 0.44 to 0.84. The actual interpretation is the probability that p lies between 0.44 and 0.84 is 95%, full stop. So that's super easy. Now, there's a lot loaded in this word probability here because it's the Bayesian version of the word probability that maybe not everyone would like to agree with, and not everyone would like something that's more objective or something like that. But nonetheless, if you're willing to buy into the Bayesian way of thinking, the simple interpretation of the credible intervals is quite nice. And this interpretation is, if you see a confidence interval in the news or you present a confidence interval to people who have just a little bit of statistics, this is how they want to interpret confidence intervals. And you can't say this statement for a frequentist interval, the probability that p is between 0.4 and 0.84 is 95%. Because in a frequentist way of thinking, the p is just a fixed parameter. It's either in the specific interval or not. It's not random. So the probability is either 0 or 1. I mean, if you're being a hardball frequentist, you can't make this statement. I've had, people who have frequentist leanings say, yeah, you can just go ahead and make the statement because frequentist intervals can approximate Bayesian intervals of sorts, and they're fine with that. So I think in all the cases, the kind of fuzzy interpretation that all the intervals, they agree for one thing, and then second of all of them measure some amount of uncertainty associated with our point estimate. They're calibrated in some way in the likelihood interval, calibrated relative to likelihood ratios, in the frequentist interval calibrated relative to frequentist coverage rate, and in the Bayesian interval calibrated relative to posterior coverage. So that gives you a sense of Bayesian interval, likelihood interval, and frequentist intervals for the exact same problem. This is an interesting area. Bayesian statistics is quite popular, and it's a good thing to know about. Bayesian statistics, even if you are a frequentist, use of the Bayesian manipulations frequently turns out to be a very good way to create, say, confidence intervals or hypothesis tests. It's just a very useful way to think about statistics. Well, that's the end of today's lecture, and I hope you enjoyed it. And if you're interested in reading about Bayesian statistics, there's tons of good stuff on the web, and it's a very interesting area, and I hope you do so. I look forward to seeing you next time for our very last lecture. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 14 on logs. In this lecture, we're going to talk about what it means to log data and what impact that has when you do things like take arithmetic means of logged data and create confidence intervals and this sort of thing. So we'll talk about logs, we'll talk about the geometric mean, which is intrinsically related to taking logs of data and taking arithmetic means. We'll talk about the geometric mean and its relationship with the law of large numbers and the central limit theorem. And then we'll go through some of the existing techniques that we've already gone through, like creating t-confidence intervals, but just go over how they're interpreted with respect to log data. And then we'll finish talking about the log normal distribution. So just to remind everyone a little bit about logs, log base b of the number x is the number y such that b to the y equals x. And log base b of 1 is always going to be 0 because b to the 0 is going to equal 1. And then this log base b will always travel to minus infinity as x travels to 0. And then, for the class, we've always been writing just log as when the base is e for Euler's number, and sometimes people tend to write ln in that case. There's basically only 3 bases for logs that people ever use. Base e has a lot of nice mathematical properties. Base 10 is nice because then log speaks of orders of magnitude, right? Log base 10 of 10 is 1, log base 10 of 100 is 2, log base 10 of 1,000 is 3, and so on. And then log base 2 is often very useful as well. Because it's a smaller number than 10, you get lower powers, it's often useful. And just to remind everyone, log AB is log A plus log B, log A raised to the B power is B log A, and log A divided by B is log A minus log B. In other words, log turns multiplication into addition, division into subtraction, and powers into multiplication. So hopefully none of this is news to you. So that's sort of the mathematical properties of log, but statistically, why do we take logs of data? The most common reason to take a log of data is if the data is sort of skewed high. And what I mean by that, for example, is incomes are a great traditional example of things that tend to be skewed high. You have a lot of people making very little money and a handful of people making a lot of money. And so that distribution looks like a hump towards 0, and it spreads out with a long tail towards high values. And sometimes you might take logs of income data to try and make it look more bell-shaped. This occurs frequently in biostatistics. For example, health expenditures. A lot of people tend to spend very little on healthcare until healthcare becomes a problem. Then they spend a lot. So distributions like healthcare expenditures and other things like that tend to be right skewed, especially because they're bounded from below by 0. In settings where errors are feasibly multiplicative, when dealing in things like concentrations and rates, then it's natural to take logs because then it turns that multiplication into addition. Whenever you're considering ratios, it's useful to take logs because then instead you have differences rather than ratios. And then if you're dealing with something where you're not so concerned about the specific number, but more concerned about the orders of magnitude, say something like using log base 10, as an example, if you're considering astronomical distances, you might be just more concerned with the orders of magnitude rather than the actual specific number. Then you might often take logs. And then counts are often logged. If your data are the number of, say, infections at a hospital or something like that, you might log data like that. Notice if you have several counts and one of them 0, then you have a problem with taking logs. So you have to come up with some solution for that. So let me talk a little bit about the geometric mean. The sample, I say the sample geometric mean just so we're using the same notation when we talked about the sample mean of data. The sample geometric mean of data set x1 to xn is you take the product of the observations, pi I equals 1 to n, xi, and then you raise it to the 1 over nth power. And notice if all the x's are positive, which is generally the case if you're thinking about geometric means, then the log of the geometric mean is then the arithmetic mean, 1 over n summation log xi. So it's the arithmetic mean of the logged observations. Okay, so let me just repeat that. The log of the geometric mean is the arithmetic mean of the log observations. So because the log of the geometric mean is the arithmetic mean of the log observations, on the log scale, the geometric mean has all these properties that we already talked about associated with sample means, sample arithmetic means. So the law of large numbers applies and the central limit theorem applies. I have a parentheses here that says under what assumptions, but under whatever the assumptions applied for the arithmetic mean to have the law of large numbers and the central limit theorem. The geometric mean, by the way, is always less than or equal to the sample or arithmetic mean as a just general property. So let me just give you a quick example of using geometric means. In some domains, people use the geometric mean so frequently that when they talk about mean, they're referring to the geometric mean, not the arithmetic mean. So as an example, when what you're thinking about is inherently multiplicative, you would often think of the geometric mean. So suppose that in a population of interest, the prevalence of a disease rose 2% one year, and then the next year it fell 1%, And then the year after that, it rose 2%. And then it rose 1% again. Well, if you're thinking about what's the end prevalence of the disease after the starting prevalence, inherently you would multiply the starting prevalence times 1.02 times 0.99 times 1.02 times 1.01, and you would get the ending prevalence. So the geometric mean of these collection of increases and decreases would be a relevant quantity to study, and so that geometric mean would be the product of them raised to the 1/4 power. And what's interesting about that then is if you take the starting prevalence and you multiply it times 1.02, 0.99, 1.02, and 1.01, you get the ending prevalence after the 4 years. If you take the geometric mean and multiply it times the starting prevalence 4 times, you get the same number. So that's what the geometric mean is considered in the sense of the arithmetic mean. The arithmetic mean is the number you would have to add 4 times to get the same end result. The geometric mean is the one you have to multiply 4 times to get the same result. And that's why it's useful. So if you're thinking about things that are inherently multiplicative, like percent increases and decreases, then it's common to take the geometric mean. So if you work in certain financial sectors, for example, if they say mean, they are referring to the geometric mean because it's obviously more natural to talk about. Okay, so just rehashing some of these points. Multiplying the initial prevalence by 1.01 to the 4th power, in other words, multiplying it 4 times, is the same thing as multiplying by the original 4 numbers in sequence. So 1.01 is the constant factor by which you would need to multiply the initial prevalence each year to achieve the same overall increase or decrease in prevalence over a 4-year period. Take that in contrast to the arithmetic mean, and that's the factor by which you would have to add to achieve the same total increase. And in this case, it's clear, to me at least, that the geometric mean makes a lot more sense than the arithmetic mean to talk about. On the next slide, I was thinking about how to explain this. I Googled the geometric mean and the arithmetic mean, and I found this great example at the University of Toronto's website. And it has a really fun geometric interpretation of the arithmetic mean and the geometric mean. So if you have a rectangle, and A and B are the lengths of the sides of a rectangle, then the arithmetic mean, A plus B over 2, is the length of the sides of the square that has the same perimeter as the rectangle. The geometric mean, A times B to the 1/2, is the length of the sides of the square that has the same area. So if you're sort of interested in multiplicative things like areas, you want the geometric mean of the sides. If you're interested in additive things like perimeters, you want the arithmetic mean. So I thought that was really cool when I read that. So back to statistics, the log of the sample geometric mean is just an average. And so provided the expected value of log x exists, then that average has to converge just by the law of the large numbers to what I'm defining here as mu equal to the expected value of log x. So remember, the log of the geometric mean is itself just an arithmetic mean. We have the law of large numbers, which tells us what the arithmetic mean converges to. It converges to the population mean. So therefore, the log geometric mean converges to expected value of log x, where x is a draw from the original population on the natural unit scale, not on the log scale. Therefore, if you want to know what the geometric mean converges to, the geometric mean is the exponential of the log of the geometric mean, of course, because e to the log x is x. So it would be nice if that worked out to be expected value of x, but it doesn't, because e to the expected value of log x, the exponent can't move inside this expected value. So we get something which I'm going to just call e to the mu. It is exactly e to the mu. And this is not expected value of x. And this quantity e to the mu, which is the exponent of the expected value of log x, it doesn't really have a name, but I like to call it the population geometric mean. Because, if you have that the sample arithmetic mean converges to the population mean, the sample variance converges to the population variance, the sample median converges to population median, then by that logic, the sample geometric mean should converge to something that's called the population geometric mean. So I'm going to call it that. I don't see that too often in books, but what the heck, I'm going to do it. So to reiterate, the exponent of the expected value of log x is not equal to the expected value of the exponent of log x, which is equal to e to the x. So what I'm referring to as the population geometric mean is not equal to the population mean that we defined earlier. It is, however, interesting to note that if the distribution of log x is symmetric, which remember, that was one of the reasons at the beginning of the lecture we stated for taking logs of data is to turn skewed data to data that's more symmetric, then if the distribution of log x is symmetric, then consider the median. The median is the point where 0.5 is equal to probability that log x being less than or equal to mu. And in this case, because log x is symmetric, mu, the mean on the log scale, is in fact also the median. So this first statement, 0.5 equal to the probability log x less than or equal to mu, is just reiterating the statement that for this distribution that's symmetric on the log scale, the mean and the median on the log scale are equal. But now on the interior of this probability statement, we can, because everything's positive and because the E function is monotonic, we can take an exponent on both sides of this inequality and get that the probability that x on the natural scale, not on the log scale, but x on the natural scale, the probability that x is less than or equal to e to the mu is also 50%. So the conclusion is that for log symmetric distributions, the geometric mean is estimating the median. So why am I saying all this? I'm making fairly simple ideas rather complicated. The idea is you have data, you log it, and you just do all the normal stuff you do with your data, you're just using it on log data. And what I'm trying to say is I'm trying to relate the quantities that you get from doing that, they have interpretations back on the natural scale. That's what we're trying to say. You don't have to discard the natural scale units when you log data. You get a lot of interesting interpretations back on the natural scale. So at any rate, if you use the central limit theorem to create a confidence interval for the log measurements, then your interval is estimating mu, the expected value of the log measurements, the expected value of log x for log units. Then if you exponentiate the interval, then you're estimating e to the mu, the population geometric mean as I'm calling it. And then in the event the distribution of the log data is itself symmetric, then your exponentiated interval is also estimating the median. So this is kind of a backhanded way of getting a confidence interval for the median. If you're willing to assume that your data is symmetric, the population from which your data is drawn is symmetric on the log scale, then when you take the log of the data, create the confidence interval, and then exponentiate the endpoints, then you wind up with a confidence interval for the median. And remember, we also talked about getting a confidence interval for the median using bootstrapping, but this is a lot easier. It just uses the ordinary t confidence interval. And then this is especially useful for paired data when their ratio is of interest. So let's just quickly go through an example. So remember, I quoted before this book by Rosner, Fundamentals of Biostatistics, which I like. It's very thorough and covers a huge chunk of biostatistical topics. At any rate, on page 298 of the version that I have, which unfortunately I think was the previous version than the current one, it gives a paired design where it compared systolic blood pressure for people taking oral contraceptives and matched controls. And so paired design is where you have a person and you have a bunch of covariates that you're concerned with when you want to compare, say, oral contraceptive use to controls. You're worried that the group of people that take oral contraceptives are different than the group of people who don't take oral contraceptives. So what you might do is you might take this list of things that you think might explain that difference and match on them so that the person taking the oral contraceptive, they have a twin, in a sense, in the control group that, at least insofar as the other variables that you can measure, they're very close. That's this idea of matching. The matching to the extreme, you couldn't do it in this experiment, but imagine if you were investigating aspirin, you would give, say, a person an aspirin, and then after a suitable washout period, give them a placebo. And then that person would be perfectly matched to themselves as their own control. So that's the extreme version of this case. But let's suppose you're in a circumstance like this where you can't really randomize people to contraceptive use. You couldn't do a crossover experiment like that. So you could match people as closely as you could on all these other things that you think might differentiate contraceptive users from controls and match them as closely as possible. Anyway, that's a match design. But the point for our discussion is that person one, who is in the oral contraceptive group, and person one, who's in the control group, they are tied together. And so we want to utilize that information that they're similar. So what we might do is take the blood pressure for person one from the oral contraceptive use and the systolic blood pressure from person 1 in the control group and analyze their ratios, right? And so we might be interested in ratios because we just might be interested in the interpretation of, well, what percent increase and decrease does a person in the contraceptive group have over their associated controls? So imagine if we took ratios and then logged the ratio. Well, that would just be the log difference of the two measurements. Then we could just do an ordinary one sample T confidence interval for the log of the ratios done matched pair by matched pair. And so in this case, the geometric mean of the ratios works out to be 1.04, which in this case, the order in which I was dividing implied a 4% increase in systolic blood pressure for the oral contraceptive users. And the T interval on the log scale, so when I took each measurement, an oral contraceptive user logged the control user, took the difference pair by pair. I wound up with then N measurements where I started with 2N total measurements, each in pairs. I had my N measurements on the log scale. I did an ordinary T interval, and I calculated it. I got 0.010 and 0.067. In this case, the units would be in log millimeters of mercury. What we're interested in on the log scale is whether 0 is in this interval or not, right? 0 is the important thing on the log scale. If we exponentiate the interval, we get 1.01 to 1.069. So an estimated via a 95% confidence interval, 1% to 7% increase in systolic blood pressure for the oral contraceptive users relative to the controls. And so on the exponentiated scale, we're interested in whether 1 is in the interval. On the log scale, we're interested in whether 0 is in the interval. By the way, if your numbers are kind of small, like in this case 0.01 and 0.067, exponentiating is about like 1 plus. And if you're a math person, you take the Taylor expansion of e to the x and go out one term, and you see that it's pretty close to 1 plus. So you can actually exponentiate things very quickly, but just by taking 1 plus. And then obviously if your number that you're looking at is pretty close to 1 and you want to log it, you can do 1 minus, and you, same thing, take the Taylor expansion for log and go out one term. You can see if the number's close to 0 and you want to exponentiate it, 1 plus works pretty well as an approximation. If the number's pretty close to 1 and you want to log it, 1 minus does pretty well as well. That's a trick that's very useful, like when you do logistic regression and things like this where you need to take exponents quickly. So let me just talk about this example just a little bit more. This estimate, 1.01 to 1.07, this 1% to 7% estimated increase between the two groups, that is a confidence interval for this sort of paired ratio of geometric means. And that's why it's useful in that we're estimating a ratio here. So now let's just go through the same exact exercise, but instead of when we have paired observation and we have two independent groups. If you log the data from group 1, log the data from group 2, create a confidence interval for the difference in the group means on the log scale, and then exponentiate it, then what you're estimating, that confidence interval, is an estimate of e to the mu1 divided by e to the mu2. That confidence interval is exactly an estimate of the ratio of the population geometric means. Of course, it's an estimate on the log scale of the difference in the expected values on the mean on the log scale. But if you exponentiate it, then you get exactly an interval for the ratio of the population geometric means. And if you're willing to assume that the data is symmetric in the log scale, then this is also equal to a ratio in the population medians. There's one distribution where take logs of things and they wind up as Gaussian is so important that we give it a name. We call it the log normal distribution. And a random variable is log normally distributed if its log is a normally distributed random variable. Note, it's not the log of a normal random variable, as its name kind of implies. You can't take the log of a normal random variable because those can be negative and you can't take the log of them. So if you want to remember what's a log normal random variable, remember this phrase. I am log normal means take logs of me, then I'll be normal. And then you'll remember the correct order. But then also think, when you're assuming what the log normal is, if you're taking the log of something that's possibly negative, then you're doing it wrong. Okay, so again, log normal random variables are not logs of normal random variables. As I stay here, you can't even take the log of a normal random variable because it can be negative. So formally, x is log normal, and it depends on two parameters, mu and sigma squared, if log of x is normal mu comma sigma squared. And again, that mirrors kind of what we're often doing with logs. We're trying to take logs of things so that on the log scale, the data is symmetric, and then hopefully the population distribution is also symmetric. And if log of x is normal, for x being log normal, then if y is normal mu comma sigma squared, then e to the y is log normal. So you can generate a log normal by generating a normal random variable and exponentiating it. I give you the log normal density here if you want to. It depends on the mu and the sigma squared. Its mean is e to the mu plus sigma squared over 2, where mu and sigma squared are these mean invariants on the log scale. And the variance is 2 mu plus sigma squared times e to the sigma squared minus 1. And its median is e to the mu. And of course, its geometric, what I'm calling its population geometric mean, is e to the mu as well. So you can see here, this gives you an exact example where expected value of x and e to the expected value of log x are two different things. Expected value of x, in this case when x is log normal, is e to the mu plus sigma squared over 2. E to the expected value of log x is e to the mu. Okay, so if x1 to xn are log normal mu sigma squared, then log x1 to log xn, where I'm calling those yn, y1 up to yn are normally distributed with mean mu and variance sigma squared, so they satisfy the conditions to create a t confidence interval, and then mu is the log of the median of the xi. E to the mu then gives the median on the original scale. It also gives you the population geometric mean. And then again, assuming log normality and exponentiating t confidence intervals for the difference in two logs again implies that your confidence interval is estimating ratios of geometric means. So let's just go through a quick example of doing this. Now, I'm assuming you can do the arithmetic of this because you already know how to create two-group t confidence intervals. So all that we're doing is logging the data and doing something you already know how to do. So I just want to go through the interpretation real quick. So imagine if you took gray matter volumes. I actually did this for some data that I have. I have brain gray matter volumes for a young and an old group defined as younger than 65 and older than 65. But of course, this doesn't account for being young at heart or whatever. Young and old as per my definition. But if you're 65, rest assured, I don't think you're old. It's just the definition I'm doing here. So we did two separate group intervals. And for the old group got 13.24 to 13.27. And for the younger group got 13.29 to 13.31. Both of them are in the units of log cubic centimeters. If you exponentiate those intervals, you get 564 for one group and 578 about for the other one, and 592 to 606 cubic centimeters for both for old and young, respectively. So both of these intervals estimate the population geometric mean gray matter volume among the older and younger groups, respectively. If we're willing to assume that the population of brain volumes on the log scale are symmetric, then both of these intervals estimate the population median gray matter volume for old and young, respectively. Then if we were to take the two groups and do a two-group t interval on the log measurements yields 0.032 to 0.066 log cubic centimeters, exponentiate this, you get an interval of 1.032 to 1.068. Again, remember the trick. You add 1 when you exponentiate it close to 0. You wind up with about a 3% to 7% higher geometric mean brain volume among the younger group than the older group. Or if we're talking about medians, if we're willing to assume that individual populations are symmetrically distributed, then that would be estimated between 3 and 7% increase in gray matter volume for the younger group. This, of course, being the case because as we age, we start to lose a little bit of gray matter volume over time. Of course, you develop more neuronal connections, so you get wiser. So you have maybe more neuronal connections, but decrease in volume. So any rate, what I hope you learned from this was when you take logs of measurements and do what we talked about in terms of creating confidence intervals and exponentiate the intervals, I hope you know what the estimates are then referring to. And it's a common problem. People do this all the time, but I'm not sure people always understand exactly what they're doing. And that's why I devote an entire lecture to the subject of logging, which is in practice is a trivial extension of what we've already done. Take logs of your data, do what we already do, and then exponentiate the intervals. So no change in what we're doing. But I wanted everyone to understand exactly what the implications of those things were and why log is sort of special in the sense that it yields uniquely interpretable results as opposed to doing other functions. You could take, say, cube root of the data, create the confidence interval on the cube root scale, and then raise the interval to the third power, and you wouldn't get the same nice interpretations like you do with log. Log is special that way. All right. Well, thanks, troops. This was our last lecture. I hope you enjoyed the class and hope you survived the intense biostatistical training. And I hope you go on to do great things with this knowledge and all the other courses you take from Coursera.